Okay, welcome everybody. Good morning, good afternoon, good evening from wherever in the world you are joining us today. Welcome to this virtual conference on earthworms, water fleas and algae, the future of wastewater treatment. My name is David Tompkins. I'm the Head of Knowledge Exchange and Innovation here at Aqua Enviro. It is my pleasure to welcome you to today's conference. For those who don't know us, Aqua Enviro is a UK-based wastewater consultancy specialising largely in biological treatment from proof of concept to troubleshooting at wastewater and biowaste facilities. We're one of 19 partners in the INNOQUA project. You will hear more about other partners, and other partners will be presenting throughout today's proceedings. And our role specifically has been to support the communication and dissemination activities of INNOQUA, which is just coming to a close at the end of this month. So the objectives of this event today are three, as listed on the screen. For me, the third objective is probably the most important. It's particularly important for the INNOQUA consortium as a whole, and hopefully for many of you who are joining us today. As you'll hear through the proceedings, there are clear opportunities for commercialization of parts of the INNOQUA system, while others require further research and development. Consortium members are keen to be involved in further development of INNOQUA and also other projects. So please take advantage of the chat and networking functions to make new contacts or perhaps to revive existing contacts. You will have noticed in the emails that came around yesterday that we're using two event spaces. You have links to both of these spaces. The first is room 1, where we are now. This is a Zoom webinar, not a meeting. So only panelists can share video and audio in this room. If you have any questions, please just type them in the chat box in the normal way. If your question is for a specific presenter, then it'd be really helpful if you could start your question with kind of the @ symbol and then their name, or make it clear who your question is directed at. That would be very helpful for the facilitators. In the later part of the conference, we will open a second room, this one as a Zoom meeting, a conventional Zoom meeting I'm sure many of you are familiar with, and everyone in that space will be able to share their video and audio. There's no problem moving between those spaces. You can do so at your leisure, but to keep it simple and to minimize potential for clashing, just close all existing Zoom windows, Zoom apps when you want to move. Find the link to the space you need in the email I sent yesterday or in the little chart I pulled together, because they both link to the same spaces. Just so find the link to the space you want, click on that, start a new meeting, and you'll rejoin where you need to be. Finally, in terms of housekeeping, just to let you know that each of the main conference sessions has a facilitator. I will facilitate the first session before handing over to Eoghan Clifford from NUIG Galway, who will then hand over to Jean-Baptiste Dussaussois from NOBATEK for the third session in the main conference. Our roles are the same in each session: to ask questions of the panelists and to keep us to time. The conference program is very structured, with each session comprising 4 presentations followed by a discussion. But this structure does give us some room for maneuver. So the most important thing is that we start sessions 2 and session 3 on time, as we might have delegates dialing in just for those parts of the program. So we might have to flex the length of the breaks a little bit, but don't worry, the facilitators will keep you up to speed. And if you need any guidance, just send me a private message in the chat or send me an email directly. So that's all what I wanted to say, other than, again, welcome to this conference. I hope you enjoy it. I hope you get something incredible out of it. And I'll now show a short introductory film about the INNOQUA project before I hand over to Jean-Baptiste. So I will now attempt to not break the technology. Okay, it gives me great pleasure at this point to hand over to our first presenter of the day, Jean-Baptiste Dussaussois from NOBATEK. Jean-Baptiste has been a very able coordinator for the INNOQUA project, and it gives me great pleasure to hand the floor to you now, Jean-Baptiste. So please feel free to share your screen and start your presentation when you like.
Okay, well, so good morning, everyone. Good afternoon or good evening to where you are worldwide. I hope that you can see my screen now. So thank you, David, for this introduction. Thank you for sharing video, and welcome to everyone to this conference. I'm really happy to present you today the overall situation of the INNOQUA project that we started now 4 years ago. So basically, the idea is that, we have many wastewater treatment issues worldwide. In some cases, even still exists a lot of wastewater treatment solution. In some cases, can request a lot of maintenance, high cost, or space requirements, or in some cases also we don't have any collective network to collect this water to be treated properly. So basically, the point is that, of course, of this wastewater, which is flowed directly into environment, can lead to many issues. And as we can see in the video, and today we estimate that 2.6 billion people worldwide don't have access to appropriate sanitation. So that's why we decided to start this project to develop a nature-based wastewater treatment solution to answer to this issue, which is, of course, an issue about wastewater quality, about water bodies protections, but also about health, economical growth, and also development of population, because now we are in a world where population is going to grow, and more people are going to live in urban area, meaning that we have to take care of this issue about the wastewater treatment, both in urban and rural area. So I'm going to give you an overview of the project. So I'm Jean-Baptiste Dussaussois. I'm the project coordinator of the INNOQUA project. And I'm working with NOBATEK. I'm located in France, more exactly in Biarritz, so southwest of France, close to the border with Spain. And so my company, NOBATEK, is a research and technology organization where we are developing a solution for the sector of the sustainable building. So meaning that we are not only focused on wastewater treatment, we are also developing energy and economical solutions, tools, and so on. And I'm in charge of the water aspect. So basically, the commitment of our project that we started 4 years ago, but now an extension, an unexpected extension of 6 months, because as David mentioned, we're going to have our project over by the end of the month. So was to develop a decentralized wastewater treatment solution which can fit with global north and global south country, even if I'm not really fine with this kind of what to say, global north or global south, but meaning in different conditions, which can fit with urban and rural area, meaning that in some location we don't have many space available to install a system, where in some cases we don't have any collective network to collect the wastewater. And so we decided to develop this project through 4 years research and development activities with 20 different partners. So let's say that in this project, the key point is, and let's say the look we have, is having partners from broader reasons. As you can see, we have some technology providers. We have also partners who are in charge of exploitation, market building, but also to make sure that we can perfectly understand what are the market and ground needs, which is really important if we want to develop a system which can fit with the market, the ground issue we can find. So we also have system integrator and field demonstration, because in such a long project, of course, we have tested our technologies in different conditions and in real conditions. And we also have developing countries expertise to make sure that we catch all the aspects from this type of market. Basically, the idea and specification we have intended to develop in this project is to have market study. As I mentioned, it's really important to make sure that we can understand what we are developing and if it fits with the final requirements, which can be for mainly for the end users. And one point which is really important in such project is make sure that, and especially I mean with wastewater treatment, is make sure that we can have a social acceptance of. It doesn't make sense to develop a system which is not accepted by the end user at the end of the project, where we have a product ready for market. Of course, of technologies have to respect the legal requirements, which is also really important to make sure that we can have access to market. We also conducted different assessment, and especially environmental and cost assessments through LC and LCC assessment, because we were really willing to make sure that we can have the less impacted system on the environment and the more cost-effective system, because we already pointed the fact that the cost can be a limited factor and a barrier for the development of wastewater treatment solution and the implementations. And basically, of course, and finally, I mean, we are developing communication activities, and you can find a lot of information on our website, so INNOQUA project, if you want further details later on. Basically, what is the INNOQUA system? So today we would like to discuss about the INNOQUA system through 4 different technologies. The idea of the INNOQUA system is to make sure that we can have a modular system, meaning that according to the condition we are facing and the regulation we want to respect, or water quality we want at the outlet of the system, we can plug the system differently through different combinations. So I'm going to present you briefly the different technology. After me, my colleagues will present you more, let's say, deeper on more technically the system. But so the different technologies are as following. So the first one, which is installed on our demonstration site that I will show you later on, is the Lumbrifilter. So basically, it's a filter where we show your raw wastewater. So you can put directly your raw wastewater or after a settlement tank, your wastewater at the top of your system, and you have a percolation from the top to the bottom of your system, and different layers of organic and inorganic matter, where we have development of aerobic and aerobic bacteria. And basically, the principle of the system is that thanks to earthworms, we avoid having any collapsing of our system, especially at the top of the layer, meaning that we can reduce the maintenance of the system. So we have called this system the Lumbrifilter, which is quite similar to other systems which can exist, which are mainly called Vermifilter, and we will discuss in another session today. So this is the first technology. The second one is the Daphniafilter. So basically, this also is called a filter, but basically it's a tank full of water where we have a development of biofilm, microalgae, and Daphnia, which allows us to decrease the thinner part of totally suspended solid we can have in water, and which can act as a secondary treatment system. And we also have installed this system after the Lumbrifilter in different conditions. Fourth technology is the BSP, stands for BioSolar Purification system. So it's a single-use system, a recirculating system, where we have our wastewater after the primary and secondary treatment used to flow from the top of this ramp to the bottom and recirculated. And thanks to the thin layer and development of algae, and thanks to action of the UV radiation, we can decrease organic matter, but also we can decrease pathogens which are present in this wastewater treatment, and this wastewater, sorry. So basically, this is a tertiary treatment system. It's exactly the same as a more common system, which is a fourth technology, which is the UV system. Basically, this is the UV lamps, which is, let's say, well known, and which allows disinfection of wastewater as a tertiary treatment. Basically, what we did in this project, so we have tried to better understand the system, because there are nature-based solutions. So the first one was to clearly understand what are the system, what are their boundaries, what are the limits where we can have the system working properly. And so we have realized we have completed different tests University of Galway, but at University of Girona in Spain. And here you can see a picture of different tests we have completed, especially about Lumbrifilter and efficiency of the system. So, because as I told you, the point in such projects is just to make sure that we can have a compact system which can fit with the market's needs. So it doesn't make sense having a really large system if we can just find the boundary of the system and make sure that you can have a really compact system with the same efficiency. So this was we did for several months at the beginning of the project, meaning that make sure that we can understand the system and test the limit. So this was mainly lab scale test. Then we have moved to a second phase of the project where we have tested in such called pilot scale or system, meaning it was in, or it is in real condition, but controlled conditions. So basically we have used bypass from sewage treatment plant just to make sure that we can have real wastewater effluent go to our system, and we have tested our system with overloading, with shutdown period and different aspects to clearly understand the efficiency of the system, also the dosing arrangement that we can set to the different technology, because this is also really important for the efficiency of the system at whole. And so we have moved to the third and last phase of the project, starting now about 20 months or 18 or 20 months ago. So it's a demonstration phase, meaning that we have installed our system in real conditions and non-controlled conditions. So when I mean non-controlled conditions, this means that we have treated and we are still treating wastewater directly from what's happened in reality. So sometimes we have an overflow, which can represent 200 and 300 of overloadings. We can have shutdown period, and this was the case unfortunately due to the sanitary situation with lockdown in some case, where in some of our sites we did not have production of wastewater. So this is absolutely a real condition where we have tested our system, but of course we have monitored the system to make sure that they can respect regulation and make sure that they can fit with the local demands of wastewater treatment system. So basically, you can see that you have a LBF for stand for Lumbrifilter, UV for the UV lamp, DF for the Daphniafilter, and the BSP for the solar system. So we have tried several combinations of systems to make sure that it can fit with what we can expect from the system and the regulations. So for doing that, we have different representative specific case, and there's a case in Galway, in Ireland, where we are treating some wastewater coming from cattle farming, so the dairy wastewater. And also another one, which is the second French one, in Lacanau, the city in France, where we have treating not directly the wastewater from the aquaculture site, but the sludge producing by another system. So that's why we are not developing here and tested the Lumbrifiltration itself, but the Lumbricomposting. So basically the challenge of doing this was as follows, meaning that, as you can see, so this is the main parameters of water quality at the inlet of our system. So as you can see, for instance, for the TSS, we have absolutely a broad range of TSS from Ireland, which can be considered as really high, and in Tanzania, where it can be, let's say, for small concentration of TSS. This is a volume that we expected to treat. So as you understood, so the system is set for decentralized wastewater solution, meaning that we are treating up to 2.4. In fact, it was something like almost 3 cubic meters per day maximum, but make sure that we can have a system which can be directly plugged on a building, on your system, or on your toilet, and can work directly because it's NBS solutions. We also were facing a challenge, which is about regulation we have to respect. So basically, it's an overview of regulation we have to respect at the outlet of our system. So for discharge in the environment, even if in some cases that I will show you and my colleagues will present you later on, we also intend, thanks to modularity of the system, to make sure that we can reuse the water at the outlet of our system. For instance, if we just put the Lumbrifilter, you mostly won't be able to reuse water according to the regulation you have in your country. But if you want to be able to make sure that you can reuse for irrigation of crops or other reuse purposes, you can plug other INNOQUA modules to reach this efficiency at the outlet of your system. So I don't going to take too much time, but basically, so just give you some view and pictures about the system. They are, meaning that you have here the seat, so meaning on the left part, the Indian demonstration site during the installation. You have the French one here, which is plugged directly on the NOBATEK office in France during the construction, and also here in Ecuador. So just to show you, so for the Ecuador side, so we started with only this, and now we have, let's say, a nice installation and integration of the system itself, which was really important in that case, because this was at the main entrance of an office, which used to receive publics. And meaning this can be really important to explain that, of course, we have a wastewater treatment just under the terrace, but it doesn't smell, it doesn't make noise, and it can be perfectly integrated in your site. So basically on the, I'm going to browse roughly, briefly the different demonstration sites. So in Ireland and in Ecuador, so we have installed only the Lumbrifilter, and so to treat the wastewater. So on our demonstration site in Italy, we have installed so the Lumbrifilter and the UV lamp to make sure that we can respect the discharge limit, which are really constrained. In terms of, especially in terms of bacteria and E. coli, especially because it's absolutely in front of the sea, so a lot of regulation to respect regarding that. And the system has been directly installed in the house, a 4-people house, which was really a challenge because the house were already under construction when we decided to install the system, but our overall system fit perfectly in the basement of this. We also have installed so the Lumbrifilter and the Daphniafilter, so on the NOBATEK headquarters. So this is our building, so located in France. So and on the right part, you can see the in the first Lumbrifilter, and you also have the Daphniafilter. This is also another challenge because we have a lot of variation in terms of occupation of the building, according if you are organizing conferences, if you're receiving public or not, if you have holidays. And of course, in the system, we mostly have people only 5 days out of 7 during the week, meaning that we have a lot of fluctuation. And this was really interesting to test the system in such conditions. Then we have also tested the Lumbrifilter and the Daphniafilter in 2 other different sites. So on the left part, it was on the Romanian part, where the system is directly plugged to an hotel, which is now turned into an offices. The challenge of this site is that we have a temperature fluctuation, let's say about from 25 plus 25 to minus 25 during winter. So it was a really great challenge to make sure that we can have a system which can work in such conditions. We also have a kind of, but not so extreme condition in Scotland. So on the right part where we have decided to isolate our system. So this is not the usual yellow tank we have, but this is the system protected to our demonstration site in Little Mill in Scotland. So the Lumbrifilter and the Daphniafilter. We also have installed the Lumbrifilter, the Daphniafilter, and the UV system in our demonstration site in Turkey, in Sinop, where we are intended to be able to reuse water at the end of the system. And the wastewater went from several households. So it was 15 different households, and we treated wastewater coming from these buildings. Also, we have installed so the Lumbrifilter, the Daphniafilter, and the UV lamp on our demonstration site in Tanzania, so in Lalakwa, really close to Dar es Salaam. And so where we are able now to treat the wastewater up to a quality to be able to reuse this wastewater for irrigation of banana plants. It was absolutely a great need to make sure that we can reuse the water after the treatment on site. Then we have our Indian and Peruvian site where we have installed the full system. So you can see directly on the left the Indian site where we have put the system directly for treating small communities. So we're receiving all the water from the communities and we are treating water so up to reuse quality, and the same for Peru site. This is a site we have in Peru during the construction period. So in Peru, it's located in Arequipa, and in India, it's located in Bengaluru. So basically, that's it for my overall presentation of the project. So I'll leave you a few seconds if you want to collect contact of the closest site you are from where you are, and if you want to be in contact with them, they will be more than happy to present you some results, details, and to discuss about your interest of the INNOQUA system. And so, of course, from my side, I remain at your disposal for later on if you have any question, and if you want to keep in contact, keep in touch for any question, I will be happy to answer to you. And then I will let my colleagues to present the different results of the technology we have developing in the project. So thank you very much for your participation. Thank you very much for being there, and I hope that you will have a great time all together. Very much.
Fantastic. Many thanks, Jean-Baptiste. I've spotted some questions coming into the chat, and I propose to take those during the panel discussion. But while I have the mic, Chris, could you clarify on your question about removal above 100%? So that's a question for Jean-Baptiste. Could you clarify which parameter that was for, please? And then also, Andrew, could you just clarify whether you mean the groundwater directive or the water framework directive? So I'll definitely pick those questions up during the panel discussion after the presentation. So thank you. And if anyone else has additional questions, please just pop them in the chat box. I'm monitoring that, and I'll take those out and raise them with the panel at the end of the discussion. So thanks again very much, Jean-Baptiste. It gives me great pleasure now to hand over to our next presenter of the session, Eoghan from NUI Galway. And I think Eoghan may have the privilege of being the only panelist with his own Wikipedia page. You can find it after the event. So Eoghan, welcome.
Hi everyone, and I'm hoping you can see my screen right now.
Yes.
I just had a little problem unmuting there. Thanks very much, David, for the introduction, and thanks, Jean-Baptiste, also for introducing the project. So firstly, my name is Eoghan Clifford. I'm a senior lecturer in NUI Galway. It's a university on the west coast of Ireland, where we're having yet another what we call soft day here. Basically, it's raining the whole time. And I'm presenting the results today specific to the Lumbrifilter technology, which is the technology based on the use of earthworms. And obviously I've have to thank all the INNOQUA consortium, because I'm basically using the results that they have generated from their various sites. So just to reiterate, this is just a presentation of the results from this particular technology only, and some of my colleagues will present the results from other technologies which would have been bolted onto the Lumbrifilter in various sites. And it may answer some of the questions also that have come up. So just in the project itself, we did quite a lot of laboratory work at the beginning, just to, I suppose, stress test the system, the Lumbrifilter system, understand a little bit more about how it works, how the earthworms react to different hydraulic, organic loading rates, or household detergents, or various things like that. And we first moved from laboratory to two prototype sites. One was in Galway in Ireland, and the other one was at the University of Girona in Spain. And in those two larger prototype sites, again, we did a lot of testing and various research with the Lumbrifilter to try and understand a little bit more about how it worked before we started moving to the demonstration sites. And we implemented 10 uncontrolled demonstration sites worldwide, which represented a wide variety of applications. Jean-Baptiste went through the diverse influent characteristics that we had across various sites. So, for example, in Ireland, we were in one site treating agricultural wastewater, so a very strong type of wastewater. Scotland had, in comparison to that, a weaker type of wastewater in terms of organic load. And you can see there's quite a variation between the different sites in terms of suspended solids, ammonium, BOD, COD, etc. I should mention as well that in different sites, different parameters were mentioned or were measured, and I'm only going to present the main organic carbon parameters and nitrogen parameters. I'm just going to focus on those in this presentation, but there may have been a wider variety of parameters measured across different sites. Again, Jean-Baptiste mentioned that there was a wide variety of discharge limits, which we, I suppose, were working to. Depending on the particular scenario, depending on where the wastewater was being discharged to, or whether it was being reused or not. So in the case of reuse, of course, we were working to reuse standards. In the case of discharge, we were working to various discharge standards, which varied between different countries. In the case of discharge, most of the discharge would have been to surface water as well. Finally, the climatic conditions, again, just a brief reminder, they were quite diverse. So, for example, Romania and Turkey would have had possibly the coldest temperatures, maybe followed by Scotland and Ireland. Again, in India, Turkey, I suppose Peru, Romania, there would have been the warmest temperatures, and in Italy, Ireland, and not surprisingly, would have had generally the highest levels of rainfall, which in our case did impact one of our sites, and there'll be a bit more detail on that in this afternoon's session. And Peru would have had very low levels of rainfall. So just to give you an idea of the diversity of the different sites. So the main block of this presentation is just going to focus on the main results from each site. Now behind this, I should say that we have a much more detailed report which we're finalizing, which looks at the specific organic loading rates, hydraulic loading rates, energy costs of the system, etc., etc. But I'll just, I'm going to focus on, and I suppose highlight the main removal percentages across the different systems. And the initial slides will have given you an indication of the types of influent concentrations. So our agricultural site, sorry, I should say that one of the other things I'm going to try and do is maybe across various sites, we would have had different types of challenges. And I'll try and highlight maybe one or more challenges for each of the sites, just to give you an indication of the types of things we encountered outside of the normal, design and construction issues. So the first site I'm going to look at was in Ireland, a town called Crugell, which is east of where I am now, near enough to the west coast of Ireland. It was a dairy farm, and we were looking at treating dairy wash water with a specific view to reduce organic carbon concentrations and nitrogen concentrations before the wash water, which would be generally spread on land. The particular reason being because this farmer, like all farmers, will be covered by the nitrates directive in terms of the amount of nitrate that they can actually put onto their land. In this particular site, we would have had very high concentrations of suspended solids, BOD and COD entering the system. And I suppose there was two challenges with this system. There was the very high strength wastewater, and there was also the fact to see as to whether these high levels of suspended solids within influent of the system would result in clogging in the system, and could we control the dosing sufficiently to prevent clogging. At the beginning of this particular experiment, we did encounter clogging problems, but after we got, I suppose, more careful control and dosing for the remaining, I suppose, 9 months of the experiment, we didn't have any clogging issues and achieved quite high removal rates, removal efficiencies of COD and BOD. One of the, I suppose, the positive ones as well was the high levels of ammonium removal. Much of that was actually as a result of nitrification in the system, because we were able to measure the conversion to nitrate between the influent of effluent and effluent. But for a continuous loading over nearly, after we solved the initial problems, we didn't encounter any issues with clogging. And I think that's when we really began to match the organic loading rate with the capacity of the filter and the worms to break down the organic matter. The second site, which comprised only a Lumbrifilter, was in Ecuador and in Quito, and that was a domestic wastewater. And the big challenge here was in fact space, and because of that we had to reduce the height of the active layer, which is basically the layer where the worms live. And they're living in a layer which is a wood chip layer in most sites, albeit we tried other media in some sites. And this did have an effect on the effluent performance. I suppose it was something we were conscious of beforehand, because we had seen in our laboratory results that once you reduce the active layer below about 800 millimeters, that we did begin to see a disimprovement in performance at laboratory level. But we were challenged by space, and there was no alternative in terms of the design considerations, as you can probably see from the photos. And you can see the removal rates here for BOD were about 54%, COD about 60%, TSS about 64%, and ammonium about 27%. One of the very positive things about the system, as Jean-Baptiste alluded to, was this was outside an office residential building where people were coming in and out. And after some initial issues with this particular system throughout the main operational system, there were no issues with odor or anything like that, which, considering that people would have been literally able to walk straight past the system, was very positive. The next one I'm going to show you is in Italy, in Vasto, which is along the Adriatic coast. Lovely sunny weather over there for a lot of the year. And in that particular system, there was a Lumbrifilter and a UV system installed, and this was at a large domestic residence. I suppose some of the challenges we had at this site were just aligning with the construction project that the residence was being built at the time. It was also being built as almost a bed and breakfast as well. However, we did have to align our construction with the construction of the house itself, and also it turned out that once the house was occupied, it was lower than expected hydraulic loading to the system, albeit the organic loading was close to what we expected. The loading rate in this particular case averaged about 400 litres per day. It was domestic wastewater, and this particular site operated extremely efficiently over the duration of the experiment, which would have been well over a year. And you can see extremely high removal rates across all the main parameters which we had to measure at that particular site. The next site I'll talk about was in Angers in France, and this was treatment of office wastewater. So as Jean-Baptiste, this is the actual office where NOBATEK, who coordinate this project, work out of. And so we were basically taking the office wastewater from their office and treating it. The loading rate there was about 600 litres per day, so about 0.6 meters cubed per day. And this was one of the sites alongside one of the Irish sites where we did quite a bit of experimentation with the different types of preliminary and primary treatment that might be most effective with the Lumbrifilter. In most sites, we have implemented primary treatment via primary settlement, but both in Ireland and France, we looked at a variety of different mechanisms, from dosing on raw wastewater without any preliminary treatment to using various types of filters to something akin to septic tank systems. So at steady state operation of this particular system, again, over a long period of time, we had, again, high removal rates, BOD about 90%, COD 70%, high removals again of ammonia about 72%, and high removals of suspended solids. And again, this is just through the the earthworm system alone, the Lumbrifiltration system alone. The Romanian demonstration site was in Ilișești, I believe the pronunciation is, in Romania. And this was one we had an opportunity to visit as well. Some of the considerations around this site, well, in fact, initially this site was designed as accommodating a tourist residence. So there would have been intermittent loading. However, during the project itself, the site was changed into a business residence or a business office. And so therefore the expected use and the expected loading of the system changed quite significantly after we had installed it. The other challenge was to deal with the low winter temperatures. In this case, the system was located indoors for that particular reason. Again, the system operated in this case it was treating about 1.6 meters cubed per day of wastewater. And you can see some of the average removals highlighted here in yellow, about just under 80% for BOD, about 66% for ammonium, and again, 64% for suspended solids. The next site was in Turkey, in an area called Sinop, which is in northern Turkey. Again, you can see it along the coast. There was again some considerations with this particular site. This site was designed to take on board domestic wastewater from residences that were being constructed at the time when the project started. For various reasons, they weren't completed as early as expected, and the system suffered from lower than expected hydraulic loading, and we had to, I suppose, take measures to counteract that. That also resulted in lower than expected biological load, and there was also a single very extreme rainfall event after we commissioned the system initially, which caused a lot of damage to the system itself. That particular event would have damaged most wastewater treatment systems. It was a very large flooding event, but it just was unlucky for us. It happened just after we had commissioned the system. However, again, after we got this system up and running, there was good steady state performance. The percentage removals might be a bit misleading in that the influent concentrations, particularly of BOD and COD and suspended solids, were very low to start with. In general, they were less than about 20 or 13 milligrams per litre to start with. So again, the removal rates there are a bit misleading in that. Ammonium removal rates were high, and probably compared to the other treatment system, there was higher than expected phosphorus removal rates. All these systems as well, I should say, are in operation. In this particular system, we did for a period of time actually have to import wastewater as well to ensure that we met or kept as close as possible to the loading rates. The loading rates averaged about 1.3 meters cubed per day in this particular case. In Tanzania, our Lumbrifilter was joined onto the Daphniafilter and the UV system. Again, the results I'm presenting are just for the Lumbrifilter system. It was treating domestic wastewater with flows that varied quite significantly between about 1.4 to approximately 3.7 meters cubed per day. For a period of time, we had up to 9 meters cubed per day coming into the system unexpectedly, and we did have to take action against that because the system wasn't designed for that type of hydraulic loading rate. It was domestic wastewater, and we had some unique challenges in this particular area as well. There was issues with intermittent electricity supply, which can occur, of course, in many countries. And also we had some interesting challenges around, I suppose, local customs, maybe our policies in terms of dealing with complaints from the public. So initially, there were some complaints for the public to do with odor issues. And it was quite interesting how that was, how we had to go about solving that and how communication worked with the public in that particular scenario, and I suppose with local leaders. That site was run by Borda, one of our partners, an NGO based from Germany. And I think once those initial issues were resolved, the system actually performed very well over an extended period of time. I think one of the limitations in this system, and I suppose a lesson as well, was that again, our loading rates in this particular case were higher than we had expected, even when we did bring them somewhat under control. But once the system is in there, it's hard to stop wastewater coming into it, of course. In India, in Bengaluru, we also installed a Lumbrifilter, Daphniafilter and UV system. We also had trials for the BioSolar Purification system. The results I'm presenting again are just for the Lumbrifilter part of the system itself. Some of the considerations here were the high temperatures, erratic loading to the system, and intermittent electricity supply as well were issues. The loading rate averaged approximately a meter cubed, so 1,000 litres per day, but it was quite erratic, both in terms of organic loading and hydraulic loading. Average removals here were quite high across the study, particularly, I suppose, once we solved some of the initial issues over the electricity supplies and loading issues. And you can see removals of 81% suspended solids, just under 90% BOD, 80% COD, and 82% ammonia. In Peru, in Arequipa, we also installed a Lumbrifilter with Daphniafilter and UV system. And this was also one of the sites where the BioSolar Purification system was to be trialed. Again, these results are for the Lumbrifilter system only, and this was actually installed in a university campus building with an average flow rate of about 1.3 meters cubed per day. We were taking just a proportion of the wastewater generated by that particular building. One of the challenges that we had actually, particularly at the beginning of this system, of the operation of this system, was that the highest temperatures coincided with low season, so with basically campus closure or holidays. And it did cause issues for the earthworms themselves, simply because there was no water flowing through the system. Now, there are remediation measures, of course, that you can put in place, such as recirculation, etc. And the earthworms are, across all the sites, were very tolerant to temperature changes in general. The key thing was that the system was kept moist. So that was just an initial challenge, and just had to do, I guess, with timing issues, etc. Once the system was up and running, the removals again were quite good. The low removal of COD might indicate the nature of the wastewater there, with a relatively high inorganic fraction of soluble inorganic fraction of COD. But again, 78% removal of BOD, about 73% of suspended solids, 73% removal of ammonium. And again, these are over extended periods of time. 3 of the sites which I'm not going to talk about in this presentation. Some of these we will discuss in some of the sessions later in more detail, are La Carnourgue in France, which is actually, I suppose, a different type of system. And in this case, we've deployed the Lumbri technology, so the earthworm technology, to Lumbri composting. So it's composting wastes from an aquaculture facility. And we're also going to present later on the results from 2 sites, one in Little Mill in Scotland, where we have a system, where we have a system treating wastewater from a small village. And the other one is from Tuam in Ireland, which is near where I am now, where we have a system operating probably, I think, the longest of the systems. It's operating for 2 years, basically, treating municipal wastewater in those 2 sites. And there'll be more details on those in this afternoon's sessions. So my final slide is just to try and summarize some of the lessons from the Lumbrifilter technology and some of the issues, I suppose, we learned from this operation. I suppose the first thing is the good organic and solids loading rate design is key. It might seem obvious, but in this case, you're trying to match the organic and solids loading rate, not just to bacterial activations that might occur in the system, but also to the capacity of the earthworms themselves to particularly break down the organic matter and the organic solids. Most sites started with initial worm densities of about 5,000 worms per meters cubed. Mature worms were generally used, different worm species across different sites. We had some interesting issues with customs, actually, particularly with regard to getting equipment to South America. In general, the active layer of about 1,000 millimeters to 1 meter was found to work best. And once the active layer reduced below about 700 to 750 millimeters, we did see potential performance issues, particularly with regard to suspended solids and knock-on issues for COD and BOD. Each site implemented intermittent loading, where generally there was dosing approximately once per hour for a period of a few minutes. There can be some issues with that when you have sites with very low flows, because obviously distributing that flow over 24 hours can be quite tricky in terms of pump selection. The system would work very well in a situation where topography allows you to use gravity, I suppose, to feed the system. Primary settlement or some sort of primary treatment was used in all sites, albeit in France and Ireland, as I mentioned, we did research and look at various different preliminary and primary treatment mechanisms. We do have energy costs for most of the sites measured. I just don't have time in this presentation to go into those. In general, they are extremely low. The only cost is a single pump. So for example, in the Irish sites, it might be a 100 or 200 watt pump coming on for 3 or 4 minutes every hour. And that's the only cost of the system. In terms of maintenance, the key maintenance that would need to occur is occasional raking of the top surface. In fact, we found that as the organic and solids loading rates matched what the filter was capable of doing, then this was often not necessary in our case. And however, what would be necessary is occasional top up of the wood chip. So the wood chip does tend to settle over time, and approximately 100 millimeters needs to be added every 4 to 6 months, albeit in Ireland we have left our system go without any top up for about 12 months now at this stage. But the active layer now has dropped by about 250 millimeters, so it would need to be topped up. We did do a lot, some work looking at locally sourced material, so trying to use locally sourced material both for the active layer where the earthworms live, and also underneath that layer, the kind of drainage layer, which is at the very bottom of the filter itself. We generally found the system to be very robust and recovers quickly when flows have stopped, even for several weeks, providing the wood chips remain damp and don't freeze. They're the key issues. If you can keep the wood chips damp at all, then generally the Lumbrifilter we found was extremely robust, and we saw that across a lot of sites. And for example, in the Irish site, the temperature ranged from about -8, the air temperature from about -8 up to about 26 degrees was the absolute maximum we had. Generally about 19 or 20 degrees would be the maximum we would have. And the water temperature would generally have varied between about 6 degrees and maybe 11 or 12 degrees. And we noticed very little drop off in performance between winter and summer, some slight impact on ammonium removal, nitrification, but very, very small impact. I suppose when wastewater volumes are low periodically, a good mechanism can be, if you have the capacity there, although it adds some complexity, is to try and recirculate a small portion of the wastewater through the system just to keep them moist. And I'll just finish by saying it was interesting just to see the different challenges that were encountered in every country. So in many cases, countries where you might expect we would have had more challenges, we didn't have challenges. In Ireland, we had particular challenges, for example, due to stormwater, which impacted our system quite a lot and meant that our wastewater often became extremely dilute, and then some occasions was extremely strong. And so that was quite a hard challenge on occasion to overcome, because we tend to have combined sewers for larger urban areas here. But definitely it was very interesting to see the different challenges that occurred across every country. And I suppose a very good aspect of this project was to put the Lumbrifilter in place in different areas with all these various challenges, and just to see how both the team reacted and how the technology itself reacted. So thanks very much for your attention. There will be a session later on with more specific detail on 2 of the sites, which is occurring after lunch.
Fantastic. Many thanks for that, Eoghan. Before you disappear, I am very conscious of time, but there are some kind of, I'll call them high-level questions, which I'll come back to during the panel discussion, specifically on things like system costs, overall system compliance with regulatory requirements, those kind of things. But a few specifics just on the Lumbrifilter. And the first one, is there any activation of the biomass? And I guess kind of initial conditioning or any other? Nothing.
No, we didn't. In the lab, we did a little bit, but on site, we, being honest, we filled up the Lumbrifilter with wood chips, we put the worms on top, and we started dosing them. Yeah. That was it. Yeah, no, very simple.
Yeah, thanks.
It took about maybe 2 weeks in the Irish conditions to reach steady state conditions.
Perfect, thank you. There's a question on how would you explain the high ammonia removal efficiency at the island demo site? Was that nitrification or nitrogen incorporation into the biomass during BOD removal?
Both, and also physical filtration likely as well. So what surprised us maybe in the Irish demo site, and it's extremely surprising to be honest, was that we expected to have nitrogen incorporation and also physical filtration, removal of nitrogen through simply removal of suspended solids. What we didn't expect to have was effluent nitrogen values of 40 or nitrate values of 40 or 50 milligrams per liter. The influent nitrate values were close to 0. So there was substantial nitrification occurring. I suppose it showed maybe a couple of things, that perhaps down near the bottom of the filter, there were areas where autotrophic microorganisms were able to thrive. There was oxygen present. The organic carbon is a bit of a conundrum, but they're the results we consistently got over a long period of time.
Perfect. Thank you. The final question, do the physical characteristics of the wood chip, their size and shape, impact on performance?
No, not really. What I would say is we have done work before on what type of wood you should use, and I suppose a key thing is to avoid wood types that are likely to disintegrate obviously quite quickly. Now, wood in general doesn't, but there are certain woods that would disintegrate quite quickly. That is the biggest thing. We generally used wood chips. They were probably sized between maybe, I'm talking length of maybe 5 centimeters up to maybe 20, 25, but we didn't really put any great effort into trying to size them. We literally got them off a local sawmill or wood mill, and whatever they had, we just took them basically.
Grand. Many thanks for that, Eoghan. So thanks very much indeed again for that presentation and answering the questions. I'm going to move very quickly on now to our next presenter. So it gives me great pleasure to welcome Victoria Salvado, who's a professor of analytical chemistry at the University of Girona. So Victoria, please, if you'd like to share your screen.
Okay.
Thank you.
Good morning, everybody. I hope that you can see my screen. Many thanks for your presentation, David, and also for the organization of this virtual congress. As I'm going to explain in this presentation the story how Daphniafilter, a tertiary treatment and nature base, was developed. As you know, tertiary treatments are needed in some cases to meet legislative requirements for effluent discharge or to improve the treated water quality to be reused. Physical chemical tertiary treatments attach some of that you can see in the slide: lamellar clarifier, membrane filtration, disinfection, and advanced oxidation treatments implies energy consumption and the use of chemicals that can result in environmental problems. Alternatives such as constructed wetlands and polishing ponds are good, but demand large areas of land and present difficulties in meeting the discharge criteria all year round. Especially in the case that we have the objective of reuse the water, the application of tertiary treatments becomes essential to meet the quality criteria established by the Spanish or European legislation in order to reuse this water for urban use, water recharge, or even for environmental or agricultural applications. In this natural ecosystems, a consortium of bacteria, fungi, algae, and other biological organisms perform the water depuration. Water fleas are filter feeder organisms that are able to remove small particles, so as a filtration system, and also they can remove pathogens and reduce the bacterial load. They can be exploited for wastewater treatment purposes if they can survive in wastewater or maintain their filtration capacities, and also if nutrients can be also removed. So we first tested in a laboratory test this capacity of Daphnia to survive in wastewater. As a result of this test, we know that they cannot be put directly in contact with primary, they cannot be used as primary treatment, but they are compatible in secondary wastewater. So we designed the concept of Daphniafilter reactor that consisted in the combination of the filtration capacity of Daphnia together with the bacterial algal biofilms that can help to remove nutrients. Of course, as a living organism, and also to improve the removal processes, there is need some sunlight. To test this combination at laboratory scale with these experiments and using synthetic wastewater. The results obtained, can you see in the slide, are nice because in the case of removal of organic matter, we obtained 90% of removal. In the case of nitrogen species, 55%, but the problem is in the case of phosphorus that only it was possible to remove phosphorus at 10% of efficiency, and in the case of the high gas resistance time. From the knowledge learned in these experiments, we have designed and installed a reactor in a pilot site in Quart, Spain. This reactor have the capacity to treat 1,500 liters per day that we calculated that corresponds at 10 population equivalents. You can see in these slides the inlet and the outlet of the reactor, the lamella separator that can help to remove the highest solid particles, and the covers that are designed in order that the light can enter into the water column. This reactor was fed with secondary wastewater from the wastewater treatment plant and has been operated for 1 year. Some people in the audience, I saw that was asking for the time that we have operated, but in this case, the combination of Daphniafilter with secondary wastewater from the wastewater treatment plant was 1 year of operation. And the objective of this test was to evaluate the suitability of the effluent water to be used, to be reused. So we pay attention to the parameters, the quality parameters for this aim there are in the Spanish legislation. In the case of total suspended solids and turbidity, we obtained higher removals, and at the different flow tested, because we have operated the system at the nominal load, that is 1,500 liters a day, half of the nominal load, and to stress the system by operating it at the double of the nominal load. As you can see in these slides, for 10 months, regarding this parameter, the values are lower than those cited in the Spanish legislation. In the case of the nutrient and pathogen removals, we can see for ammonium and total nitrogen that also the removals are good, but it depends on the period of the year. And in the case of pathogens, we obtained height removals. In the case of we have monitored the total coliforms, E. coli, and Enterococcus, and the best results were obtained when the system was operated at half of the nominal load. In order to evaluate the suitability of this effluent to be reused, we defined the quality parameters, taking into account the parameters of the Spanish legislation. And here in this table, you can see that in the case of the quality of this quality ratio was less than 1, this is the periods marked as green, color green, and in these cases, the wastewater producer for the Daphniafilter can be reused for several applications. In the other cases, the system fell in some cases as the E. coli content was too high, and in some cases, especially in the case of environmental problems, of environmental applications, the problem was related to the nitrate content. After evaluating the performance of the Daphniafilter connected to the secondary wastewater, we have connected it with the Lumbrifilter. In this case, in the Girona pilot site, we connected the 10 PE unit of Daphniafilter to 2 5 PE units of Lumbrifilter. Here you can see the connecting tank, and this is a view of the upper part of the Daphniafilter. In this case, we have treated raw influent wastewater. The tests were performed for 2 periods of 6 months because we have stopped during the lockdown due to the coronavirus crisis. The results obtained in terms of nutrients, suspended solids, and BDE are presented in this slide at the different flow tested. As you can, for each unit, this is the result for Lumbrifilter, this Daphniafilter, and this is for the whole integrated system at the different flow rates. This is the number of points that are included in this information, and the parameters that are depicted are the COD, total suspended solids, ammonia, BOD, and turbidity. As you can observe in this representation, Daphniafilter have, in all the cases, an important contribution to improve all these parameters. And the most important contribution is related to turbidity. In the case of ammonia removal, you cannot see any value in this graph. That is the lowest flow tested. As in this case, the Lumbrifilter practically removed all the ammonia, so we don't have ammonia to feed the Daphniafilter. The one important thing to be remarked is that compared with the previous tests that were performed with the Daphniafilter connected to the secondary wastewater treatment of the wastewater treatment plant, in the case of Lumbrifilter, although the variability of the inflow wastewater was high, after being treated by the Lumbrifilter, the effluent from the Lumbrifilter have a very constant characteristics. And this is very good in order to test the Daphniafilter. In the next slide, we can see for the same configuration, the removal of pathogens, the three that we are monitoring. And you can see also that when we are performing the test at the highest flows, the contribution in removing these pathogens from the Lumbrifilter are lower, at the contribution of the Daphniafilter in the total removal increases. As in the previous experiments, the best removal rates for the pathogens are obtained at the lowest at the lowest flow. That means at the higher resident times. As has commented before, the Daphniafilter and Daphnias in particular, they can remove small particles, so are very good in removing suspended particles. You can see here a picture with the Influent wastewater, the water coming from the Lumbrifilter, the Daphniafilter. As we can see in this graph, you can see in this is the small particles, and the removal by the Daphniafilter is very important. In this other slide, we can observe that this removal can achieve 99.9% of removal in the case that we can operate the system at the lowest flow. Finally, one of the challenge of the Daphniafilter is to have a stable population of Daphnias inside the reactor. And this was the reason why some of the results from the different demo sites are not presented here. And only I'm going to compare the results obtained in our pilot plant in Girona with those obtained in India. It's important to remark that the wastewater characteristics of both demo sites are really different, as well as where the water temperature and the flows used in the experiments. So there are not can be directly compared. In the case of the India demo site, there were extreme conditions, especially for water temperature. The optimum conditions for to have the highest filtration capacity by Daphnias is 20 degrees. And in the case of the India demo site, water have more than 30 degrees most of the days. You can see the results in this table, and taking into account the difference, there are also difference in the values of the efficiency in removing total suspended solids, organic matter, and only in the case of the ammonium removal, the results are similar. So we can conclude that in the case of Daphniafilter shows a high efficiency in inhibiting pathogens, achieving an elimination rate of around 90%. The same in the case of small particles, and this contribution can be very important in the case of using a UV lamp, because if you reduce the turbidity of the water, the efficiency of the UV lamp will be improved too. So Daphniafilter acts as a pollution stage that is important in the case that we need to meet some restricted limits for effluent discharge and also for the water reuse, and also contributes to eliminate nutrients. The integrated system composed of Lumbrifilter and Daphniafilter allow the water reuse, as has been demonstrated in the case of the pilot site of Girona. And about the maintenance, it's very easy in the case of the Daphniafilter, but for example, in our demo pilot site, we need to clean the sludge. There are some sludge that are deposited at the bottom or in the lamellar plugs of the reactor after 12 months of operation. And in the case of the shutdown, no performance difference was found in the periods before and after this shutdown. In general, energy consumption is only related to the use of a pump that you can use a small garden pump to introduce the water inside the reactor. You don't need chemicals. About the Daphnia population, we have inoculated with 0.5 Daphnia per liter the reactor, and if the conditions are good, after 2 weeks you can have the optimum population of around 400-500 Daphnias per liter, and this population is maintenance because the Daphnia have a life cycle that allows this maintenance. We don't need inoculation, re-inoculation, only in case that there are some disaster. For example, you can some high content of organic matter can go inside the reactor, and for more than 2 weeks you will need to inoculate, because the Daphnia have a mechanism of resistance that consists on putting resistant eggs that can exploit when the conditions are favorable. So in conclusion, the low energy consumption, minimal maintenance, absence of chemical, and the small sludge production make the Daphniafilter both ecologically and economically sustainable. I would like to acknowledge all the partners of the INNOQUA project for their contribution. We have a good time working together, and especially I would like to thank to the team of my university, of University of Girona, that have contributed a lot to obtain these results, and thank you for your attention.
Perfect. Many thanks, Victoria. I am being told off in the chat for my terrible timekeeping, and I'm conscious really that we need to start the next session on time. So just a couple of points. The presentations will be made available after today. So anyone online is welcome to contact the presenters directly if they have detailed questions. Some of the questions are also being answered in the chat as we go along. So I'm not trying to duck difficult questions. The presenters will be very happy to answer those directly if you'd like to follow up with them. I will pick up just probably 1 or 2 questions before we break after the next presentation. But Victoria, I just have one question for you, if I might, and it's what do we know about the different treatment aspects of the lemna on the top of the Daphniafilter, the biofilm itself, and then the Daphnia? So has it been possible to break down the treatment impacts of those different elements, or is that subject to future research?
We still need to make some improvements, especially to eliminate nitrates. So, but this is not related to the design of the internal part of the reactor. The most important thing is to have enough surface in order to allow the biofuel growth, and also to facilitate is in case that big particles that cannot be fit for the Daphnia can settle. This is the mission of the lamellar separator that we have inside. So both functions. And also the place where are located, we made some simulations because we need to to have the Daphnia happy. So they need some space to swim. We have measured the swimming velocity of Daphnia in order to make this. So this, it seems it works okay. The only thing is this part, they have that circle that is to distribute homogeneously the water. Probably this can be, is not necessary. We need to make more experiments on this.
Okay, perfect, thank you. So I would summarize by, if I might, by saying, like other nature-based systems, the effectiveness of the Daphniafilter is a result of various organisms working collaboratively or interactively. Yeah, yeah. Perfect. Thank you very much indeed, Victoria, for that presentation. I will now hand over to our final presentation session. So it gives me great pleasure to give the floor to Costel. Costel, if you'd like to share your screen, please. Welcome.
Thank you, David. And good evening to everyone. I'll try to be as short as possible. So I'm Costel Bumbach. I'm a senior research scientist within the Environmental Technologies and Technology Transfer Department of Eoghan in Romania, and demonstration manager within the INNOQUA project. Eoghan in Romania is a national research and development organization dedicated providing services to in the field of pollution control, environmental monitoring, impact assessment, ecotoxicity studies, air, water, wastewater, and soil treatment, and waste management. My presentation today will focus on the microalgae-based polishing step module, also known and referred to as BioSolar Purification module, proposed by the INNOQUA team as an alternative for advanced nutrient removal. Within the INNOQUA system, the microalgae-based treatment is the option for polishing the Lumbrifilter Effluent in sunny climate conditions as alternative to the Daphniafiltration and before any final disinfection treatment for wastewater discharge or reuse. The BioSolar purification process is based on the induced symbiotic relationship and metabolism between bacteria, as bacteria are consuming influent organic matter and oxygen produced through photosynthesis by algae, while the microalgae consume the CO2 produced by the bacteria and produces the oxygen in an engineered system with the purpose of nutrient uptake. Having in mind the decentralized market targeted within the project, we knew from the beginning that we had to adopt the technological approach of BioSolar purification, which was initially developed and validated. Technology which incorporated quite expensive elements such as vacuum airlift for recirculation, mixing, and or light wells focusing the light streams towards the BSP reactor. Thus, thinking of lowering the costs both in terms of investment and operation. Within the project, the alternative of microalgae-based polishing step has been proposed initially by Hello Food Technologies, and afterwards, since they went out of the consortium, the technology has been developed further and validated by Eoghan and NOBATEK with the help of other partners on field at lab and pilot scale. The system has been transformed to an open system with natural cascading on thin layer photobioreactors, where the influent is being fed on the platform during daytime, and the recirculation pump ensures the required contact of wastewater to sunlight. The newly developed concept has the Environmental Technology Department of Eoghan. The experimental rig consisted on 3 reactors in duplicate with the purpose of assessing the influence of platform design, if any. We tried single platform design, double cascade reactor design, influence of water height on the platform, 1 and 5 centimeters in height. Establish a stable operation and assess potential treatment performances of this treatment step prior to pilot scale development. And we also tried to assess the impact of recirculation rate and evaluate the amount of ESS generated in the effluent as a result of biomass-specific growth due to nutrient uptake. All experiments were performed at lab scale using synthetic wastewater, trying to replicate the Lumbrifilter effluent. The reactors had a capacity of 10 liters each and were all fitted with individual feeding pumps and recirculation pumps, while the light was ensured artificially using a LED photosynthetic light source. The source of nitrogen was initially for startup boost ammonium nitrogen, as this has been observed in previous experiments as being the preferred source of nitrogen for microalgae, and was switched afterwards to nitrate nitrogen, along with the increase of light intensity to start the simulation of polishing the Lumbrifilter effluent. As operating parameters, we have chosen a photo periodicity of 12 hours light and 12 hours darkness, and a hydraulic loading rate of 250 liters per square meter per day. All experiments being performed at room temperature, meaning 22 plus minus 5 degrees Celsius. Since the very startup, the system succeeded in removing approximately 60% of COD, 20 to 40% of nitrogen ammonium, the higher rate corresponding to the very thin layer cascade photobioreactor, and approximately 20% for phosphorus removal. Once with the increase of light intensity during the second stage of testing, removal efficiencies increased to an average of 70% for COD removal, 80% for nitrogen removal, and 60% for phosphorus removal with the limited influence of platform design. The specific removal performances of lab scale systems were approximately 12 to 13 grams per square meter of nitrogen per day, 1.3 grams per square meter a day of phosphorus, and approximately 30 grams of COD removed per square meter a day. For the tested conditions, the platform design had almost no impact on organic load removal performances. Of the effluent being mainly associated to the biomass washout as organic DSS. While for all filtered samples, the COD was below 20 milligrams per liter. You may see in the first graph that during startup, during the first weeks, the effluent COD in homogeneous sample were higher, as this corresponds to the suspended growth period, the effluent being discharged with suspended biomass. However, after these 2 weeks, once the microalgae bacteria biofilm has grown on the platforms, the TSS in the effluent has been consistently lower. And even though the initial design of the BSP proposed by Heliopour with the incorporating expensive equipment such as the vacuum early for recirculation were especially designed not to harm the microalgae and ensure suspended growth, it seems that the cascading platforms approach correlated with the recirculation from the tank to platforms ensures proper condition for biomass to grow as biofilm, and thus offering the advantage of assessing the effluent. On the other hand, as a little drawback, just to keep the balance even, as there is no perfect technology, growth as biofilm means at the same time that biomass accumulation on platforms and correspondingly the need for regular maintenance through harvesting of the biomass or of the detached biofilm. So for the lab scale experiments, we observed that the excess biofilm detached and accumulated on the platform need to be removed to avoid biomass decay and nutrient resource. Phosphorus removal efficiency was the most affected by biothermal accumulation and decay, leading to uncontrolled accumulation and liberation of phosphorus, leading to performances. Once the maintenance of the system by harvesting of the biomass was in place, performances were improved. The microalgae-based polishing module is being tested in Spain by University of Girona, in India by Borda, and in Peru by the Catholic University of Santa Maria. The systems are being tested after the Lumbrifilter and in parallel to the line to the alternative with Daphniafiltration and UV system. The INNOQUA system in Spain is being fed with municipal wastewater, the system being installed as wastewater treatment plant. The municipal wastewater fed to the Lumbrifilter has approximately 500 micrograms per liter COD and 20 to 60 milligrams per liter of ammonium nitrogen. The removal rates after Lumbrifiltration alone are, as Eoghan previously explained, about 80% reduction for all parameters mentioned earlier. And by adding polishing steps, either Daphniafiltration, either BioSolar Purification, the treatment level reached performances close to 90% for COD and BOD, or above 90% TSS and nitrogen ammonia. To sum up, the BioSolar Purification presented significant average removal of for TSS of approximately 62%, for nitrogen ammonium 57%, and for turbidity 59%, on top of the Lumbrifilter performances. While phosphorus removal was assessed only as phosphate removal for this site, and the performances were about 35%. The system installed in India is evaluating also comparatively the performances of the Lumbrifilter in combination with Daphniafiltration or BioSolar Purification as polishing steps. The Indian system is treating the wastewater generated from 9 households from a rural low-income community next to Bangalore. The influent is of high strength, typical to low flush community, as water scarcity is a major issue in India. The influent fed to the about 2,200 milligrams per liter of TSS, 1.1 grams per liter of BOD, approximately 100 milligrams per liter of nitrogen ammonium, and the temperature ranging from 20 to 38 degrees Celsius. By the Lumbrifilter, and the flow from the Lumbrifilter is divided into 2 streams. One goes directly towards the Daphniafilter, following the UV system, and the other goes close to the BioSolar Purification system. The BSP system installed in India consists of 2 platforms, 2 square meter each, made of polypropylene, cascading from one to another, corresponding to a total surface area of 4 square meter. And the system has been designed to treat 1 cubic meter of Lumbrifilter effluent per day, and has been built locally using local materials and trying to keep the cost to a very minimum. The inoculum used was harvested actually from the inside walls of the Lumbrifilter, where a microalgae biofilm has been formed on the sides exposed to sunlight. And we also added some, something like 20 liters of pond water. So even in this harsh testing condition, high TSS and nutrient loads, the system performed really well, achieving removal performances above 80% for most parameters tested only through Lumbrifiltration alone, while adding supplementary modules as polishing steps improves the quality of the effluent, reaching at most times removal performances above. As you can see here, the Daphniafiltration plus UV has slightly higher removal performance, but this is due that along the Daphnias in the Daphniafilter, there were an abundance of water plants such as water cabbage, which contributed a lot to nutrient uptake. In Peru, the INNOQUA system treats the wastewater from the campus of the Catholic University of Santa Maria in Arequipa, Peru. The wastewater sources include toilets, a kitchen, laboratories, and other activities in campus buildings. A stream of all that wastewater generated on site is diverted and treated into the INNOQUA system. And as for the Indian demo site, all materials to build the BSP module were sourced locally, and the system was installed on site. For this case, the inoculum used were cultured chlorella and Genedesmus cultures provided by the biotechnology lab at the university. In general, the Lumbrifilter plus the BioSolar Purification provided similar removal rates as the Lumbrifiltration plus Daphniafiltration configuration, with relative better performances for BOD removal and ammonium. In any of the configuration, the system performs with removal efficiencies of approximately 80% for TSS, BOD, and ammonium. And researches are still ongoing in the development of the BSP to increase the nutrient uptake as microalgae biomass and to establish the maintenance schedule correlated with the influent quality of residual biofilm harvesting. As a general conclusion, we may say that the BSP module, as developed within the INNOQUA system, is suitable as a polishing step. However, it might be more suitable for larger scale installation, as it might require regular maintenance, which is unlikely to bring social acceptance to decentralized individual household use. However, the module brings added value in terms of wastewater treatment and helps in bringing the nutrients concentrations of nutrients in discharge effluents to lower limits, aiming towards discharge limits and environmental protection. If you have any questions, I would be more than happy to answer them now or later on in the chat box. Thank you for your attention.
Perfect. Thank you very much indeed, Costel. And apologies to everybody for my terrible timekeeping, which means we've just taken up all the break time. As before, just to remind everyone, a lot of the answers to these questions are in the project deliverables, which will be on the project website. So I'm not trying to duck difficult questions. Some of the elements of the project have been challenging, and you will find the demo site feedback and kind of some of those challenges elaborated in the project reports. But Costel, before I let you go, I just wanted to ask a couple of brief questions, if I might. Firstly, is inoculation with microalgae compulsory in these kind of systems? And then the second question, what do you think the next generation BSP unit might look like, kind of physically? How might it operate and how might it look?
So, thank you. First, inoculation, it's not compulsory, but it speeds up the process of startup. Let the system self-inoculate with indigenous species. It might take up to 2 months. And if you use inoculation of locally harvested biofilms or pond water, or you may end up with the startup of only 2 weeks until you get a stable biofilm on the platforms. And regarding the next generation of microalgae-based wastewater treatment processes, it's definitely going to be biofilm or other form of aggregated biomass, such as granular microalgae and bacteria. As the main drawback of the technology in scaling up is the residual biomass harvesting from the final effluent. If you have suspended growth, you have very high costs of harvest and leaves the process uneconomically feasible. While if you use biofilm, you may use the techniques usually used in biofilm-based wastewater treatment technologies to remove the detached biomass and go along without any problem like that.
Great. Thank you very much indeed for those answers, Costel, and apologies we haven't got more time for questions. I know that you're available on the chat if anyone would like to ask you questions.
Yes, I will be answering on chat. Yes.
Yeah, perfect. Thank you. So at this point, before we break, I'd just like to invite Jean-Baptiste back onto the screen just to answer one question for all of us. And the question is, or what's going to happen next with the INNOQUA technologies, with the INNOQUA projects now that we're coming to the end? So if you'd like to share any comments on that, Jean-Baptiste, that'd be great.
Thank you, David. Thank you, everyone, for your presentation. So thank you, David, for this question, which is really important indeed. So the project gonna to over at the end of the month, but this doesn't mean that we're gonna to stop our system. So most of our system gonna to continue to run and to treat wastewater on site, because of course, and it was reflected in some of your question, we need to continue to monitor our system on a longer period, just to make sure that we can have appropriate data regarding especially maintenance of our system, even if our system are installed now for years and years, and some of the technology are already known, even if we are perform update on an upgrade of our system. So definitely we're going to continue with us having our system running, continue monitoring, and also we're going to continue to invite you on our site. So if you want to visit the site which is close to where you are, so feel free to contact the different demonstration manager or me directly, and we'll be happy to put you in contact. So I think it's really important to continue disseminating the data we have and to visit on our site.
Fantastic. Thank you for that, Jean-Baptiste. I will make sure that a list of the demo site managers and contact details is circulated to all delegates after the event. So it's a very clear list rather than hidden in a large report. So everybody will have access to that information. And please, I urge you to contact the demo site managers. They are distributed in 10 or 11 countries. So there may be one relatively close to you. Yeah, there may be one relatively close to you. So fantastic. On that note, I apologize again for cutting the discussion short and for my terrible timekeeping as the chair for this session. I will take a 7-minute break. If we can restart the conference at 5 minutes to the hour, that'd be fantastic. And I'll hand over to the next session facilitator, Eoghan, for that session. So thanks very much indeed. I look forward to see you all again in 7 minutes time.
Thank you, Dave.
Hi everyone. So to keep ourselves on time, I'm going to kick off this second session straight away. So as you've heard from me before, obviously my name is Eoghan Clifford and I'm in NUI Galway University in Ireland, and I'm just going to host this particular session, which I'm very much looking forward to, given the various speakers and the talks that we have. So I'll hand straight over to our first speaker. Our first speaker is Fabio Massi from Fabio is the technical director and R&D manager of the Italian engineering company Iridra, and this company specializes in nature-based solutions and green infrastructure. And Fabio is going to talk about innovative nature-based solutions for future smart and circular cities. So I'll hand over to you now, Fabio. Thank you.
Good morning, everyone. So as first thing, I want to make my compliments for the very nice results obtained during this INNOQUA project. And I appreciated a lot of the presentations of this morning. The developed technologies are really interesting. And I am currently chairing a task group in the International Water Association, which is just dealing with nature-based solutions for water and sanitation. So these new options, which are even not so new in some cases, like the vermiculture is already a quite old technology, let's say more than 10 years, are surely representing part of the tools that we have and that we can select in each particular case. So it's like 25 years that I'm working in the nature-based solution sector, and we developed quite a nice paper like 4 years ago, where we have listed all the possible integrations of functional, let's say multifunctional green infrastructures in urban settlements. So what we want to avoid is obviously the linear economy approach that is now strictly linked to the water management in urban settlements, as also the fluxes of whatever we put in the water, dirtying it. So our excreta, for instance, which are chemically speaking, instead values which have a real good value on the market. How to do that? Just decentralizing as much as possible, avoiding the very expensive gray infrastructures that have to be maintained with very high cost, and trying to build up very short loops where to produce biomasses, where to link the water cycle to other two cycles, which are the energy and the food one. So just creating this nexus between water, energy, and food, we can really try to build up a more sustainable society. Well, for doing this, one of the main issues we have dealt with in the last 3 decades has been the land occupation of these nature-based reactors. Normally, nature needs time. Humans need a faster time for providing us food at the good rate that we need, and so on. And just for obtaining this, the nature-based reactors would need a very high footprint. I mean, occupancy of surface land in the urban settlement. And that's obviously a big issue a lot of times. Therefore, I'm just going to present you what are, in our experience, the most promising nature-based solutions enhanced in order to reduce the footprint, or just to reduce the land occupation on the normal surface, let's say. And so we shifted, as you can see here in this picture, to occupy the walls, occupy the roofs, and so on. So the first one is obviously to add some aeration in passive wetlands. This kind of technology is already very well known at the moment. We have equations and models that we are able to use for sizing the systems. And what we can say at the end is that we can aerate both the horizontal and the vertical wetlands, and we can reduce the area in comparison to a passive solution to about 1/3. This is meaning, for instance, in a Mediterranean climate, we can reach already surface water limits for discharging with about 3 square meters per person, both with the horizontal and a bit less with the vertical flow. And we can go down to about 1 square meter per person if we make use of the aeration in these systems. All this is very well described in a new book that you can freely download from the IWA website. That's called Treatment Wetlands. One of the following presenters is one of the main authors and editors of the book, Gabriele Dotro. And so everything is very well described inside here. Just going fast because I have very few time. We realized it recently in one project we are running, an AWEMET, which is focused on the Maghreb area, Tunisia, Lebanon, Jordan, and so on. And so one possible usage is a compact modular system, which is still making use of the wetland technologies. So that's an aerated wetland just built inside a container, and that can be transported. In our case, we have adopted it for a temporary urban settlement, which is a refugee camp. Just think to 100 of possible application of this kind of modular systems in temporary events, like, I don't know, 3 days of rock concert or something like that. So that's just a sketch of the section. So aerated wetlands can be compacted and transported around. And one even more interesting variation is going to be developed, I mean, is under patenting at the moment. And it's called the French-American system because it's joining the French reed beds, which is a particular kind of constructed wetlands where 2 following reactors are placed in series, and in the first one, raw wastewater is going in without any kind of primary pretreatment more than a simple grid for removing the plastic bottles or the big floating matter. And so all the primary sludge is collected in this first bed, which is then building up a top organic layer, and it gets aeration on the bottom. So we don't have primary sludge, and we have a reduction of the area a bit less than 1 square meters per person. That's obviously referring to continental or Mediterranean climate. It is going even down to 0.5 or even 0.3, which makes the system quite comparable at the end to the classical approaches like the activated sludge systems, which are occupying at least from 0.1 to 0.3 square meters per person in total. If we go in hotter climates like tropical ones. Then, as I was mentioning before, are focusing a lot on recycling water. Why? Because it's 70% of the domestic wastewater. So if you learn how to close loop it at the building level, then that's the best way to send less water to the maybe centralized wastewater treatment plant located at the end of the gray infrastructure. And obviously you can reduce of a big amount, let's say in some cases even the 50% your water bill immediately the day after the installation of your treatment system. The best solution is still to build nature-based solutions on the ground if possible. So if you have space, that's obviously the cheapest solution that every time you have. But if you don't have enough space, let's say we are working a lot in Indian settlements, for instance, and it's really hard to find spots where to realize in the ground. And therefore, we can shift going on the walls. And that's just an example of an installation in front of the houses for recycling the grey water on the ground. And if we go on the walls, we have some parallel side benefits, let's say, like, for instance, we have some interaction with air pollution, but mainly we are creating a sort of insulation layer. And we will see later on that we can even increase this effect of insulation. Obviously, we are including some green, so we are increasing the biodiversity, we are reducing the noise, the longevity of the building will be longer, and obviously all these have aesthetic effects. Can we also do the wastewater treatment in all this? Yeah, we can. And sorry. So, yeah, and we have demonstrated by a pilot installed in Pune in India that with about 1 square meter of green wall per person, which is equivalent in India about 6 square meters in total for an Indian family, and with a cost ranging around 600 USD, that's an Indian cost, which is much higher if we buy the plastic pots in Europe, for instance. Well, we can already obtain, in this case, the wastewater was really diluted, but we already obtained it with about the 50% of removal of the organics and the ammonia, kind of effluent, which is respecting the regulations, the big part of the regulations worldwide for the reuse, let's say. We have gone further, making some other experiments for other 2 years with the University of Turin, where we have tested some filling material. Obviously, installing green walls have the issue of being obliged to make use of very light material, especially if you are retrofitting an existing building without adding too much weight to the walls and so on. Therefore, we are focusing on materials that are every time offering a very good surface for the biofilm growth, but even being light. And so the perlite is, or the LICA, are normally the main one used, which is then mixed to some other more active materials, or some finer materials, because the main problem is to keep the water long enough inside the pots in order to have enough retention time for ensuring a good treatment. So we have tested polyacrylate, biochar, and activated carbon in order to see if their removals were better performing. And yeah, we have obtained very good, especially in terms of organic matter removals, very close to the 100%, very good nitrification. So still having a hydraulic loading rate up to 700 liters per square meter per day, which is much higher than what we are normally used to design for passive vertical flow wetlands. We obtained this kind of results, and that's quite a good finding. So I was saying before that the installation can be done like this, just screwing some metal guides to the wall, and then screwing the plastic or aluminum pots on top of them. But we can use stifferite, for instance, as insulation material in the middle, in order to increase the energy efficiency of the building. So if the walls are not enough, we can even go over the roofs. Also here, obviously, the problem is mainly static engineering. So we have to interact with the engineers that have designed the building and understand if putting 1 cubic meter of water on the top per square meter can be an issue or not for the building staticity. As a very last signalation of one promising technology, that's the one elaborated by one group of researchers in the University of Alcalá in Madrid, and one of the experts is just attending this presentation. I've seen Arantxa before, and this MET, microbial electronical technologies, is making use of electroactive bacteria. So it's like to create a flux of electrons inside the wetland that can drive some different enhance the performances, let's say, enhance the processes. And what is obtained with this kind of technology, which is making use of special filling material, in particular coke. And for the moment, the implementation issues are just related to the cost and the availability of the electroconductive material on the market, but that could be easily solved if the technology will develop in the future. And even in this case, like for the aerated wetlands, we can obtain a reduction in area of about 1/3 to 1/5. And yeah, also in this case, we have very few consumption of energy, but even there is no recovery of energy as we were thinking in a first moment, but still, for instance, you can create a flux of electrons which are going where an electron donor is needed. And so you can miss to have the electron donor present there if you are able to bring the electrons directly. And that can really enhance some kind of electron needing processes, like, for instance, the reduction of nitrates to nitrate. With this, I think I've given general view about what are the research frontiers at the moment and what are the market exploitations we are trying to do in order to implement these new kinds of nature-based solutions in settlements. I'm open, obviously, to every kind of question.
Thanks very much, Fabio. And actually, some of the images, I guess, that you have in your slides are, I guess, you know, something that we probably, hopefully, most of us would like to see our cities looking like in the future. So I think I've just time and go for a quick question or two. So I might just ask you maybe two questions. The first one is, are there clear cost benefits for all or most of these nature-based systems? And I suppose this is from David Tompkins, and his point is that in some certain countries, such as the UK, they may be resistant to that, and perhaps it's an economic issue. Or have you any comments on the cost-benefit analysis?
Well, normally it's the cost of the water in the specific country, I mean the water supply, which is determining what is the payback time for a kind of investment. So in Europe, for instance, where these systems are already very competitive on the local market, are the countries like Germany, where the cost of the water is over €3 per cubic meter, even going to €4 per cubic meter. In the countries where we have a political regulation of the water price, like in my country, for instance, in Italy, we are paying it less than €1 if we are consuming not so much per day. And at the maximum, we are going up to 1.5 or €2 per cubic meter. In this case, the payback time is becoming obviously the double in comparison to Germany. So what we can say is that still the payback time has a range in this investment. If you make ground installation, it can be quite fast. So let's say in 5 years, you can get back your money. And from the 5th year, then you will have a big saving on your water bill. That could be enough for convincing families to make the investment. So to pay the capex, the investment, the installation cost, just having then to afford a very, very low, the lowest, I would say, in comparison to all the other technological options, OPEX, which is the operation and management cost. So the main advantage of this nature-based solution is that their management is quite inexpensive. And so it's just a matter of finding a way to finance the realization. That could be done by the public subsidies, for instance. That could be another political decisions. Instead of keeping the water price low, they could instead finance interventions in order them to make a more sustainable reuse of the resource. That could be a big gain for everybody. And that could be a solution, but that's politically driven. The other one is to try to make them the less expensive as possible, so to focus our research in order to make them inexpensive, or the less expensive that is possible, still having good performances. So the other alternative is doing nothing and producing a loss in natural capital, which is something that our nephews will pay then. So it's just to understand how this cost-benefit analysis has to be done, let's say.
Yeah, that's actually very interesting. And I guess a lot of politics as well, of course, is short-term. And I should say in Ireland, the cost of water might be low in Italy, but in Ireland, if you're on a public system, which most people are, you pay nothing for water. Oh. Yeah. So, which obviously makes a cost benefit. Yes, that's a matter of great controversy here. But anyway, there are a couple of other questions, but I might leave them until the end, and I might move on to the next speaker, and we'll have time at the end to put some of the questions to the panel. So thank you very much, Fabio. And our next speaker is Dr. Sven Eoghan, and Sven is from the Swiss Federal Laboratories for Material Science and Research. And he is an experienced researcher of next generation urban infrastructure systems at that institution. Thank you very much, Sven.
Yes, hello everyone. It's my pleasure to present you a bit a different perspective. So I will, like in the next couple of minutes, present you mainly research I've done in my PhD. So it's not on the technical side, but it's more about the question like what would be like a good system. So how much centralized or how much decentralized treatment should we have? And you can read all the details in my publications and particularly my PhD thesis. And I will structure this talk in 4 bits. So first I will give a Swiss perspective, which hopefully represents to some degree also Europe. And then I will talk about the cost assessment of centralized and decentralized treatments, which is important to then understand sort of potential entry markets and market potentials for decentralized treatment systems. And finally, I will present you with some lessons learned. So this is the place I grew up. So in Switzerland, they even installed like a sewer pipe up to this mountain, which then like flows down for 2,500 meters. So Switzerland spent a lot of money like into the centralized system with lots of pipes. And here just some snapshots how Switzerland might look like. And typically we not only have cities, but also these more remote locations with complex terrain where sort of the centralized approach becomes very expensive because you just need to build long pipes. Historically, Switzerland sort of from the 60s onwards, they built up their centralized treatment system. So up today, I think we are about like 97% of like the population is connected to centralized treatment systems. And we also have like a mandatory connection rule. So basically everyone needs to connect, which shows again that we are dealing with socio-technical systems. So like the choice which system gets installed also depends on the regulatory framework. And of course, if we look for Switzerland, like in many other European countries, we have like high connection rates, but of course that's not the same. So I would also be looking forward to the presentations from other contexts. And like the Swiss infrastructure, they face many challenges. not so much sort of the global environmental change, so we are not so affected by water scarcity like in other places in the world, but we also have like a aging infrastructure, and we have like fast social demographic change. So particularly like many people are moving away from the Alps, leaving behind underused infrastructure, etc. And because we have built up such a strong centralized system, we are sort of locked in, and we have very strong path dependencies in these centralized systems. And it's really hard to think about or to rethink existing infrastructure systems. Which basically, I always make the case that like even Queen Victoria would probably recognize sort of the underlying principles how we still treat and transport our wastewater in Switzerland. Good. So in the next section, I will talk about how I approach this question about like the market potential. So how much central and how much decentral treatment we should have in Switzerland. And I sort of did a spatio-economic simulation approach. So I sort of looked at costs for central and decentral treatment and sort of compared it. And more generally, I think assessing these costs is quite tricky because we sort of have networks. So we have economies of scale, and we like have networks effects, and there's also like the important role of geography as I've indicated initially. So the way I approach this is sort of, I think along like a spectrum of a fully decentral system. So with basically every house having its own system versus like a fully central system where we have one big central network which connects every building. And then we sort of have hybrid systems, which are something in between. And I will just walk you very quickly through like the main rationale behind different elements, like cost elements. So on the one side, we have like the central system. And if we compare like this connection rate from like a fully decentralized to a fully centralized system, like for central treatment, we typically have these economies of scale. So the more people we connect to a central system, the lower per capita costs are. So this is well known and pretty standard, and also relatively easy to calculate. The more challenging bit is sort of the whole transport costs. So typically like the sewer-based transportation costs. And there we have like the opposite situation. So typically if we like with increasing connection rate where we start to connect like also like the remote settlements, etc., costs typically become very expensive. So in order to reach like 100% connection rate, this becomes very expensive because of like the remote settlements, etc. So if we combine these two cost elements, okay, so the way sort of how I calculated these like transportation costs is sort of with a heuristic optimization method. So where I sort of simulated like artificial like sewer networks and sort of used terrain and pumping costs, etc., to come up with like costs for different system configurations. So, well, if you're interested in that, you find more information down here. So if we combine sort of the costs for central treatment, we sort of get this typical U curve. And moving on to like the decentral transport side. So for the treatment side, it's typically sort of constant. So it doesn't matter how many of sort of like modular systems we install, the per capita costs are more or less the same. So a very different like cost function here. On the transport side, I think that's less understood how costs are made up there. So in one paper I looked at sort of, I did a modeling approach to model sort of sludge transport and then sort of to see how the transportation costs would look like for different like placings of sewer systems, etc. And so there it's typically sort of, we find such a hockey stick function. So costs only become like very high if we only have a low density, and like the basic message is if we have many of these systems, costs become very, like quite low, and we sort of end up with sort of a more of a flat curve. Eventually, this combining again these two cost elements gives us this hockey stick, and in the final step, if we combine all these costs, we can come up with a cost function which looks like this. So we can see this red line, and basically we sort of find an optimal cost configuration. In this case, it would be like around 50%. So 50% would be decentralized and 50% would be centralized. I know this was all a bit quick, but the basic point is just that I used these cost elements and I simulated them to assess sort of the optimal degree of centralization. And in the next step, I sort of did this whole simulation exercise for the whole of Switzerland for all these different raster cells. And I basically correlated the population density with the calculated like degree of centralization. So this gives me like a good proxy to estimate like the potential also for different contexts. And this is what I did. So for many European countries, I think not all of them, but for many, I did this screening, and I sort of estimated what would be sort of the decentralized treatment share of the population, which would make economically sense. And interestingly, I sort of found three categories of countries. So there's Switzerland, or for example, Austria. There I found that we actually have like over-centralized. So it would actually be cheaper to go a bit more decentralized. And like in a second group of countries, I found that the current degree of centralization sort of is very similar. So these systems seem to be operating at a good level. And then in a third group of countries, we still have like lower connection rates today. And there may be several reasons for that. But basically, these would be good places to go more for sort of these hybrid approaches, and also to extend the centralized system. This simulation then allowed to sort of estimate the European population equivalents, which could be served by decentralized treatment systems, which I estimated to be around 35 million people. And then breaking this down to sort of the number of modular treatment systems, this would be sort of an estimated 100,000 systems a year. And well, looking just at the European map, we see that there might be very different, or like different interesting entry markets where we can scale up enough and get a good number of modular treatment units, well, to also make production well, economically, or well, that there is sort of large enough potential to use many of them to bring down costs. So for example, Germany, or also France and Italy. So maybe some lessons learned from my like PhD and this sort of economic spatial simulation of modular treatment systems. I think one key takeaway is that if regulations would sort of increase the spatial differentiation, this would foster sort of a decentralized treatment. So if we would stop like subsidizing living remotely with centralized systems, I think that would be well, something to think about. And then some countries, I would recommend that they sort of leapfrog this age of fully centralized systems. So maybe it's, or I would recommend that it's better to sort of end up with a hybrid system instead of like Switzerland, to first connect everything and then think about like costs. And then again, my analysis showed promising entry markets, and of course, still many socio-technical challenges remain. So I, for example, mentioned this mandatory connection regulation in Switzerland. This would be like a policy advice for Switzerland to revisit this this regulation. And then other countries, for example, the UK or Germany, I think they could focus on technologically upgrading their systems. And like other countries such as Portugal or Hungary, they should, well, think carefully about where to connect and to generally increase connection rates. So maybe one final thought. This is like a figure for like which shows the price development of batteries for electric vehicles, and like taking this analogy for like decentralized systems like membrane batch reactors or something like that. It will be very interesting if like these costs come down really low, and we might see a complete shift in sort of how the economics behind decentral and decentralized treatment would look like. And then finally, I guess only time will tell where we are or where we will be in Switzerland in terms of connection rate. Thank you.
Thanks very much, Sven. Again, very interesting. There is a question left for you there, but in fact, I'm going to be sneaky and ask my own question instead, if that's okay.
Yeah, sure.
So actually, the results from the various countries were interesting, and for the countries that I would be most familiar with, they were also quite intuitive in terms of the countries where I would expect decentralization to have most impact is what you found. I think that's obviously very good from your point of view. But I was wondering, what is the key characteristic that would make a country more conducive to decentralized treatment than, and maybe the second part to that is, what is decentralized treatment? At what size do you think decentralized treatment comes into play?
Yeah, that's always the good question about scale. I mean, if you talk to Chinese, I think they consider like decentral even something with 10,000 population equivalents. I mean, in my case, I sort of defined decentral as sort of 10 population equivalents. So that's the very modular small, and then 100 typically still is small. But yeah, I think this needs to be defined on the concept, like context. And then the other question, what makes it most conceivable to go decentral? I think like topography is an important bit, obviously. And there is like the obvious countries which come to mind, of course. Yeah, but for example, like the whole water stress situation, I think that doesn't apply to Switzerland, but I think these will be big drivers as well. Yeah, but I mean, there are many factors what determines this question, I guess. But maybe coming back to the final remark about having a system which is developed somewhere else in China or Japan, and then maybe also this innovation might come from a different place. So yeah.
Yes, yeah, no, I agree. Okay, there are a couple of other questions, but we will. I will go through the questions at the end during the panel discussion. So we'll move on to our next speaker, and thank you very much again, Sven, for a very interesting talk. So our next speaker is Tamsin Kennedy, and Tamsin is a senior project manager in the innovation team at Scottish Water, and she's going to discuss the opportunities for decentralized nature-based wastewater treatment for municipal utilities. So I'll hand you over now to Tamsin.
Hello, everyone. You're always wondering if the technology is going to work. So I'm hoping you can all see my slides.
Yeah, we can. Looks good.
Brilliant. Thank you for confirming. Hello, I'm Tamsin Kennedy, and I'm the Environment Innovation Programme Manager at Scottish Water. I'm here talking to you from a very wet Glasgow in the west of Scotland, which is why it looks like it's the middle of the evening here. It's really dark. Today, I'm going to talk to you about opportunities for nature-based wastewater treatment in large utilities like mine. I've locked away the dog and the husband, so we shouldn't get any interruptions, but no promises on Christmas parcels, just to let you know. Just in case you've never heard of Scottish Water, It is a publicly owned organisation and the sole provider of water and wastewater services to Scotland. There are some key stats up there for you. We service 2.54 million households, and critically for this presentation, we have 1,827 wastewater treatment works. These can vary in size from a few houses all the way up to a large city of 1 million people, like here in Glasgow. You'll see there, we also have over 33,000 miles of sewer pipes. It's about 1.5 times around the Earth. So you can agree, we've not got a small job to do. Earlier this year, Scottish Water launched our strategic plan, which covers our planned transformation over the next 25 years. It has 3 ambitions: delivering service excellence, reducing our carbon footprint to achieve net zero, and providing great value for customers. All of these are aligned with the ideals of nature-based wastewater treatment, such as providing a service to all our customers, not just those in big city areas, very low carbon solutions, and responsible spending. Bear with. Also, a major factor in our decision making is Scotland's wastewater sector plan. This was written by the Scottish Environmental Protection Agency in collaboration with the industry to shape the future of these services in Scotland. I have put up the relevant sections to our discussion here: protecting the natural environment, using more blue-green solutions, creating fantastic places for people to work, and minimizing the use of energy and materials. So as you can see, there is a lot of strategy and regulation supporting the transition to more nature-based assets. As you can imagine, we face many challenges in delivering our services. I mention a few here. The climate emergency will change the quality and quantity of our watercourses. It will create increased volumes to treat and introduce greater restrictions on what we can discharge back to the environment. Scotland has targets to reduce its greenhouse gas emissions to net zero by 2045, and Scottish Water has gone one better by committing it to do it by 2040. We always like to outperform our targets. The next slide gives you some more numbers. By 2035, our population is expected to grow, and subsequently, so will the number of households, increasing the demand on those 1,827 treatment works I mentioned. Population movement and changing geographics will require a more flexible and adaptable approach to how we provide services to our communities. As always, there is updated legislation which we will need to be mindful of, which introduce new standards of treatment we will need to meet. All of this means we need to be open to new ways of working and new types of assets and services. We need to seek out those that work with the environment and can be easily adapted to meet the changing requirements of our customers while remaining cost effective. For me, this is where nature-based treatment comes in. I'm now going to talk about our specific challenges in this area and the benefits they can bring companies like us. 90% of our assets serve 10% of our population. I'm going to let that one sink in for a second because it takes a moment to get your head around. 90% of those thousands of assets I talked about only serve 10% of our population. While there are a lot of private supplies in Scotland, that is a large number of people living rurally, serviced by small, distanced assets, which is probably why we have almost 1,200 septic tanks, many of which discharge to the local watercourse under licence. As we know, septic tanks don't last forever, So we need to look at these and decide if we are going to replace them with the same technology, or with all the drivers I mentioned before, if we can look to other solutions. How might decentralized nature-based treatment meet these challenges? If it is working well, final effluents are clean enough to be discharged to the environment. They have small energy and maintenance requirements and use fewer chemicals. However, they may need a larger footprint if we get into wetlands. Though something we have in abundance in Scotland is space. We can also agree that looking out onto a managed wetland is much nicer than looking at tanks and kiosks. As I mentioned, there are benefits for utilities to using these kind of systems. Costs are reduced, which is good since Scottish Water is funded by the public. We can also avoid pumping sewage across large distances, which is expensive and uses a lot of energy. There is a reduction in potential environmental pollution events, and there is a lower health and safety risk for our operators, which is really important. Ideally, we would involve the customers living nearby in system development and maintenance of these systems, so they are invested in seeing it working well and it enhances the local community. However, the big issue here is meeting compliance. Public health is of the utmost importance. So whenever we consider using new treatment, we must safeguard the health of Scotland as well as the environment. Finally today, I would like to give you an overview of some of the research Scottish Water is doing in this area. Although our INNOQUA demonstrator is now finished, and if you want to find out more about that, please visit the virtual site visit this afternoon, we are hoping to detail some further research for the unit ourselves. Septic Tank of the Future is the project we are running with Cranfield University, looking at a new design of tank and wetland to replace current assets. I'm sure Dr. Dottro will talk more about this in her presentation after mine, as well as other nature-based solutions. We have been doing some work with Glasgow Caledonian University on microalgae treatment systems. This is really interesting to me as the harvested algae have the potential to be used as another resource later on in a circular economy. Finally, there is potential exploration going into microbial fuel cells at rural sites. That's all for me today. I'm really keen to find out what you want to know about utilities, if I can answer it. I put up some of the links to useful websites that I have been discussing. If you have any questions, please put them in the chat box, or we can capture in the session. Thanks for listening.
Thanks very much, Tamsin, for the very interesting talk again. I'll just have time for a question from David Tompkins, and just asking if Scottish Water have done any outreach work to small communities about taking on their own treatment assets. And I might just extend the question slightly because it does link with maybe the Irish situation as well, as to what level of political support there might be for stronger regulation, maybe in terms of the management and maintenance of very small wastewater treatment systems. So maybe two parts: firstly, outreach to small communities, and secondly, the political will maybe to impose. Yeah. You might want to answer the second one, but anyway.
No, it's fine. So yes, we are running small projects with communities to gauge their interest in joining with us on this journey for nature-based treatment. And so far they are coming back very positively. In Scotland, we've always had a tradition of wastewater treatment being, out of sight, out of mind, don't get very interested. However, there has been a shift, and now the public is far more interested in knowing where its waste is going, and that includes its wastewater. So it is a journey, and we are just starting, but we are reaching out to those communities and finding what is the best way to work with them and how they want to be involved. The second question about government. So we're lucky because we are government owned. We're very much involved with them and have great discussions. Scotland is one of the countries kind of leading the charge in terms of climate emergency, circular economy. So they're very supportive of all of these issues, looking at reducing greenhouse emissions and protecting the environment. So although we've got a long way to go, like all utilities, I don't think they're going to be a barrier. I think they're going to be very supportive in what we're doing.
And I might just quickly ask a second question, just from Kevin Jeffrey here. And where do, I suppose, innovative technologies or nature-based systems like these fit into the types of decision matrices that utilities maybe, and he mentions in the UK, might use when they're choosing or doing technology selection?
That is something that we're looking to at the moment, and we might hear some more about that from other participants. Our main, like I said, our biggest issue at the moment is compliance. So we cannot install any technology that isn't going to meet all the regulations we need on wastewater discharges and drinking water. In Scotland, we take most of our drinking water from the watercourses. So we really need to protect those. So for us, it's about going through things like INNOQUA, checking that it meets the standards that we need. And once we're satisfied with that, then these nature-based solutions will get onto our decision-making tools, because that's our goal. We haven't nailed down an exact number yet on how much we want to increase our nature-based assets, but it's definitely one of our goals that will come out in our transformation plan going forward.
Thanks very much, Tamsin. So
I see all the questions.
Again,
I'm
we'll
like,
take
just
some
wait.
more of the. I'm sure there'll be more. We'll take some more after the next talk, because we will have time. So thanks again for your very interesting talk. Our next speaker is Dr. Gabriella Dautro from Cranfield University, and Gabriella is a senior research fellow in environmental engineering at Cranfield University, who specializes in nature-based wastewater treatment. And she is going to talk about wetlands for wastewater treatment in the UK. So I'll hand over to you, Gabriella. Thank you.
Thank you very much. Hopefully you can all see and hear, and everything will be fine. Thank you again for the invitation to talk at this event. It's been really interesting. I did try to coordinate with both Tamsin and Fabio, so there wasn't too much overlap. So we'll see how this goes. I've been working on nature-based solutions, and in particular treatment wetlands, for over 15 years. So I'm quite passionate about this. Following on from Tamsin's talk, I'm going to be giving you a perspective on sewage treatment applications for the UK. And the UK might be different from other places in the world, where we have all of our wastewater is managed by utilities that own a large number of sewage works. So we're not working at the municipal level, but in England and Wales, there's private utilities, and then Scotland and Northern Ireland have publicly owned utilities, but all of these manage a large number of sewage works. And that has an impact on how you manage investment and how you manage the systems themselves. And obviously, we have a large number of population connected to the sewer network. And like Tamsin mentioned, a large number of these sewage works are small works, so they serve less than 2,000 population equivalents, and that's my definition of small, which I'm sure people can debate. So Tamsin did a really good job outlining some of the challenges and the opportunities. This I've made from the financial regulator for England and Wales. They approved the next 5 years of investment for each of these private utilities. And these are some of the headlines that came from that business planning review. So there's going to be a need to address drought and flooding, as you expect with climate change. And there's obviously opportunities for nature-based solutions to help contribute to the solutions to that. There's also a key area for improvement in terms of reducing pollution incidents and improving water quality. Some of you may be aware that England failed all of England's river failed good chemical status this year. So there's really room for improvement on how we're doing things. And that can be sewage treatment, but it can also be working in partnership with other users and sources of potential pollution. Nature-based solutions, the good thing about nature-based solutions is that they can provide multiple benefits. And one of the things that you can use them for is, like Tamsin would say, is customer engagement. So engaging with the communities where these systems are placed and influencing the customers' attitudes. All of this is going to be delivered by always keeping the bills lower, and that's from a purely economic standpoint, and that I think is key, that nature-based solutions can deliver these multiple benefits, so you're getting more bang for your buck, if you will, and that's with the traditional approach. Other companies are going with 6 capitals or 5 capitals, depending on where you are, and when you're considering contributions to natural capital, and you make that part of your decision making on what kind of infrastructure do you want to invest in. And there are other companies that are making a really big splash about investing in nature, so restoring ecosystems and planting trees, that kind of thing. So nature-based solutions certainly have a role in that. And treatment wetlands in particular are very well suited for this. So I know Fabio talked a little bit about wetlands. Just if there's anybody by any chance that don't know what they are, this is what they look like. It's basically engineered systems that you design to mimic and enhance the processes that naturally occur, the pollutant transformation processes that naturally occur in natural wetlands. Some will have open water areas, so you can see the water and they look more like a natural wetland, and others are subsurface flow where you shouldn't be seeing the water. But the key thing is that there's many different variations of the technology, and you can design them and operate and maintain them so that they favor certain pollutant removal processes, which are targeting the pollutants of interest. So the use of treatment wetlands in the UK is something that is not new. There's over 3 decades of experience of using treatment wetlands, also referred to as reed beds in some cases. And this is a typical flow sheet for England, actually, where the traditional use of the wetland or reed bed is as a tertiary treatment unit, but they can also be used for secondary treatment. And the original intention here was to remove residual BOD and particulate solids. So we use the horizontal flow variation of the technology. But more and more, we need to remove nutrients as well. And therefore, these flow sheets are being upgraded so that you can provide nitrification, either through vertical flow systems or aerated wetlands that Fabio also mentioned. For phosphorus removal, we can combine them with great technologies like chemical dosing, but also we can look at reactive media systems and more recently into surface flow wetlands for passive capture of phosphorus. So there's plenty of opportunities and there's plenty of examples at full scale that have been going on for a number of years in the UK. Other flow sheets that are very common here are, well, this is a bespoke 7-trend design, I would say. So this is a combined reed bed. So that's a tertiary treatment process that also receives flows bypassed during storm events from the crude. So it will receive a flush of diluted effluent, influent, into the wetland combined with the secondary treated effluent. And there's also a number of septic tanks followed by vertical flow wetlands. These are primarily for small discharge applications and a lot of private properties. But there's actually UK guidance on how you design them so that you can meet 10 BOD, 10 solids, and 5 milligrams per liter of ammonia that was issued by the Constructed Wetland Association a few years ago. So there's guidance for how you design them to ensure compliance, and also from European countries, because that's been one of the main applications for the technology in other parts of the world. So that's what's already there. In terms of opportunities, we've started playing around with French wetlands. Fabio mentioned this. So these are typically 2 stages of vertical flow systems that have also cells in parallel, so that you can rest these cells. You can overload them and rest them for a period of time, and then you reuse them. And what this allows is you can treat sludge and the water in situ, so there's no tanker movements in and out of the site, and you need to go in every, say, 10 to 12 years to do some basic refurbishment of the bed. But other than that, there's no tanker movements, and that's the beauty of them. And they are very either low energy or no energy if you have enough gradient for doing them. Oops, sorry, I just realized that's not coming in. Another thing that's coming in, and this is primarily being brought over from Ireland, are the integrated constructed wetlands concept. And here you combine ponds for initial settling of crude, followed by a series of surface flow wetland cells. And again, that's allowing you to do combined sewage and sludge treatment in situ. We have the septic tanks of the future flow sheet that we've been developing with Scottish Water. And this is a baffled anaerobic pond that is covered, so we're not generating any emissions of greenhouse gases. We're capturing those, and then we're treating with a wetland or two wetlands, depending on what's the application. The last one doesn't have a sizing, so I tried to put some indicative sizings for these things. I didn't put it for the metlands because even though metlands were developed as a secondary treatment technology, and they have a massive reduction of footprint, so you can have a 1 square meter per head metland for secondary applications. We're trying to do in the UK, together with the inventor, so we're not going to destroy this, is to adapt them for a crude sewage application. So again, we eliminate tanker movements from sites. But that's all about treatment. And the idea is that wetlands as nature-based solutions can also deliver co-benefits. So depending on how you design them, the things that you can promote. So you can look into habitat creation, amenity or aesthetics value, and then provisioning services, flow attenuation. It really depends on what are the things that you want to incorporate in the design. But there are ways to do it, and there's examples around the world for doing that. So I brought here some examples, opportunities for the UK and things that we've done in the UK already. So the chart on the left is some work that Nottingham Uni did actually, and they've looked at the biodiversity in treatment reed beds, so wetlands that are used for sewage treatment, that have not been creatively designed. So these are monocultures, only Phragmites as the sole plant species, but you can still have a comparable biodiversity component when you compare it against a natural reed bed that is of similar size in the same region. So that's been really good. So you can deliver biodiversity benefits, even if you don't put that much effort into it and you just build a wetland, a conventional wetland. We've also done some work as part of a European project on ecosystem services quantification. And one of these things, the things that we looked at was on habitat connectivity and where can you place these nature-based solutions so that you can improve habitat connectivity for target species. It doesn't, I wanted to show here that it doesn't take that much to provide these extra benefits, and you can do it with your treatment system. So in this case, with the aerobic wetland, or you can have a tertiary small system that is not designed to provide any treatment, but that can provide additional benefits, and that is safe to have the public in contact with it. And it doesn't cost any more than it would cost you to do another nature-based flow sheet. So this is some work we did for Scottish on the septic tanks on the future flow sheet, and we benchmark the costs of our proposed flow sheet with and without the surface flow element at the end to provide amenity, buffering, and biodiversity benefits, against the grey infrastructure alternative of upgrading that septic tank with a submaturated filter. And we're at less than half the whole life cost of that grey infrastructure. So there's really a strong case for these things. And I'm not saying you should do it for everything, but there's really a strong case that can be made for including some of these benefits in your cost assessments. There's also opportunities engaging with people, and I think a lot of people are more aware this year of the importance of having some nice places around, some green spaces, some blue-green spaces, and there is an actual value that people are placing on that. So wetlands give you the opportunity, with all the large amount of sewage works we have in the UK, to engage with people and to provide these additional benefits. And I put there at the bottom a picture, and I don't know if you can see the clothesline there, but basically that's somebody's garden, and this is from Denmark. So you can design the system so that, you know, people actually want to be near them. And it's also, to me, it's an opportunity to engage with people and reconnect. I think there was a question in the chat and the previous session where they were asking about, you know, the UK has a flush and forget attitude. Yes, we do. and that needs to change. That's not sustainable. So one of the things that we can do by using wetlands is engaging in educating the public. We helped facilitate the implementation of a French flow sheet for Severn Trent a few years ago, and I was involved in the public engagement campaign where we showed people around, you know, this is what we're proposing to do. You're not going to have this grey, horrible infrastructure in your area. You're going to have this green solution that has all these benefits. But we really need you to stop flushing things that you shouldn't be flushing, because that's going to end up on the wetland. And that's one way of getting the message home. Another is to open the site to the public. And if you're walking your dog and there's nasties on your system, you're not gonna ignore that next time you're about to throw something that you shouldn't be flushing. So there's opportunities there for engaging and reconnecting. There's also opportunities for intercepting combined sewer overflows, which are very topical. And there's also opportunities for new markets and green finance, so a different way of doing things. So we can design the system so that we can generate a valuable product, biomass that we can recover. We can engineer them, or we think we can engineer them so we can do carbon sequestration. We can open this for amenity, tourism, education facilities, and also contribution to natural capital, which I've mentioned before. So I could stop there, but if I have a few more minutes, I would like to talk about the challenges of what I'm trying to say. So this is about considering the local context, and Tamsin touched on this. What do actual people value? Do they want to go to the sewage works and walk their dog nearby it, or would they rather have just out of sight, out of mind? So while I believe they're great, not everybody shares that view, and we need to be conscious of what we're trying to do and where we're trying to do it. Co-production is the way forward. So if you're just going to be forcing people to accept something that is not within their core values, it's not going to work. Other challenges are related to risks. So are you going to allow people onto your site? How are you going to keep health and safety concerns? How are you going to mitigate for those risks? And also, where is the consent point? So I put here an example, and everybody in England will be very aware of the River Ingle scheme that Anglian Water and Norfolk Rivers Trust did a few years ago. And that wetland is a tertiary surface flow wetland that was placed after a conventional grey piece of infrastructure in Anglian Water. But the consent point is before the wetland. So when you need to consider what are the risk implications and how you can engage with your stakeholders, the regulator, on how to make this work for the benefit of all. And then there's challenges about the technology itself and the implementation. And I can give you a whole tirade on operation and maintenance tasks. And if it's subsurface, you should keep it subsurface, that kind of thing. But if we don't go there and we talk about just effluent quality, and there was a question on this again in the chat. This is an example that I brought from the implementation that we did of that French system in the UK. And the UK is our sewage works are consented differently from how they're consented in France. So we're consented on spot samples, and compliance is 95th percentile. Whereas the French, all the available information we had was on composite samples, 24-hour composites, and average performance. So for some parameters, it's okay. So that's our consent, 30 BOD. And if you look at the 95th percentile, we're fine. You know, the French curve is much nicer, but we're okay. But if you're looking at ammonia, then that has a bit more sensitivities, and you need to put more effort into how we design them so that we can meet that compliance. So while we'll be okay with a 24-hour composite, if you look at the spot distribution, we wouldn't be achieving our consent on a 95th percentile. So it's about developing the understanding, the processes, and building the evidence for these new designs and applications. And with that, I'll finish there. And thank you, Fabio, for promoting the books. These are all free to download resources, and I'll have links embedded in the presentation that you can click on. So those are the two IWA books, and then the CWA guidance for the UK.
Thanks very much, Gabriella. Another really interesting presentation. So at this stage, it's great. We have some time, and I've taken down and noted plenty of questions. And what I might do first of all is maybe some of the questions are more specific, and I might just pose them firstly, and then there are maybe more high-level general questions. So there was a question for Sven, and it was with regard to decentralized wastewater treatment plant message. And the question was basically, how is that message being received in Switzerland, particularly maybe in the context of current infrastructure reaching its end of life and the opportunities to perhaps rethink the current centralized model? Is the decentralized model being well received, or is it maybe not considered to be applicable?
Yeah, I guess I can only sort of give some narrative examples, but I mean, as you've mentioned, in many places, well, people need to take a lot of money into their hands again to reconnect certain remote villages, particularly. And these are good, like, windows of opportunities where people are actually really interested in sort of the findings of my work, and they, yeah, I mean, this is a critical moment. That's for sure. Yeah, and then, I mean, in terms of decentralized treatment, well, typically also like questions about how do you supervise and how do you operate these systems. I mean, these are usually sort of critical points which are not so well received. But there, I mean, my answer will be, even if you have a decentralized system, you might sort of supervise that in a centralized way. I mean, we do this also with like heating systems in homes, etc. And then again, I mean, we have 30%, I guess, of all pipes are leaking in Switzerland. So I think you just have to have the whole picture when talking about pro and cons.
Okay, thanks. And a second question, and I know there was an answer, Fabio put up an answer to this on the chat, but I might ask the question anyway, just in case anyone didn't see it. And it was with regard to the effectiveness of monitoring techniques at decentralized wastewater treatment plants. And maybe I'll just play devil's advocate in this question and say that over the course of my experience, I've tried pretty much every sensor that you can find and every variety of remote monitoring. And when it comes to wastewater applications, I have limited faith in remote monitoring, but I leave it open to anyone in the panel to maybe push back on me on that.
Well, I can just add a very short comment that the way we are trying to develop something reliable but even economically feasible, let's say, is to make use of these low-cost sensors that are built by just making use of these low-cost motherboards like Arduino and so on. And the trick is just to choose the proxy key performance indicator, which is the right one for your application. I mean, for instance, for a green wall located, we are designing a full-scale one in Lebanon. Our main issue is just to observe that the water is all time fed in a even way, let's say, in all the pots, because we have a lot of parallel lines, like 15 parallel lines. And so we have to be sure that valves, pumps, and so on are working fine all the time. So we will just put some very easy sensors, like a humidity one that is already very used everywhere in greenhouses and so on, just to look at the presence of water in the pots. As soon as we get an alarm which is saying in this line there is no water anymore, well, that's something which is going wrong there, and we need a physical intervention of workers going there and looking what is happening. So it's just a matter to look in a smart way to which kind of proxy indicator you can use in order to have a robust sensor which is even cheap. So that's the way we are trying to develop things.
Yeah, and it would be great actually for maybe regulators to engage a little bit more on that aspect as well. I suppose the surrogate monitoring, I fully agree. Maybe this could be for Tamsin and or Gabriella. Just wondering in terms of your experiences, what are the trade-offs that you're seeing that utilities are having to make in terms of the whole life cycle costs of technology versus the fact that maybe often the capital costs are really what drive decisions. And I'm just wondering, what have your experiences been on whether utilities are able to move towards more looking at whole life cycle costs rather than just upfront capital costs?
Yeah, so we're actually in Scotland, they're redoing how we do funding for utilities, and I am not the right person to talk about the funding part, but the fact is we are moving from a long period whole life cost funding model to one that is more agile, that works in shorter periods and doesn't look so much at the overall big spend as much as the benefits. So there's a definite shift in the way that we're working in Scotland. And I would say that it is very difficult because at the moment, things like capital spend on assets is a known factor. We know how much it's going to cost. We know how long it'll last. We know the treatment capabilities. And it's about looking at all these new technological solutions with the same lens. And I'll probably talk about this afternoon, but anything new has to meet or beat the standards that we currently already have, or else it won't get traction. And it's that makes it difficult when you're working in innovation because everything is new and we don't know what's going on. But that's what we're moving towards. I hope that answered your question. I think I went off on a tangent, but yeah. So we're always looking. So it's not just about cost, and we're shifting, but it is difficult because that's a kind of known outcome.
Thanks. And actually, maybe Gabriella, obviously, if you want to take up on that as well, do. But maybe if I could add a second part to that as well, is the issue over the maybe the whole life sustainability of a system. So, for example, we talk a lot about consent and discharge limits and the ability to meet those, but it's something that I know a lot of people think about is how far should we push these these consents and discharge limits, because it results in upstream utilization of extra energy, chemicals, etc., etc. And again, just in terms of your experience, where has that kind of whole life cycle sustainability or cost started to come into thinking of utilities?
Okay, yeah, no, that's a good point. Both good points. And I must say I'm a Cranfield, so I'm not a utility. So it's my experience of interacting with the different companies. And I'd say there's definitely a difference with the way we can work with Scottish, because it's a publicly owned institute, and that makes the whole difference on how we can tackle some of these things. Whereas the private utilities are, it's a different world. But in terms of, I think there's good intentions. And Yorkshire Water is doing the 6 capitals approach, and they've developed a tool so that they can prioritize interventions based on the 6 capitals rather than just the capital, the hard cash capital investment. And there's been lots of predecessors to that kind of approach. But the reality, so there's the trend is going in the right direction, but it's not quite there yet. I think still capital investment, it all comes down to capital investment at the moment still, in spite of everybody's best intentions. And when we have put forward these innovative flow sheets, we can get away with a demonstrator where you can spend a bit more money than the alternative grade solution, but you wouldn't be able to extrapolate that to a large number of works without improving that capital investment. So I think there's still a way to go. And your other point about sustainability, and that's something again that it's because of the way policy is moving. So the net zero targets are, in my view, they're helping because there's been this push of lower, and with aerobic treatment that means more air, and that means more energy, and we're just shifting the problem from water to atmosphere, and that to me is doesn't make any sense. So we are starting to move in the right direction, but I would say we're at a glacial pace compared to what's actually needed. Yeah, that's my view, though. With that. Not Cranfield University's views.
No. And I know it's interesting to get that experience of someone who does work with, obviously you're working in Cranfield, but who does, you know, liaise a lot and work with utilities in the UK and maybe elsewhere. Maybe on a broader issue, and one of the things that struck me, you know, working on this project, but obviously on other projects, is one of our demonstration sites, for example, in India. And we went, as part of that, we went to see a fecal sludge treatment plant near Bengaluru in a place called Daphniafilter in India. And it was a brilliantly engineered piece of infrastructure, something that would not even be thought of in a European context. It was basically treated for about 30,000 people with utilizing no energy, just utilizing what I call engineering ingenuity and scientific ingenuity. And my general question is that we talk a lot about maybe knowledge transfer, but perhaps I wonder, do we talk about it sometimes in the wrong direction, as in, do we think that we should be teaching other countries how to do things, or is the problem actually that maybe in a European context, because that's what this session is about, we need to learn more? So I'm throwing that out there for general discussion. And if so, what do we need to learn?
Who wants to go first? Fabio, do you want to go first? Because you do, I mean, I come from a developing country, so I come from Argentina. And I think, what is it the same? Necessity is the mother of all invention. Just when resources are scarce, you do things differently. And I think there's certainly things that we could be learning from other contexts that are relevant to European way of living sustainably. I don't know, Fabio, if you want to comment on that one. I know you've done a lot more work than I have actually on that.
Well, yeah. So yes, we have had a lot of international experiences, most often developing economies, let's say. We have also worked a lot in India, for instance. And just taking the specific case of India, what we have met there, just trying to introduce our knowledge of 30 years of experience on wetlands, science, and so on, we have found that the local companies were selling similar wetlands, let's say, which were shrinked to 1/10 or even worst in terms of size, in comparison to the normal worldwide accepted design guideline for this kind of treatments. So they were undersizing the system severely. And at the beginning, we have tried a lot to interact with the local engineers and professors of the universities, telling them, well, you can operate such shrinked systems for a couple of years, then you will get them clogged. And what we have discovered is that their monitoring is simply stopping after the 6 first months of operation in most of the cases. And that's why they don't observe the long-term performances. And they are putting out of the market other companies which are trying to make things in a more, let's say, long-standing way. So that's a difficulty we have found there, but that pushed us for finding a sort of midway. Let's say our fully scientifically covered knowledge and way to design the system can try to go in the direction of the Indians designers trying to adapt to the advantages that, for instance, a tropical climate country is providing in terms of kinetics of processes and so on. And that's something that is simply missing literature for giving us enough numbers for calculating constants and so on. So until we don't have good monitorings done and big data sets to be observed and to play with, then we can simply adapt our knowledge to other countries' knowledge. And so it's simply a basic availability of data what we are missing at the moment when we are operating in different situations. What we can learn is the practical approach. I mean, for instance, in Jordan, they are treating the grey water with 3 plastic barrels filled with gravel. where the water is flowing downflow, upflow, downflow 3 times, and that's enough. That's a fixed biomass, which is quite similar to a vertical flow. Simply the plants are missing, but that's a technology they are using since centuries. And why not to consider it? I mean, it's a simple trickling filter, but by the way, that's the method that the households are using in that country where the water is missing since forever. So they have the problem and they have found a solution. It's good to learn how they do that and then to try to put our science and our knowledge, all the backgrounds we are having, for understanding what they are traditionally doing and explaining it with the questions. Yeah.
Thanks a minute, Fabio. I'm going to, I know we are due to stop, so I'm just if I could ask just one other quick question, and maybe I'll direct this at Gabriella, but obviously probably any of the panel may be able to answer. But you just spoke about the community engagement aspect, and I think as part of the INNOQUA project, the system itself, as you know, uses earthworms, and I've worked in wastewater for a long time, both on mostly on conventional systems, but also on natural-based systems. And it's the first time I felt guilty about doing certain types of experimentation on my reactors, because normally it's just bacteria, and it doesn't really matter what you do. But in this case, there were worms who had actually been treating wastewater for a year or 2 years, and here I was going to try and stress them in some way, and I felt a bit guilty about it. So I was struck by your by what you mean about community engagement, and I was just thinking during your talk that even if someone like me who works in these things every day can be, impacted by having a more natural-based system or dealing with kind of living creatures within your wastewater treatment system, that there must be a huge scope to re-engage the public in wastewater treatment in the way that they are maybe with water, potable water or energy. And just maybe if you have any kind of final thoughts on that aspect of community engagement and how we can leverage that to the highest degree possible.
I can try, and then Tamsin can come in with the what did we call that project on community engagement. I think, so, with the disclosure of personal stuff that is recorded for all eternity, I'm vegan, so I'm not so keen on the earthworms myself. But I think there is real potential for seeing how these things can help us reduce our impact in the environment. I think, what was I going to say? The question that I hear a lot, especially when we're talking about treatment wetlands for industrial wastewater treatment applications, is how are you gonna protect those birds? How are you gonna protect? So you're generating a biodiversity hotspot for in your treatment system. Is that really a good idea? So those are some of the things that need to be thought through in the design, and what are you trying to achieve, and how are you going to keep this so that it's not creating more harm than it's making any good, if that makes sense. But those are sort of the trade-offs that you have to consider in part of the design. And I think it's important that messaging is made as clear as possible as well when you're engaging with the community to get the support. That's, my view.
So yeah, I think we're up against the clock. So I'd just like to thank the panel yet again for both all their presentations and for the discussion afterwards. There have been some questions also left in the chat, which were answered on the chat or might be answered in some later sessions. So I didn't go through all of them. But David, will I hand back to you just with regard to the next session, and thanks again to the panel.
Thank you. Sure. Thanks so much indeed, and thanks very much to the panel members for that fantastic session. This is just a reminder, we're taking our final break now.
Hi everyone. So welcome back to our third session of today's conference. So for those who join us, so I'm Jean-Baptiste Dussaussois from NOBATEK, so located based in France. So NOBATEK is a private research and technology organization, and we are working on the development of technologies service into the sustainable building sector. So for some of you who were present for the first and second session. So we have discussed about many points regarding natural-based solution and how natural-based solution can tackle the issue about the wastewater treatment in different contexts. And for this third session that I'm really happy to chair and to facilitate, we're going to discuss about some other specific point and about how the natural-based solution system and in some way how more specifically the Vermifilter system can address the issue of wastewater treatment. So basically from this afternoon, we expect having a full presentation. Unfortunately, one of the presentation made by Andreas Schmidt won't be able to join us, so you apologize for that. So we're gonna to shorter a little bit our session, this our third session, and I'm really happy to have today with me for this presentation and to continue discussion regarding this topic, to have Claire Furlong and to have also Chris Buckley and Ajik Owak, and we're gonna to start with your presentation, Ajik. So your presentation will be about commercialization and how you succeed and you are doing the scaling up of the Tiger biofilter technology in India. So I will let you introduce yourself in your presentation, but roughly and briefly, you are engineer and owner of a Primove consultant based in India, and you are also the founding director of TBF Environmental, and you have worked with Claire, who will present later on a presentation about the development of the Vermifiltration. So I'm happy to having you, and I'll let you the floor to share your screen and to start your presentation. Thank you very much.
Yeah, thank you very much. Just give me a minute before I sort of share my screen. So can everybody see my screen? Can I just get
yes, it's okay.
Yeah, great. Thank you very much. So yeah, so right. So I'm Ajit Oak, and I'm working with a company which is newly formed a couple of years back called TBF Environmental Solutions. And I'm coming from a different background than what we have heard so far in this conference. I'm coming from a completely commercial background. We have been working on this technology on vermifiltration for last now close to more than 6 years. I think initially Claire was also involved with us. And we're trying to, we are in the market to basically scale this and commercialize this, this nature-based technology. So we have got actually 4 products that we've developed with vermifiltration, starting from household toilets that you see on the left. So these are digesters that we have developed, which can be sort of attached to any of the 4 flush toilets, and they treat the waste right on spot. They also use vermifiltration. Then we've got sewage treatment plants, large-scale sewage treatment plants, which treat urban wastewater. Then we've got similar smaller scale ones, which are good for apartments and small houses, small housing complexes, and commercial enterprises. And then we also got what we call as fecal sludge treatment plants. So all these apply vermifiltration technologies, and we've been trying to push these into the market in India. So again, based on vermifiltration, we use tiger worms mainly in our treatment, which is Icena fetida, and that's how we call this tiger biofilter technology. And I'm not going to go too much into this. We've been hearing about vermifiltration since the start of the conference. So yeah, I mean, these are found around the world. They are the best composting worms, and they also self-regulating, which in terms of population, which is a really handy thing to have when you're trying to treat organic waste. So as I said, we've got these different applications, and we have been in the market. So the Tiger toilet digester, we built more than 4,500 toilets so far in India, in about 11 states, so different geographies. So I mean, we've got very good results and feedback for this. The main feedback that has come from the rural population is the fact that there are basically no smells, and you don't need to desludge. Our oldest toilets are now more than 6 years old, which Claire was involved when we put them together, and they are still going pretty good. Similarly, we developed these apartment scale or small scale sewage treatment plants and larger scale plants which are treating urban wastewater from a few families. Now, the largest one we have is treating about 500,000 liters of wastewater every day, and the water is being recycled for gardening. And we've also now built fecal sludge treatment plants, which is actually treating waste that's brought in from septic tanks with vacuum trucks. So very strong waste. So coming back to commercialization, because I'm going to focus both on the technology as well as the commercial side of things. So coming to commercialization, just looking at what we need to have in order to scale up. So there are certain criteria which we've tried to list, and we're trying to develop ourselves around this, which is having the effective technology, having the right certifications and recognition, having the IP, and trying to maybe have one or two solutions where you can really create a niche market around and create your own space. And we feel this is the fecal sludge treatment plants that we have recently started installing, and we've got very good results around that. Of course, we need a strong team which we're trying to build. We need favorable policy environment where nature-based systems are being pushed. We need good partnerships and, of course, funding in order to scale up and expand. So that's the sort of canvas we have. Just very quickly on the functioning of these technologies. So our Tiger toilet digesters are very simple digesters, as you can see here in these sketches. So they attach to rural toilets and they receive the waste and very quickly decompose. You can see this is a picture inside a digester that is 4-year-old, and it's being used by a family of 4. And there are now more than 4,000 of these in different parts of the country which we've built. Similarly, we've built these Tiger biofilter plants. You can see this small sewage treatment unit that is fixed under the stairs in a parking lot, and this is treating the waste from an office upstairs, and it is being again recycled. The one on the right you see is a larger scale version of that. Now we've got still further developed these into packaged units, which we can actually pack off and send and install in a day's time. So we are sort of continuously improving on the product there itself. In terms of the results, I think we've been able to achieve fairly good parameters, meeting all the pollution control norms. You can check out the COD, BOD, which is like below 50 and below 20 is the targets that we need to achieve, which we are very easily achieving. Similarly, there is increased dissolved oxygen. There is reduction in total suspended solids. So we've been basically able to meet the standards pretty well. So in terms of solutions, I think what we find right now is probably the most powerful application of this vermifiltration technology is for fecal sludge treatment, centralized fecal sludge treatment. There is also a big opportunity to do good work. Right now in India, there are so many towns and villages which are dependent on septic tanks and pits which get emptied and get sort of discharged, very unhygienically. And there is a big drive to provide good fecal sludge treatment units, and we are trying to provide solutions for that. So for that, we've now built 3 fecal sludge plants, each treating fecal sludge from population of about 30,000-40,000 people. And so the trucks bring in the waste sludge and it gets treated into this. So it's not purely a vermifiltration based system, but a sort of a hybrid system which has a step for anaerobic treatment followed by vermifiltration and followed by more like a wetland system. So it's a combination of 2 or 3 different technologies, and it is achieving pretty good results. As you can see here, we get waste ranging from, you can see COD ranging from 33,000 to 139,000, BOD ranging from 2,700 to 43,000. So that's the range. These are laboratory test results carried over a period of 1 year on one of our fecal sludge plants, and we've been able to sort of get reports, as you can see here on the right, which are fairly, we've been able to give very good outputs for all the parameters. And right now we are trying to promote this across the country, trying to bid for different projects being floated by the government. And as an output of these fecal sludge plants, what you're getting is treated water, which can be used for irrigation, gardening, and of course vermicompost, which is a very good fertilizer. So there is a lot of potential currently in India, with the fact that, as I mentioned earlier, a lot of towns and cities do not have sewer network, and it is very difficult to lay sewer network across large towns and villages. So this provides a very quick solution where the town actually buys some suction trucks and they provide a centralized treatment unit, and the pits and the septic tanks are emptied and brought to this place for treatment. It is a fairly low capital intensive. It has very sort of quick turnaround time, and you can get the system going quickly. And that's what we're trying to sort of harness right now. This opportunity which is there. So far we built 4,500 toilets. We built a number of sewage treatment plants. We have 3 fecal sludge plants commissioned and 5 in construction phase, and to be commissioned in the next 2 or 3 months. We've recently also gone out of India, installed some systems in Hawaii in the US, and they are being tested right now for approvals for wider applications. We've also won some contracts for large scale sewage treatment plants with vermifiltration technology. In terms of sort of going ahead from here, we are looking for partners or dealers in different parts of the country for small scale STPs, and also we've got queries from outside India, from Africa, and from US, where we are trying to forge some partnerships. We are looking at licensing the Tiger toilet digesters to small scale operators and local masons who can actually do this, and we hope that this would really help scale up the efforts quickly. Also for the large scale STPs sectors, we are in discussion with some utilities and companies to accept the technologies. Of course, there are a lot of hindrances in clearing the initial sort of gateway where the technology has to get approved at various levels. And as I mentioned earlier, the fecal sludge technology market is what we are trying to expand. And we are looking for investments, and basically as we go for government tendering, we are looking at a level playing field because we are new entrants and we are with a natural based technology. So that's where we are. We've got a number of publications which you all can refer to. A lot of them are from somebody who's going to speak after me, Claire Furlong. So she's been involved in the development of this technology right since the initial stages. And we filed for a few patents as well, which are under consideration. We have been also recognized by press in the print media as well as internet. And so it is slowly sort of catching up, and we will hope that it helps us scale up. So that's where we are. Thank you very much. And I can take any questions now or later.
Thank you, Ajit, for your very nice presentation. So thank you very much for all the opportunities that you presented for the vermifiltration in India. I just gonna in the way of some questions that we receive, and it's absolutely the ways that I would like to discuss and try to catch your views regarding what can be the barriers you are facing for uptake more quickly, let's say, the system, at least on the Indian market. Do you have any regulation barriers, social acceptance? It seems technically not, but all other issues. What are the issues that you are facing or barriers to speed up the process of uptaking on the market?
Yeah, I mean, one of the biggest scale applications. A lot of it in India is driven by government policies. A lot of the utilities are owned by the government. Most of the work is done by government departments. So trying to break that barrier of getting your technology approved, making it acceptable, because there are a certain list of technologies that get approved, and mainly they are with this, very high energy intensive, typical standard treatment processes. So yeah, I mean, so what we've found is FSTPs is one way of entry into this, because it's an entirely new kind of thing that is getting implemented. So we are getting more space to implement there and prove ourselves. So that's where we are trying to push. But yeah, most of it is to do with regulations and approval of the technologies, and of course having enough resources to be able to expand.
Yeah, of course. And do you think that on a broad market, for instance, you explained that you will have a system, or you have a system installed in US. Do you think that you won't have this kind of buyer, or maybe different buyers? What is your expectation regarding, let's say, exporting your solution?
Yeah, I mean, there I think what we can really compete with is the price right now. So,
Yes.
the solution that we are offering is, quite a bit lower than what's rightly currently prevalent there. And if we pass through again the barriers of the long testing procedure that has to go in order to prove the technology, then potentially we have a good market, I think, especially in areas in the US which are like Hawaii or southern parts, which are not exposed to extreme colds, uh, is I think a better potential market at this stage.
Okay, and to briefly come back to your exploitation strategy. So it seems that you already installed more than 4,000 systems in India, or Tiger toilets. What is, let's say, the business model you have decided to set? Or, I mean, do you have any subcontractor, installers, a network of distributors? How do you work? Because, mainly for NBS, the main issue is how we can transfer from the concept, which is proved, and the demonstration site we have already proved the efficiency, to the direct market, meaning that being integrated in a sometimes already existing network of installers, distributors, and so on, or not existing. So how did you proceed on that, and how are you proceeding now?
Yeah. So there is, I mean, basically we have to look at it in two ways. The toilet solution is a very different solution than the other more centralized solutions, or the ones that INNOQUA has also tried, which are more centralized. The toilet solution is something that is used by mostly rural populations. It is very decentralized. It is one family, one customer at a time, maybe. We had a good opportunity a few years back where we could sell in large numbers. It was a big government program called Swachh Bharat Mission in India, which was trying to push toilets, and we could get into the market that time. That was mostly through, again, a lot of NGOs or the district administration, which was trying to install as many toilets as possible, and we could get our product out there. Now, what we found is that it is very difficult to sell this product in being in a centralized position. So, what the way we are looking at now is to make this technology or the approach available freely to masons and self-help groups, and at least for the toilet part, and let them actually implement, and we can provide the technical support with very small licensing arrangements, even if that is required. So that's one approach we have taken for the toilets part, and for the larger units we are trying to bid for government tenders or partner with other organizations and be a technology provider for them.
Okay, and do you think such a let's say, business model of kind of open access, I mean, where you will provide technical consultancy, can be replicable to other markets, especially the one that you are targeted? I mean, or do you think that we have to think about new business models if we want to make sure that we can implement as much as possible this solution, which can be, in fact, be a support for local communities?
Yeah, I mean, there are a lot of potential opportunities. Again, we have to see for different line of products in a different way, but there are opportunities of tying up with local groups, local self-help groups, local microfinance groups, and implement these solutions, because there is also a lot of demand from these small towns and villages for better sanitation solutions. So although there may be now a number of pit latrines and the coverage may have increased, but there is always this aspirational issue involved to this. So trying to identify such partners at local level is going to be the key. So perhaps in order to scale up, what we also are playing an idea with is that we identify areas which are growing, where this demand might be higher, and then tying up with groups there. So that's one of the things that's under process right now.
Okay, so thank you, Ajit. I just browsing through the chat box, and there's a question from David Tompkins regarding the large sewage treatment plants that we have installed and about the odors issue. So did you encounter this kind of issue? Yes, no, and if yes, how did you manage this?
Sorry, is that about odors? I don't.
Yes.
Yeah. Yeah, I mean, that's one of the things that people appreciate the most, in fact, in the decentralized home toilet systems, that there is basically no odors, and that gets there. That's sort of one of the things about vermifiltration. That's the first thing that seems to get addressed very quickly, and I'm sure Claire would add to that in her chance to speak.
Okay, great. So I think it can be a nice transition for your presentation. I think that I brought a question, and I've asking mine because I took the advantage of having the mic to ask you different questions. So thank you very much, Ajit, for your presentation. And so I'm going to ask Claire Furlong to share her screen. If you can please share your screen, Claire. So you're going to present us some development and use of Vermifilter in a specific context, which are the humanitarian setting. And of course, I will let you know, introduce briefly. So Claire, you are an environmental engineer and senior lecturer at IHH Delft Institute for Water Education. And you have worked, of course, alongside Ajit on the development of vermifiltration and tiger toilet. So I'll let you share your screen and start your presentation, and I will catch all the questions you need. They will have, but anyway, so take your time, because I say that we have 3 presentations rather than 4, so meaning there'll be more time for discussion after your presentation. So please, Claire.
Can you see my screen?
Yes, perfectly. Thank you very much, Claire.
Because I've also been practicing with a laser pointer. Cool.
That's fine.
Excellent. So my name's Claire Furlong, and I'm a senior lecturer from IHE Delft. And I work generally on on-site sanitation, so non-networked sanitation. And I'm presenting work that's been a collaboration with Oxfam for about 9 years now. And it's on the development and use of vermifilters in humanitarian settings. And the vermifilter that I'm going to talk about, we call the tiger worm toilet. I just wanted to warn you that I'll be using the term shit during my presentation, so I hope I don't offend anybody. Okay. So at the moment, the world's got the highest level of human displacement on record. So there's 79.5 million people are forcibly displaced worldwide. And that's about 1% of the population. So people are displaced because of natural disasters or man-made disasters or complex emergencies. This displacement threatens their well-being and safety and prevents people from getting access to the necessities that they need for life. So things like food, clean water, and shelter. This also includes safe and dignified sanitation. When we talk about displacement, people are not displaced for short amounts of time. So nearly half of the refugees, and refugees is a term that refers to people that have been displaced outside of their original country. It's over half of the refugees have been displaced for over 5 years. And of these people that are displaced out of their country of origin, 10% live in camp settings. Another term that I'm going to be using during my presentation is internally displaced people, and these are people that are displaced within their country of origin. So they move from one place to another. So when we talk about camp settings, I think everybody will have heard of Cox's Bazar, and currently that's the largest refugee camp in the world, but not many people perhaps will know that it was actually founded in 1991. So lots of these camps have a huge lifespan. So the average lifespan of a camp is 24 years. And a huge cost that comes with these camps is the managing of traditional on-site sanitation systems. So that's pit latrines, septic tanks, cesspits. Camps are often situated in isolated areas where it can be challenging to find equipment or services for emptying. And it can even be a challenge to find land to set up a treatment plant or even dispose of the fecal sludge from these systems. So what happens in the short term is external agencies such as INGOs, such as Oxfam, tend to meet the cost of emptying. But as the crisis or the life of the camp goes on, the long-term costs of operating and maintaining these sanitation systems are, have to be covered by the community itself or perhaps a local authority. And this is why we need to explore more sustainable options for camp sanitation. All of the figures that I've talked about don't cover internally displaced people's camps. And so if you're looking, if we take as an example, Rakhine State in Myanmar, they've got over 140,000 stateless Rohingya living in camps or camp-like conditions. And we've done a number of trials with that population. So we shouldn't forget that a majority of refugees and IDPs live in urban settings. They normally live in peri-urban areas with low or no, low quality or no sanitation. And what happens in these settings is very similar to the camp settings. Initially, the service provider is an external agency, possibly an INGO like Oxfam. And then as time progresses, the community takes over the management of the sanitation systems or the local authority. And they might not have the funds to cover the operation and maintenance, the emptying of the pit latrines, the emptying of the septic tanks. So again, more sustainable options are needed. And this is why Oxfam became involved in the development of the tiger worm toilet from its conception. So if we just look at the timeline for the tiger worm toilets, it's been in development for about 9 years. It started with a grant from the Bill and Melinda Gates Foundation. Ajit from Prime Move sat on our advisory board with Oxfam as well. The concept is to use composting worms to eat the solids in the system, meaning that the need for emptying is dramatically reduced. So I was brought in to look at the proof of concept or to do the proof of concept trials. So my research question was, do worms or do composting worms eat fresh human shit? I found out that they did. And then we went on to build our first prototype in 2012, and that was at the Centre for Alternative Technology in Wales. Oxfam then went on to do a field trial in Diradawa in Ethiopia, and then started its projects in Liberia. We started a more systematic trial with Oxfam and Prime Move and Water for India, Water for People even, in 3 countries, Myanmar, India, and Uganda, and in 3 contexts. That's an IDP camp, a rural and a peri-urban setting. So Oxfam's gone on to build over 1,000 tiger worm toilets, and it has 8,000 users in 4 countries. And they've also gone on to trial different configurations, and they've done a number of projects where they've been developing their systems more, which is what I'll be talking about. Oh, I seem to have a delay. Oh, there we are. So I've spoken a lot about the tiger worm toilet, but what is it? It's a very simple concept. I have a little, this is great, a laser pointer. So this is the vermifilter. You have a tank which has an open bottom to allow liquid to infiltrate. You have a drainage media and you have a bedding layer where the worms live. Your shit, urine, wash and flush water enters the system. The solids get trapped on the top of the bedding layer. The liquid infiltrates and the worms eat the solids. So the worms are able to reduce the wet solid volume between 80 and 90%. They convert human shit into worm shit. The worm shit or vermicompost is relatively dry. It's generated at the top of the system. So it's easier and less risky to empty. So this table details the Oxfam projects and the developments in the tiger worm toilet. So you've got the projects listed here, the number of years the project ran over, and then you can see some of the different designs that they've trialed. So they've looked at kind of the toilet type and the user interface. So pour flush, pedestal, Myanmar type, that's a pour flush system that doesn't have a water trap. They've looked at different numbers of users, the different surface area, because that's really important for the worms. We've also trialed a number of different worm species, from the tiger worm to, this is the African night crawler, this is the sister worm to the tiger worm, and the Indian blue, a mixture of worms. Oxfam's also trialed a number of different of bedding materials, mainly wood derivatives or coconut husk, and this was informed by the laboratory studies. We've also experimented with different worm densities because in some areas actually sourcing the worms can be slightly problematic or expensive. So we started from 2 kilograms of worms per meter squared, and we've dropped down to 0.66 in our latest trial. In this last column, what you can see is the different innovations that have been trialed by Oxfam. And I've got this trial here in bold because it's worth highlighting, because we have a really nice data set. So we've got 20 months worth of data, and I'll be writing this trial up into a paper soon. And this was a trial of a communal tiger worm toilet at an IDP camp with Rohingya IDPs. So I've spoken a lot about the trial, so let's just, hopefully I'll be able to transport you there with some of our pictures. So this was a trial in Monrovia. It's in a peri-urban environment. The toilet itself would be in the house, and this is the Vermifilter. And this trial was implemented with community training program. And the idea was that people would go on to start businesses with the new skills that they acquired. This was, these are pictures from the trial that Ajit was involved in, but these pictures are from Kachin in Myanmar. It's another IDP camp, and this trial was funded from by Water for People, USAID. You can see here that this is an offset pour flush design. In this picture, what you can see is the bedding in the Vermifilter, and then Christian sorting out the worms to add them. So the results from this trial weren't published, but I think at the end of Ajit's presentation, you saw a list of publications, and the prime move part of this trial was published in Waterlines. I'm going to skip this one because I'm running out of time, but you can ask me about Gambella because it's a very interesting place.
Yes, Claire, sorry, you can take your
okay.
time. Yes, I mean, anyway, if it's too long, I will stop you. So, but if you want to present it, I think it's fully interesting, so please go ahead.
Oh, okay, so in Gambella in Ethiopia, this was a trial in a refugee camp. Gambella borders South Sudan. And this was funded by UNHCR. And this was the first trial where we were actually growing up the worms to use. And so you can see this is the harvesting of the worms. And these are the tiger worm toilets. So we used the Sato pans here for direct drop into the systems. Although the camp itself was very clean, this was the first time we'd had issues with rats, and we also had issues with the quality of the building and monitoring in this trial. This is the most recent trial. This is in Satamanje in Sitwe in Myanmar. This is an internally displaced persons camp for the Rohingya population. When we started the trial, it had been there for about 8 years. It's been there now for about 10 years. The complexities of doing research in humanitarian contexts. I mean, this trial ran through the genocide and also I think it was 2 cyclones. This was a trial of a communal tiger worm toilet. We had 2 designs and we collected data for 18 months and compared it to the standard available systems in the camps. What we found is that we only had to empty one of the 34 tiger worm toilets in the 20-month period compared to all of the controls, which were on average emptied twice during the 20 months period. Because we're looking at sustainability in a holistic way, we also looked at satisfaction. What you can see on this tiny graph is the results of a baseline and endline survey. So the green bars are the original latrines that the users had, and the orange represent the tiger worm toilets. And this is increasing satisfaction. So you can see they were quite dissatisfied with their current with their original sanitation, and they were very satisfied with the tiger worm toilets. Because of this, 99% of the users wanted to continue to use them after the trial, and they are using them. So this has been, these have been kept at the camp and are now run by a different organization. This is the inside of a tiger worm toilet, or a well-functioning tiger worm toilet. What you can see here is you can see the inlet pipe, you can see fresh human shit that's been deposited. You can see the hairy area here. This is the coir or the coconut husk, which is used as a bedding material. And if you see these dark browny black areas, this is the vermicompost as it's building up. As it builds up, it gets pushed to the edge of the system. So we like to think about sustainability quite holistically. So we kind of look at social sustainability and whether the systems function, but we also look at the economics. So we looked at 5-year life cycle costing for the communal tiger worm toilets in Satamanje, and they had 47% lower costs over 5 years. That includes the CapEx cost and the OpEx cost. When we look across the trials that we've done, we can say that CapEx, or the capital cost you need to build the tiger worm toilets, is very context specific. It ranges from $175 to $400 per toilet, and the worm costs can vary significantly as well, and they can be very costly. So in these trials, we've paid up to $210 per kilogram of worms. When we look at the OpEx, the standard toilets that are our kind of competitor systems normally need to be emptied between every 2 months and twice per year, and the cost of that is over $400 per year. But in all of the trials that Oxfam's done, they've had to empty the tiger worm toilets less frequently. So Oxfam's learning to date, well, the tiger worm toilet is adaptable. We've trialed different designs. We've been making them from local materials, and we've tried them in different contexts. Community engagement is key, but that's the same for most sanitation projects. We've had quality control issues with the building of the tiger worm toilets, and that's because we're using local materials and local labor. We've been able to use different worm species. As long as it's a composting work, it should function. And I just wanted to highlight that not all earthworms are composting worms. These have a special ecological niche. Worm supply can be difficult, but Oxfam has produced guidance on growing up the worms, which it's done in 2 projects successfully. There have been issues with monitoring and documentation within the trials, and that's just because of the complex situations that Oxfam works in. And there has been some issues with knowledge management. I just wanted to say at this stage, I'm not advocating that tiger worm toilets should be used in all humanitarian contexts. Like any sanitation technology, they work well, but there are kind of constraints to how the context that they will work in. So we have developed this decision tree, which will help you decide whether this is an appropriate technology for your situation. So knowledge management has got better, and Oxfam has produced a manual and documents to summarise its learnings to date. Within the design manual here, there are detailed designs of all of the tiger worm toilets that Oxfam's implemented throughout these different trials, and also things like bill of quantities, so you'll be able to see what kind of resources you require. Is this technology mainstreaming? Well, more people know about this technology, and it's being featured in key humanitarian texts such as the Compendium of Sanitation Technologies in Emergencies. So more people are getting to know about this technology, and the more people know about it, the more likely they are to choose it if it's appropriate for their setting. This presentation was based on a number of different trials over 9 years. So there's lots of different funders that I just want to acknowledge. And I would just like to acknowledge those who have worked on and managed these different trials as I'm actually presenting their work. And that's the end of my presentation. Thank you.
Thank you very much, Claire, for this very nice presentation. So there is many questions, not only from my side, so I'm trying to browse through the chat box. So of course, there is kind of, let's say, technical question about efficiency. Will you be able, please, Claire, to explain, if you completed already this kind of test, what can be the efficiency or in terms of treatment, and especially regarding pathogens of these tiger toilets?
So most of the work that we did, we've done on the effluent quality, so the effluent infiltrating into the soil, and it's actually very difficult to do that in situ. But from our first kind of systematic trial, we did get some data, and we believe that the effluent that we infiltrate into the soil is the same as the effluent from, or actually it's a better quality than the effluent from a septic tank. So we get like around about 90% COD removal. We get between like it's about average log 2 removal of E. coli. And obviously, yeah, and you have to remember that our influent is very strong. It's not mixed, it's not homogenized. So it's shit, it's urine, it's water. So it's kind of a very different beast if you're thinking about wastewater.
Mm-hmm.
Yeah, because you can see that it's not actually even mixed. You can see it inside the tanks. So yeah, we get about 90% removal of COD. With the vermicompost, we've done very few trials on the vermicompost, and we're starting to do a few more. I think we found about log 2 removal in the vermicompost. So there's still some of E. coli, so there's still a pathogenic load there, but it seems to be better than it seems to be safer than fecal sludge from the standard systems.
Okay, thank you. I'm just going to go through different questions from the natural ways that she's going to take. So basically, so you were talking about pour flush toilet, but just to make sure that about your pour flush toilet, what is the minimum volume that you need to flush such a toilet?
So
what are your recommendations?
So it depends on the water trap, because it depends on trying to create that water seal. In Myanmar, they don't have a water trap, so they use quite a small amount of water, probably about 500 milliliters. And we've also used it with a sato pan, which is a flapping system.
Mm-hmm.
And then you need a very small amount of water to create the water seal around the flap.
Okay.
But some water is needed for the worms to maintain their aerobic environment.
Okay, and then when you have so your organic matter in your system, so I assume it's going to be sensitive to overloading because you can have fluctuation in terms of frequentation of your toilet. So meaning that you can have maybe a period where you might have less people using this toilet, but you also can have, in case of events, you can have better use of this toilet. So how you can react, and meaning this goes to questions from the chat box, I think from David, about how long it takes for Earthworm, meaning to degrade the organic matter you have in a constant flow of organic matter.
So in camp settings, people are designated to use certain toilets. So we are pretty sure of the number of people that are using them. We have had issues in the past, especially in the trials with Ajit, where there were big parties. And so we got like a huge amount of material in the toilet, but slowly it does get degraded. You just have to make sure that you don't get 100% surface coverage, and then it will go anaerobic and the worms will die. But even if there's a little patch, the worms will survive.
Okay, and did you already encounter issue with, for instance, flies or such insect we can have issue? I mean, which can of course decrease the social acceptance of the system, because it seems that's a really well accepted system.
So yeah, we thought actually we would get issues with people worrying about the worms and confusing the composting worms with parasitic worms when we were talking to people, but people are much more cleverer than we give them credit for. And they're like, no, these are the worms we see all the time. So that's fine. With the flies and odors, so these are aerobic systems. The vermifilters themselves are pretty sealed. And most of them, if you have a water trap, you're not going to get any odors or flies within where the user interface, where the squat pan or the pedestal is based. So it doesn't matter what technology you have at the back, you're not going to get any smells or flies in the superstructure if it's well kept and it's clean. One of the reasons we had such high satisfaction is these are aerobic systems, so generally they don't smell because the worms maintain an aerobic environment. And the reason for very high user satisfaction in Saint-Manger was the lack of flies and odors. So we haven't really encountered that. And I think that's the same with the Jeep. One of the reasons people like these systems is that they don't smell like septic tanks.
Okay, and it doesn't matter what is the range of temperature that you can use the system. This is one of the questions we have, what can be the range of temperatures where the system can operate, let's say, in a good condition and efficiently?
So we normally say, you know, the optimum condition is 25 degrees for tiger worms. But in the trial with the Jeep, we recorded, so we had thermocouples within the systems, and we recorded temperatures of, I think, over 41 degrees, and the worms were still functioning well. At lower temperatures, they just slow down. So you just need a bigger area for the actual systems. But you can factor that into your design. And of course, if it goes below 0, then they will freeze. But we've operated in a number of different temperatures. And the other thing is, we say it's 25 degrees, but if worms in India are used to 30 degrees, they probably function well at 30 degrees. It's like lots of the literature's from temperate climates.
Yeah, absolutely. It's something also that we have mentioned in our project, INNOQUA, that of course we were afraid that when we can have really cold climates, we can have a decrease of efficiency of the system, but we just realized that if we are completing the monitoring in terms of temperature of your system, because of aerobic system, you're gonna to have an increase of the temperature within your system, which is absolute, of course, which can fluctuate with the exterior or atmosphere temperature, but which is not linked 100%, meaning that you can maintain a high temperature in your system, meaning that even if you have a freezing event or really cold temperature, you can continue having a good efficiency of your system. So I assume that the system, your system you've developed can work also in that way.
Yeah, and also your system's going to be either heated or cooled by any flush water coming in.
Definitely, definitely. Okay, another question also I just picked on the chat box. Do we need any reinoculation of the system? Because you mentioned that we need maintenance and, for instance, to empty the system once or twice a year. But do you mean that we need reinoculation of the system?
No, worms are generally, they don't like light and they don't like to be disturbed. So when you're emptying the system, they will probably burrow down. In general, in these systems, I think when I showed you a picture inside the system, you don't see the worms because they're under the waste and they feed from the bottom. So we don't re-inoculate. We had in Cochin in 2014, we had some flooding events within the system. So the camp flooded. And what we found was because worms, when they're under stress, they will lay eggs to obviously pass on their genetics. So it flooded, and then I think after about, I think it was about 2 months when the water receded, they had self-seeded themselves, so the worms hatched. So they're quite robust, the systems, and they found that as well in the systems that they use in Scandinavia in summer homes where they freeze, they just reseed.
Okay, and so it was also linked to a social acceptance questions we have. So did you, or do you have issues to find people to empty the system, and before, do you have difficulty to recruit people to find earthworms?
So for emptying the systems, it's a much pleasanter job than emptying a pit latrine or a septic tank, because this isn't buckets of people like fecal sludge shit that you have to get out. It's more of a spade system. So we haven't, there isn't so much of an issue because it's much pleasanter and it doesn't smell, the systems in general. Yeah, collecting the worms. I mean, in lots of places, like Ajit is so lucky. He lives in a worm hotspot. India, there's like worm growers everywhere. And actually Chris in South Africa as well. There's lots of worms in South Africa. So generally you can find worm farmers in countries. If not, then in Liberia, it was incredibly easy because there were lots of these worms that were around leaking septic tanks and toilets that weren't working. And yeah, we just recruited people, and people kind of collect them for fishing anyway.
Okay.
So it wasn't an issue.
Yeah, did you recommend any concentration of earthworms to put in your system according to the surface? I mean, this can be your recommendation, but in reality, do you think that these recommendations are followed, or only people just put earthworms that they can imagine good enough for installation of such a system?
So we started off recommending 2 kilograms of worms per meter squared, and a meter squared is a system that you would need for 10 people. And now we've dropped down to about 0.6 in the communal systems. Okay. In our implementation, the right weight of worms, mass of worms has been added. I think if you add a lower mass of worms, you might have to increase the surface area of the system to cope with acclimatization and the worm population's growth, to cope with the waste that's entering.
Okay, great. Thank you. And I'm just going to go through the last question about, as I told you, the natural flow. And so what happened then when you extract the worm's shit? So meaning, what did you dispose it? Do you have any other kind of secondary or tertiary treatment you use, or what did you dispose of?
So I haven't been there when they've emptied them, but the recommendation is that it's buried. Or it could be treated if you have a fecal sludge treatment plant. Okay. But we would say we have no proof that it would be safe to use as, say, like soil amendment in our systems. And also we do have a worry that we work in environments where parasitic worm infections are very high. And there is a possibility that it's accumulating within the vermicompost. We think it isn't, but that's something that we should bear in mind.
Okay, great. Thank you very much, Claire, for your presentation and for answering all these questions. I hope that I caught all the questions mentioned in the chat box. So thank you very much, Claire. And so we're going to move and give the floor to Chris Buckley. So Chris is going to present us a perspective from African views. So Chris, you can turn on your camera and your mic, and you can also start to share your screen. I will let you introduce you, but briefly, so Chris, you are a professor, chemical engineer and research in the field of urban and industrial water. You are working at University of KwaZulu-Natal, and you are at this as university head of the pollution research group. And now we can see your screen, and so you can start your presentation. And I'm happy to talk to you once again and to see you again. And thank you for your presentation.
Okay, that should be fine, I think.
It is.
So good afternoon, everyone. Thank you very much and for the invitation to speak to you today. Specifically, didn't want to take away from the message of this conference. So what might seem to be a little bit superficial is meant to be superficial. It is meant to be an add-on to what you've heard today and not to detract from it. So what I'm going to talk about very briefly is humans and the environment and environmental pollution, wastewater treatment traditionally, the circular economy, urine resources, separation, and impacts. So just to remind us why and what we're looking at, if we consider the planetary boundaries, we can see that we are beyond the boundaries in terms of biospherical integrity, and then the chemical flows, that's nitrogen and phosphorus. Those are the main planetary boundaries which we are overstepping. Remembering that, we'll continue in our journey. So the history of wastewater treatment is we started off relatively simply with activated sludge and acetylene. Then there was nitrification was added to it. Then denitrification was added to the nitrification, which is added to the acetylene. Then we needed to remove phosphorus, so we had anaerobic anoxic systems, the UCT and similar systems, and then activated sludge and acetylene. Then with the advent of requirement to remove chemicals of environmental concern, we started then having the same system with some sort of oxidation at the end. So you can see it's getting more and more complex. And this whole system of becoming more and more complex is actually moving us away from the whole concept of decentralization. So this trajectory that we're taking here is very anti-decentralization. So what we actually have to do is we must stop, think, I forgot to put that in there, stop, think, reduce, simplify, reuse. And this is where I hope that we'll be able to build on what Andreas would have told us about, because he would have told us, I'm sure, about the DWAT system. So Andreas was in South Africa 10 years or so ago, and he was very involved in the design and the construction of this DWATS plant, which is in Durban. And so it's been in operation since 2010. It treats the waste from over 80 houses. And we have, through here, we have the DWATS plant, then we have a vertical flow wetland and a horizontal flow wetland. On my left here, you see there's a growing tunnel. And then in the background, you don't see it very easily, is a whole agricultural area where agricultural trials are taking place. So the elements of this DWATS plant is that it doesn't require electricity. It is a passive treatment system, and it requires low skills to operate, and the treated wastewater goes to irrigation. Now, a DWATS plant is nothing more than a super septic tank. It probably, in fact, is, if we looked at what was being spoken about from Cranfield and Scottish Water, it is that anaerobic baffled reactor which they were talking about. Theirs was covered, ours, the gases actually do escape, but that wasn't the purpose of what we were looking at in this instance. And it removes, as going back to what Claire said, like a septic tank, 2 log removals of pathogens. It doesn't remove any nitrogen, it doesn't remove any phosphorus. It transforms protein ammonia, nitrogen into ammonia, and then through the wetlands we might have some nitrification, denitrification, and we could also, and phosphorus, there might be some uptake and some passive phosphorus removal. So the effluent from this system is suitable for irrigation, so it certainly has water with it. But and then if we move to our next slide here, we see that for 3 years we were growing bananas and taro intercropped, both of which are plants that use a lot of water. They are sort of wetland type plants. The taro in between, when the bananas have had the crop and they've been cut down, they will augment the uptake of the water and the nutrients. And we had this very well mass balanced around it. We were able to watch the flux of nutrients into the soil, and we were able to control that we didn't overwater, over irrigate, and it worked. The kind of products we produced were all products which were not eaten directly. Bananas with skin around them, and they're grown far off the ground. The irrigation was subsurface, and taro is always boiled before it's eaten. We also had people doing hydroponics, so we were growing tomatoes amongst the crops that we were growing in there, and the hydroponic tomatoes all grew well, and it all fine. Now, if we looked at the performance of the vertical flow wetland, sorry, let me go back to the hydroponics. There we see the hydroponics that were growing there, and they passed the test tastes and the growth rates. They were the topic of a PhD in plant physiology. So they grew well. Now, when we look at the performance after the vertical flow constructed wetland, what we've got here are the various parameters going down here. We've got the inlet, which is the siphon chamber, so that's the inlet to the vertical flow wetland, the effluent, the discharge limits. This is the discharge of limits to river. And you can see that the ones highlighted in yellow, that's ammonia, nitrate, and total suspended solids, were all above the limits. Total suspended solids is an artifact of how we were taking the sample, so we can discount those. So essentially the ammonia, the nitrogen, were the ones which were out of limit. The phosphorus was very close, but we don't think we'd be able to sustain it for long, for years and years. So we were a bit stymied. We were going to have to continue having irrigation of the whole flow of water, which was going to limit the places where we could put this sort of system in. You would need a large area for the agriculture. So if we can just digress slightly into high nutrient loads and nature-based systems. Let's just think about nature-based systems. Generally, I think nature-based systems scale with volume. So the greater the volume, the more area you generally require. Now, certainly within sewered areas of South Africa, about 35% of the water consumption is actually used for flushing toilets. And as we all know, what a waste. And it also adds to the pollution potential because the volume of water which has to be disposed of is that much greater. So is it possible to have factor 10 reduction in water in pedestals? Well, of course, the answer is obviously yes, otherwise I wouldn't have put it there. But factor 10 years ago or so was the in thing. We were all looking for factor 10 reduction. What would we do with factor 10 reduction? Well, Durban is certainly a water-stressed area. Most of South Africa, in fact, the whole of South Africa is a water-stressed area. So anything to reduce water demand is very good. And if we were able to reduce the water demand, we would be able to reduce the volume of contaminated wastewater, and we would be able to reduce the area required for nature-based systems. Of course, there are all the added-on aspects of being able to have water resources which would be sufficient to continue life as we know it. And I think you all have read about day zero water in Cape Town, which never actually comes, but we were getting very close to it. So how can we get this factor 10 water reduction on pedestals? Well, this is where research that was funded with funds from the Bill and Melinda Gates Foundation to an organization called EOS in Austria. They designed over the years with the assistance from Eoghan a urine separating pedestal, which removes the nutrients from the wastewater. And that has then the potential to remove the nutrients from nature-based systems. And so it also leads to the potential for nutrient reuse. So what we have is a more direct application of a circular economy relative to the linear economy. Let us just go back a bit and just think about urine and feces. And this is a pretty well-known slide that has been used many times. And in yellow, as you can imagine, is the proportion of the nutrients which report to the urine, and then in brown is what reports to the feces. So you'll see that the majority of the nitrogen, phosphorus, potassium, sulfur, boron all report to the urine. Calcium, magnesium, and iron report to the fecal material, and the pharmaceuticals, generally it's in the urine, but it depends on the kind of pharmaceutical as to whether it's in the feces or the urine. So by separating the urine from the feces, we've got the greatest volume stream. We've also got most of the nutrients, the nitrogen, phosphorus, potassium, sulfur. So how are we able to do that? Remembering that Durban currently has over 80,000 urine separating pedestals. Now, people are using these pedestals, but they're not very happy with them. They're a bit sort of, in the terminology, they're technical, they are dry, and they are actually situated away from the house. And originally people had to manage the fecal material themselves. So really with all of those sorts of aspects, you can see that they really didn't get off to a very good start. And so time has come to re-examine, can we do this better? I think the answer, of course, is yes. So this urine trap pedestal by this company, EOS, is very clever. And here we see a more advanced form of it. You've got your urine trap pedestal here. You have yellow, the urine coming in, feces. The urine goes directly out and comes as urine, the urine trap. The flush water comes in and it can go through something like an aquatron filter where you've got solids going down here and the overflow. So it's a hydrocyclone, the overflow water, which would be fecally contaminated water, would come here. So we're going to end up with a three-way split pedestal. But let's look at the pedestal itself in a little more detail. So here you see a cutaway of the pedestal. So up here is where essentially your knees would be, and the back wall would be against here. Feces would tend to drop down into where the U-bend would be. The flush water would come here. The urine would come down across this platform. It would flow down there relatively slowly, and through surface tension, it would be pulled out into this gallery here, and the urine would be separated out here. Now, depending on where people are urinating as to whether they were standing or sitting, they might be urinating primarily in the area over here or over there. That separation of urine is a variable, but across a population group is fairly consistent. So what we see in this slide here is the Laufen pedestal. Laufen is the upmarket sandware manufacturer in Switzerland, and this pedestal retails for about 1,500 euros. Now, that's a fairly negative sort of sounding piece of information. Why am I talking about the price of something when it is so expensive? Well, it's actually pretty good marketing, because what it is showing, this is not a design that is only for poor people and it's only good enough for poor people. This is a design for top of the market for those people, very few of them, who would be able to afford 1,500 euros for a toilet pedestal, which itself is a work of art. You see, looking into the pedestal, you'll see this is where the urine would be. The user would not see the urine trap, which is sort of sitting down here between the platform here and the U-bend. And so they have a variety of flushing mechanisms. So there's just a small flush of water down here and a larger flush to clear the U-bend. Now, when we're talking about a population that is unserved with sanitation, we were able to question a lot of the norms and standards. And so the EU standards and norms of a small flush at 3 liters and a big flush at 4 liters, well, that's totally ridiculous. We don't need that amount of water at all. Similarly, why do we need a 100-millimeter pipe to come out of a toilet? Because I'm sure no one has seen feces of that diameter, certainly not down a toilet like this. So one can get away with a much smaller U-bend, much smaller volume of water in the U-bend, and therefore a much lower flush volume. And there are a whole lot of other tricks which EOS has up its sleeve to reduce the water consumption. So the kind of system that is being installed now in Durban is, or planned to be installed in Durban, it flushes on about 200 milliliters for a urine flush and about 1.5 liters maximum for a fecal flush. So it uses a lot less water, and we have these concentrated streams. So let us look at a scenario that if we had this wetland system, a DWATS plus a wetland, then we could have a variety of scenarios. So we've got scenarios here, we're looking at ammonia, we're looking at nitrate, and we're looking at phosphate. And here the scenarios is there's no wetlands and no UD, so that's just a DWATS plant on its own, a septic tank. But we certainly can't discharge to a river there. A wetland with no urine diversion, no, that's what we had, we can't do that. No wetland and urine diversion, no, we can't get to discharge standards in the river there. But if we combine a wetland with a urine diversion pedestal, we would meet our discharge limits. So there you see that the coupling of the two technologies together enable us very easily to meet the river, or our particular river discharge standards. Now we've also got somewhere between well, in the particular case we're looking at, this is Banana City, where this housing for 900 dwellings is going to go in. We're looking at between 1.5 and 3.5 cubic meters of urine per day, which will be separated. So what are we going to do with the urine? Well, that opens up a whole lot of possibilities. Just to show two of them here, there's the direct agricultural use, where it could be taken away and used for urban agriculture. I mean, even at the beginning, before we know too much about the quantity and quality of the urine, it could be used for road construction sites, wherever there's been earthworks and things, you want to re-establish quickly some grass on areas so that when the rains come, you won't get wash away. You could be going through this nitrification and concentration system, which was also developed by Eoghan and it's now marketed by the company called Girona. Or we could look at the system that has been developed by Swedish Agricultural University, and it is the topic of a dissertation earlier this year. And this is with a direct application of urine on lime. So the urine gets discharged onto a bed of lime, it's allowed to evaporate, and the very high pH there will stop ammonia from being evolved, and you end up with a dry fertilizer type compound. It's based on lime, and you've got the same sort of nutrient content as you would have in commercial solid fertilizer. So we see then that by looking at the source of the wastewater, doing a rational thing of changing the pedestal, and that's especially important in areas where we're taking people with no sanitation to people with sanitation, we're able to have the toilet inside the house, can be flushing with minimal quantities of water. We end up with 2 or 3 streams of urine, feces, and flush water. We were able to take the urine and use it productively, and the fecal material and the flush water would go to the DWATS system and be managed there. So with that, I'd like to just bring us to some references and things. We see the Gold Ribbon Commission, or the Rich Earth Institute in the United States, which is promoting exactly the same idea. Border, of course, with the DWATS system, and the design for the DWATS plant is down in the bottom right-hand side. The Toilet Board Coalition, which talks about sanitation and the circular economy. We've got this dissertation from Swedish Agricultural University on safe nutrient recovery from human urine. We have our urine from Eoghan and Puna, and then we've got a number of references down there. So I think there's quite a lot to think about, how we could remove the nutrients at source and make the opportunity for nature-based solutions to be much wider and more easily achieved. Thank you very much.
Thank you, Chris, for your presentation. Yes, I think it was really interesting and to see how, of course, we need an NBS solution, but how we can also scale down our system by separating urine phases just to improve efficiency of our system, but also to make sure that we can, it can be, I mean, a way to enhance scaling up of natural-based solution system for wastewater treatment. I just have one question regarding the fact that, you know, this kind of system, this kind of pedestal can be really interesting, but only for new constructed system, or especially focused to people who have, let's say, poor sanitation solution to them. But what about already constructed system, or maybe in a urban context? I think it can have a lot of limits of installing such a system, or do you think that there is alternatives that we can work on?
Thank you for that, Jean-Baptiste. Well, if we take Paris, for example, there are certain areas of Paris which are going through redevelopment. There were industrial areas, there were car manufacturing plants, textile mills, and very old, well, sort of 1960s type technology. Those areas are going to be redeveloped. And I'm not too up to date with it, but they were very seriously thinking of going for the urine separation route there. So regeneration. I'm not suggesting that you take out your old toilet and you put in the new pedestals, but if we're looking, you know, specifically asked to talk about Africa, where the majority of people in Africa do not have sanitation,
yes.
Let's not follow the Victorian ways of doing things with 10 6-inch pipes. Let us be more circumspect, and you know, remember that the theory of disease that was prevalent when the flushing pedestal was developed was a miasmic theory of disease. In a way, we've gone back to it because we now cover our noses because we don't like the smells. Or is it COVID? I'm not sure. But so we're also sort of following that theory. But it isn't the spread of diseases from toilets by smell. It's pathogens, and therefore lots of water actually spreads the pathogens, maybe away from the person who is actually defecating, but there are people downstream that are going to receive it. So
yeah,
it makes a lot of sense to use less.
Yeah, absolutely. Useless meaning life footprint for our system, and maybe also for better efficiency in some way. But for sure, that can be a factor to increase implementation of NBS, because today it can be not considered as relevant solution in some case for wastewater treatment or for let's say sludge treatment. Okay, I have some question. Sorry, I don't know from whom, but sorry. So yeah, IPH and ammonia problem with ammonia loss. So it's a question, technical question. If you want to have a look to the chat box directly, Chris. Yeah, there's one question to know if you have already tried to coupling different kind of wetlands with the revised process you presented.
No, these wetlands were initially constructed in 2010. They had a bit of a refurbishment in about 2018, I think it was, or 2019. But they have remained the same ones. And there's an update of the design for the much bigger plant, which is going in sort of at the moment.
Okay, and I have a question regarding urine separation. So you mean that you can have co-products which can be nice for agriculture or other purposes. So do you think that from the Africa perspective, there is also a possibility to develop market opportunities by doing this separation, and so by creating new businesses which can be good for environment, of course, by reducing use of chemical products in agriculture, and also because we're going to decrease the flow for our NBS system for treatment?
Right, I think you've got two sort of parts to that question. One is it going to be used productively? The answer is yes. We've still got a number of safety questions that we are still to address. The first of it, of course, is pharmaceutical residues. And I think we have a strategy that we've developed for that, and we should be able to answer that question within within a year or so.
Yeah.
It's going to be at least a year before this Europe is available, so we have some time on our hands. The second safety hazard is the biosafety. More than just the pathogens, it could be the pathogens and antibiotic resistance challenges associated with this, with the pharmaceuticals. And I think we have a strategy there. We have to do a little bit more work before we can say that at least we've got a strategy for that. But there's a lot of monitoring we're able to do. You know, we've got time on our hands. It's one of these wicked problems. Every time you solve something, you've got another problem coming up, and you have the only way you can deal with. You can't get large quantities of urine very easily, and so now we're getting large quantities of urine. We can now work to scale and do things with that. We also have to recognize we have a very high HIV/AIDS and antimicrobial resistant TB population, and they're all taking pharmaceuticals for it. So we can't rely on other countries doing the research work on these pharmaceuticals because they're quite unique for large scale population like this. So we have to do that. We have to make sure that it's all safe, and then only then. But there are enough applications where you don't have to make food. You could go for cut plants. There are some quite high value agricultural products which are not eaten.
Okay, thank you.
And then the second part was about promoting nature-based solutions, I think. And so yes, when you've got this lighter wastewater, and you can then have a much you don't have to go to that activated sludge type process, and in fact there's no point in going to the activated sludge. Then you start opening up the opportunities for nature-based solutions. Take away the nutrients from a conventional activated sludge plant, and if it's a biological nutrient removal plant, you can reduce the footprint by 40%. So that leaves you a lot more space for nature-based solutions.
Yeah, absolutely. And regarding this point, I'm going to invite Claire and Ajit to turn on the camera and the mic, because I have a common question for you and for Chris too, meaning on the point that we have discussing, having a talk regarding the vermifiltration. So, and you also, Chris, presented quickly the DWAT system, and because we are talking about the footprint of a system, what are your views regarding maybe combining such system like the vermifiltration system or Taiwan's toilet, even if it's used with water or pour flush toilets, with the DWAT system, because probably we'll be able, because we will decrease the TSS or other parameters, but mostly TSS, will be able to decrease the surface of systems such as the DWAT system or other wetlands. What are your views regarding this potential combination and integration of systems?
Who wants to go first?
Oh, Claire, please go ahead.
Yeah, because your system comes first.
That's good.
So I think there's great potential. I was involved in a project where they were looking at using the vermi filters as basically primary treatment, as solid liquid separation, and then taking the liquid off into a small bore sewers for further treatment for the liquid phase. So I think there's great potential for coupling up these different technologies, which I think Ajit proves in his larger systems for building complexes and wastewater and fecal sludge treatment. So I'm passing over to you, Ajit.
Okay. Yeah, thanks, Claire. So yeah, definitely there is a lot of potential, especially with DWATs, I would say. In fact, our fecal sludge treatment plants are sort of a hybrid vermifiltration DWAT systems, if I can say that. There is a stage of anaerobic stabilization of the sludge that comes in, followed by solid liquid separation using vermifiltration, and then liquid again getting treated through a second stage vermifiltration. So that's how we have tried to integrate that, and final polishing using other DWATs like horizontal planted gravel filters and stuff like this. So yeah, there is a lot of scope for integrating, and also vermifiltration, I would say, on the other side, even with conventional like mechanized large scale sewage treatment plants, there is a lot of scope for handling the sludge with vermifiltration. So because that's a big issue in terms of handling the sludge coming out of sewage treatment plants. It normally ends up, you don't know where, it's so if you can actually convert it into safer compost at the site itself, I think that's a great potential as well.
Yeah, good. Thank you. What's your view regarding this, Chris?
Well, I'm very happy with vermicomposting if you're just taking it from the toilets. But if you're taking the whole household wastewater, which is what the DWATS plant is doing, we're using it as a total wastewater treatment plant, then well, we know that the first settler chamber receives, when we don't have any screening beforehand, it receives all sorts of things that it shouldn't receive. And now it all depends on how well behaved the upstream users are. But after a weekend, we find builder's rubble coming down the sewer. We find that just around Diwali time, the amount of oil, cooking oil, is immense, and there's cooking oil floating on the surface. There's, well, and so it goes on and so it goes on. But you only have to look at the head of a works, at a sewage works, to see what non-fecal material comes in. I'm not sure how your worms are going to, well, they're not going to do anything with it, but it's going to accumulate there unless you have some screening or something.
Could I just say something about restricting stuff that goes into, I would imagine small bore or small sewers. Like if you're talking about DWATS, it's transported. So you're talking about, is that right, Chris?
Yeah.
Yeah. Is there anything
right, so
you can do
at taking the water?
Yeah, but is there anything you can do at the, I mean, this is one of the things that we've done in our systems is when we use very small pipes, people don't want to block them. So you get less of all of the rubbish going down like rubble. I mean, occasionally if you've got like a direct drop, you find flip-flops, books, wallets, medication packages. But if you've got a poor flush with a very small bore, people really don't want to block the systems. So that might be something that can be worked on at the user interface level.
Yeah, and
that's fine for the pedestal, but the kitchen is where the problems come from, and there's usually a gully outside the kitchen, and so you've got a pot of rice which is all stuck to the bottom. So you scratch the rice and throw it down, and so on, and a lot of cooking oils and things like that comes down, and then more.
Yeah, so in our systems for the ones that we use for apartments and decentralized sort of housing communities, we have a sort of equalization tank where things are received in the tank itself, which has got sort of compartments inside. It doesn't have a long detention time, so it doesn't get anaerobic, but that's one stage we use. And sometimes we also have screens in the beginning to take care of plastics and stuff that might come through. And then there is a controlled discharge over the vermifilter. So that has worked for us so far. Yeah.
Yes, unfortunately, liters are wet. It can stuck the system really quickly and really easily. So that's the main issue. And for larger sewage treatment plant or larger system, of course, we need absolutely to have a screening system, which can be the issue because it can request maintenance. Sometimes it can also request energy. So that can be difficulties on such stuff. So yeah.
Even for very small decentralized systems like septic tanks, normally you'd have a grease trap.
Yeah.
I still think it's something worth looking at. You'll have a lot greater volume of water going through it. Do you allow the water to come up over the top, or does it all go through the bed?
Are you talking to Ajit for his larger systems?
Well, either of you, as you envisage, if you consider that conventional toilets, so there's toilets flushing on 6 liters of water per flush, there's a lot more water which has got to go through your vermiculture bed. And if that's only 35% of your total water flow from a house, you're going to have 3 times that going through your bed. So we're talking about probably, well, I guess we're going to be almost talking about an order of magnitude more water that's got to go through your vermiculture bed, unless you overflow it somehow.
So basically in situations where we are having the entire wastewater going through the system, like most of the INNOQUA systems, what we have is a balancing reservoir, and we have a controlled flow over the vermifilter. So there is a sort of equal flow that is spread over 8 or 10 hours. So it's never a sort of flooding event that happens. So it's a controlled flow over the bed, which actually takes the thing. So it is, of course, I mean the main. You are very right. The main area of concern is hydraulic loading rather than organic loading, in my opinion, for the vermifiltration beds, because the worms are pretty good at handling organics, but hydraulics is what you need to actually engineer properly.
Yeah. But you know, there could be ways of protecting the worms and having refuges to the side and things like that. So it's something worth looking at. It mustn't be just.
No, definitely there are. We've tried at looking at sort of arrangements where there are higher grounds for worms to go, and that has been proved quite useful actually. Yeah.
Okay, great. I think so. Thank you for this discussion. I think that we gonna to close our third session. So thank you very much for your presentation and this nice discussion. So thank you, Claire. Thank you, Edith, and thank you, Chris.
Okay. So first, just would like to acknowledge the project team here in INNOQUA Galway. It was myself and 4 of my colleagues over the space of the project itself. So as a brief reminder, just in case anyone maybe didn't join today's session, the INNOQUA system comprises a number of different technologies, which have been, I suppose, which are stitched together in various combinations depending on the particular demonstration site in question. In the Irish case, we focused on the Lumbrifilter itself, which is, we'll call it the main secondary treatment technology, and it also provides primary treatment. But other sites also incorporated Daphniafilter, for example. There was UV systems and BioSolar Purification systems. In an Irish context, the one system that definitely wouldn't work would be the BioSolar Purification system, because you'd actually need to have some sun, which in the west coast of Ireland doesn't appear very often, unfortunately. So my talk today and the demonstration sites that we covered focused on the Lumbrifilter system itself. So I'm just going to play a short section of this video. I'm not going to play it all, but I just want to show you what the site itself looked like. So just bear with me 1 second. Okay. So our site was located in Tuam, a wastewater research facility. So I'm just going to pause it there. And basically at INNOQUA Galway, a number of years ago, we built a fully functional wastewater attached to a municipal wastewater treatment plant. That the main municipal wastewater treatment plant treats for a population equivalent of just under 5,000 people. It's just a small town, about 30 kilometers north of where I'm based now. And the wastewater there comprises a mixture of storm wastewater and wastewater from residences, normal urban businesses, and then 1 or 2 specific companies that are located in that particular town. Our own demonstration site and itself, what we do is we basically take a proportion of the incoming raw wastewater and we put it through our own wastewater treatment facility, or any add-on technologies which we are testing at any given time. So this was the basis on which we were testing the INNOQUA system. We were using the primary wastewater coming into the municipal wastewater treatment plant directly from the town. We were just taking a proportion of that and pumping it into the INNOQUA system. The green tanks, which you can see here, the main large green tank that you can see in the aerial shot here, is the actual Lumbrifilter itself. And that comprised layers of gravel at the bottom, about 300 millimeters of gravel at the bottom, on top of which there was 1 meter of Sitka spruce wood chips, with generally the wood chips were sized between about 5 and 25 millimeters. And it was in that active layer that we call it that the earthworms resided. The only treatment that the wastewater received prior to the Lumbrifilter was primary settlement in a tank that was very similar to a septic tank. So I'll just play this through for a second. There's an aerial shot in a minute that just gives you a background of the site itself. So you can see just the overall area as well. The town is located kind of to the right of this aerial shot, but generally the area itself will be a very rural area itself. Our second treatment site, again, I'm just going to play just a few seconds of a video for that, was located at a dairy farm. The dairy farm is east of where I am. I'm in Galway City. It's about 30 kilometers east of where I am. And the farmer there has about 100 dairy cows. And what we were doing in that particular site was taking the wash water, which is after when the cows have been milked. Obviously they do their business in the milking chamber, but they're also washed down, as is the equipment, and that wastewater is collected in tanks underneath. And typically that particular farmer, depending on the time of the year, either spreads that on land directly, or else has to get external contractors to come in and remove that from the tanks, because there are regulations in terms of the nitrate directives and also when you can spread your wastewater on land. So this is just a few seconds, just give you an idea of the site itself. So you can see the cattle coming in a very orderly manner. And our system is just a small, I suppose, grey tank that you can see here above ground. We were directly taking wastewater from beneath the milking parlour, which you can see, and pumping it directly onto the top of the Lumbrifilter itself. And you just get a shot here of how it actually was pumped in. So it was very simple. The wastewater was pumped in above a splash plate, and we used a very simple splash plate that you can see here to actually distribute the wastewater itself. We didn't use any more complex distribution mechanism because we were worried about clogging due to the suspended solids in the system. But in fact, the splash plate worked brilliantly for the entire period that we were testing on the farm itself, and was well capable of distributing the wastewater, as you can see in the photo there, very nicely directly onto the wood chips itself. So I'll go now to the main body of the presentation itself. So just a brief reminder, the two sites I'm going to cover are the Ireland 1 and Ireland 2. And I'm just giving you some typical values of COD and BOD that occurred in the Irish 1 site, which was the dairy farm site. So you had suspended solids up to about 5,500, albeit the average was significantly lower. The highest CODs recorded were about 8,100, total nitrogen of about 250. In the municipal wastewater site, the suspended solids went up to about 320. The average was in the mid 100s. COD went up as high as 1,950, and in a bit of an anomaly, that same sample showed a higher BOD than COD, which is obviously not possible, but it gives you an indication of the, I suppose, the extreme end of the samples that we were getting in the Influent itself. Generally, the COD and BOD would have been about 500 and 300 respectively for the municipal wastewater site, but they were heavily impacted by storm water entering the municipal treatment plant, which was actually quite a challenge for us. In the municipal site, we implemented primary settlement prior to the Lumbrifilter. During our tests on the municipal site, we also looked at directly dosing raw wastewater onto the Lumbrifilter, and also we looked at various filtration mechanisms to remove suspended solids prior to dosing onto the Lumbrifilter, which I'll talk a little bit about later. So there's a little bit of background here on the Lumbrifilter technology itself. I think most people probably were in the session earlier on, so I'm sure you're probably well familiar with it, but just, in brief, basically the Lumbrifilter itself uses earthworms and microorganisms under aerobic conditions. to consume and transform dissolved and solid organic matter in wastewater. It's particularly targeted at removal or oxidation of ammonium and also organic carbon and removal of suspended solids. Obviously, the wood chips themselves provide a very important filtration mechanism, and you have bacteria which grow in the system as they would in any, I suppose, such type of system. And you also have the action of the earthworms themselves. So our initial work at NUI Galway looked at laboratory scale filters. It's always good to work with laboratory scale filters because you can do a lot more specific tests on these systems. And the idea was to look at a variety of issues from everything from the earthworm species that we would use in the system, the height of the active layer, hydraulic and organic loading rates, the impact of household detergents, etc., etc. So you can see maybe just some of the photos of the columns in the lab. You can see some pictures of worms in the filters themselves. And we tried to, I suppose, cover as many different scenarios to help us optimize the system as would be possible. We did, over the course of that study, also leave 3 of the filters operate without any change for a period of 180 days. So in general, in our laboratory work for the past 3.5 years, we've been making various changes to the systems, but we left 3 systems operate, and these were replicates with 1,000 millimeter active layer for 180 days without any changes. Those systems were dosed with municipal wastewater, which we brought in directly from site into the lab, and it was directly dosed onto the system. So the following 2 slides are just going to give you some of our ideas to the types of results that we got in the laboratory filter. So you can see that there was over that period of time very high removal rates of COD, suspended solids, ammonium. We didn't typically measure BOD in the lab simply because we take samples quite frequently and COD is easier to measure. But the high ammonium removal rates there and the high nitrification rates, which we measured in site, would indicate that BOD levels would have had to have been very low in general. You can see also that there was very little deviation in performance throughout the 180 days. The types of hydraulic loading rates we had, were about 474 litres per metre square per day and 474 litres per metre cubed per day, given a 1,000 millimetre active layer. The initial worm density was just over 6,500, albeit it was hard to check that thereafter, worms per meters cubed. And these systems operated at 10 degrees Celsius was the room operating temperature consistently. You can see here very high consistent levels of COD and also really very high and excellent removals of ammonium in the Lumbrifiltration system using municipal wastewater over that entire period of time, after the initial approximately 35 to 40 day startup period that it took for nitrification to kick in. So obviously development of biofilm. I'm not going to focus too long on the laboratory studies, but one of the interesting things that we did do was we ran a control column against that particular Lumbrifilter. The control column was the exact same in design and received the exact same loading rate, except for it did not have worms. So the only difference between that and the other columns were there was no worms. In terms of organic carbon removal and suspended solids removal, it performed equally when compared to the Lumbrifilter. However, it did not manage to last the entire 180-day trial, as it clogged after about 90 days. And the second area where performance dropped compared to the Lumbrifilter system was with regard to ammonium removal, which was significantly lower than in the Lumbrifilter system and is possibly related to the earthworms creating passages within the system, allowing air to dissolve or to move through the system, and also related to the lack of clogging that would have occurred in the Lumbrifilter column. So other things, I suppose, within normal household detergent usage, we found that the earthworms were not impacted. We had to go well beyond what you would consider normal household detergent to have a significant impact on the earthworms. And we found, I guess, that the active layer height of about 1,000 millimeters was optimal for the system. We compared 2 earthworm types. I'm not specifically an expert myself in earthworms, so I won't be able to tell you the exact difference between them. The reason we did the comparison is that tiger worms, which are, I suppose, the common name for the earthworm type that is generally used in Lumbrifilter systems, are not readily available in Ireland. So we used night crawler worms, which is a common earthworm type available in Ireland. We found there was no difference in performance between the two. So moving on from that to maybe the large scale demonstrations, we had two sites, as I mentioned before, the agricultural demonstration site, and we had a municipal demonstration site. So I'm just going to talk about the agricultural demonstration site. And just to note that everything that you kind of see below the ground level, which is marked, is existing infrastructure that was on the farm itself. And what's above it is what we installed. So simply, we were pumping from a holding tank underneath the dairy parlour into a holding tank above ground. And from there, we directly pumped from that holding tank onto the Lumbrifilter. So there was no additional primary or preliminary treatment. The initial holding tank that we pumped into provided very little primary settlement because the residence time there was very low. So the quality of the wastewater entering the Lumbrifilter was almost the same as that which was pumped out of the dairy parlour system itself. This is just the results here. Obviously, we have a lot more detail behind this, and I'm sure we're finalising our technical reports, but they will all be available in the coming weeks. But I'm happy to discuss any of that in more detail. But the overall removal capacity of the system was actually a lot more positive than I would have expected, given that the organic and suspended solids loading rates to the system were quite high. Our hydraulic loading rate was about 0.2 meters cubed per day, which is approximately equivalent to maybe 100 litres per metre squared per day in surface area. But when you account for the high organic loads and the high suspended solids loads to the system, you can see that the organic and suspended solids loads would have been extremely high. So we got very good removals of suspended solids and COD, and indeed total nitrogen as well, mostly somewhat due to nitrification, because we did measure nitrification in the system itself, and also due to physical filtration and other mechanisms. This is probably a key result in this particular context, is the removal of nitrogen, because in this context, this farmer would have been limited in terms of how much wash water he could spray on land because of the nitrogen content of it. Hydraulically, he wasn't limited, but he was limited because of nitrogen. So obviously, being able to remove nitrogen in this scenario was helpful. In a practical application or a larger application of this, what would likely happen is that you would simply discharge the wastewater from the Lumbrifilter back into the holding tank, the net effect being to reduce the overall nitrogen concentrations in the holding tanks and make it more amenable to be spread on land. The municipal demonstration site, I've just shown you, I suppose from the short video, you'll have seen an appreciation of it before. As I mentioned, it was based at a municipal wastewater treatment plant, whereby we were taking a direct feed of raw municipal wastewater from the inlet of the main treatment plant, and we were distributing that into our Lumbrifilter system, which you can see as the large green tank. Prior to that, we had a septic tank-like system, a 2-chamber primary settlement tank into which the wastewater flowed. We also tried pumping raw wastewater onto the system, and we also tried the use of a variety of physical filtration mechanisms prior to the system to remove suspended solids. I'll just comment on those two aspects. First, the use of physical filtration is not something, I suppose, that we would normally have tried because of all the issues that go with that, and not surprisingly, very quickly, the use of kind of barrier mechanisms, so whether sock filters or metal strains, etc., they quickly became clogged, and obviously for small applications that would not be an ideal scenario. Pumping raw wastewater onto the system worked pretty well. The only, I suppose, the biggest drawback of that in our case was that we were in a municipal treatment plant, and basically anything that came into the municipal treatment plant we were likely to get, which you would normally not expect to get in a smaller domestic scenario. So as anyone who works in a municipal treatment plant knows, anything that can fit down a toilet will be flushed down or has been flushed down. And so we got all sorts of exotic things coming in. And the second disadvantage is that you do have to substantially reduce the hydraulic loading rate in order to ensure that the system does not clog. So after trialing those two, we went for a more traditional setup where we had primary settlement akin to a septic tank before the Lumbrifilter. And they are the results that I will talk about. Just to give you an idea of the range of these results, it's over about a 540-day average up to about the end of September. The results are just from the Lumbrifilter technology. The temperature range for the water was between 5 degrees Celsius up to 20. There was just 1 or 2 days where the water temperature went above 13 degrees and suddenly went up to 20. It must have been some external discharge from industry or something, but in general, it ranged between about 5 and 13 degrees. Air temperature between about -5 degrees, which you would have seen quite often, up to a one-off temperature of 26. In general, the maximum temperatures would have been about 19 during the summer or 20. Rainfall is relevant in this site because it's the system in that town is a combined sewer, so relatively it would be quite consistent rainfall throughout the year, ranging from about 1,200 to 1,400 millimeters per year. The dosing rate was just under 500 liters per meter square per day, so about 1.45 meters cubed per day. We started with an initial worm density of about 5,000 worms per meter cubed, and the overall cost of operation for our system was about 30 to 35 euros per annum in electricity. So the only device we had was a pump to pump from the primary settlement tank into the Lumbrifilter itself. In fact, that pump was oversized simply because because we're dosing intermittently, so once every hour, and that's a key consideration, which means that the flow rates can be quite low. So we had to throttle back against that particular pump again. So the energy costs will be somewhat inflated by that. So the average percentage removals. So these are percentage removals that are given here, I should state. So the average percentage removals for COD were 75, BOD 92%, total nitrogen 46%, ammonium 80% through the Lumbrifilter. The effluent concentrations for COD were 121, for BOD 21, and for ammonium just under 8. The COD in this particular case, and this is an issue that we see in this particular, the main municipal treatment plant in this town, is that they have quite a high level of soluble recalcitrant COD entering the plant itself. So the main effluent from the main municipal treatment plant would have had similar issues. I've just given you an idea of the surface removal rates. You can see here in terms of grams per meter squared per day. In terms of maintenance in this system, we topped up the wood chip over the 539 days. We've topped it up twice. Now we do need to top it up, and in fact, had we topped it up during the summer, but unfortunately because of COVID restrictions we couldn't. And during the autumn, in fact, we still have been restricted with travel. I am pretty certain that these, particularly the BOD and the suspended solids in particular, would have been a lot lower. They were impacted by 3 or 4 outlier values that occurred from very high influent concentrations. We carried out no other maintenance on the system. We had no clogging. We didn't rake the system. We did absolutely nothing else to the system throughout the whole period except for top up the wood chip. So I suppose some key conclusions after 500 plus days. At the start of the project, we were working with an active layer height of 1400 millimeters, but found that reducing that to 1000 millimeters did not negatively impact performance. In terms of worm populations, of course, it's very difficult out in sight to count how many worms are in the system, but it is very easy to see whether they're active. Generally, when you open the system, and if it's just after dosing, you will see the presence of worms in the system, or if you ruffle around the top layer, you will see them just underneath. And throughout the whole period on both sites, that was present. In terms of primary treatment, we deployed primary treatment on the municipal site, and that is when the site was at its most effective in terms of trading off between the fact that you have primary settlement in place, which does require desludging periodically, versus the higher loading rates that we could achieve on the Lumbrifilter. In terms of shock hydraulic loading, at site loading rates up to 150% of design loading rates over extended periods, the system worked fine without any disimprovement of performance. Where we did see disimprovement of performance was on a number of particular days due to excess rainfall and issues like that, we did have to overload our system by about 500 or 600%, and that resulted in I suppose, leaching of suspended solids through the system, which actually negatively impacted some of the results that you would have seen there. Again, I would suggest that in a domestic or very small scale situation, that would probably not be an issue, because you wouldn't expect to see such accumulations of stormwater. Wastewater distribution, we found that we used a splash plate at the top of the system. You saw an example of that for the agricultural system. To be honest, I wouldn't even try another type of distribution system, because the splash plate on both sides work brilliantly. There's no issues with clogging. We found distribution was very good, but it is key, whatever way you go, that you do have good distribution at the top of the system. Ease of access to the Lumbrifilter for inspection should be included. So the fact that you can maybe open the top of the tank quite easily if you do need to rake it. Top up of the system is likely to be needed on maybe a 6 monthly basis, although we have kind of stressed it and let it go quite a bit longer than that. In general, you're looking at, if you're to do it every 6 months, approximately 100 millimeters of wood chip would need to be added every 6 months, maybe 150. In both studies, in the results, the period of the results that I have shown you for both studies, we had no clogging in the system at all over the entire period. So we never had an occasion where there was water pooling outside of the dosing periods. So basically, by the time the next dosing period came up, any of the water at the surface had long gone at that stage. So it wasn't an issue during our studies. So just a couple of, this is just the last slide, a couple of other observations. I hope I haven't gone on too long. Occasional raking may be necessary at the top of the Lumbrifilter. Particularly in a municipal site, we abandoned it after a couple of months because we felt we didn't need it. We found it to be very robust. We didn't notice any disimprovement in performance during the winter months, apart from for ammonium, where there was a slight reduction in our slight increase in effluent ammonium concentrations of maybe 1 or 2 milligrams per litre. And just in general, in long periods, if you do have long periods where you have low wastewater volumes entering the system, or for example, if it's operating in a tourist resort where you may have during the winter time no wastewater entering the system, it's likely there will be more than enough organic matter in the system to sustain most of the earthworm population, but you may need to maintain some level of hydraulic dosing just to make sure that the system is moist, and it also helps it not to overheat. So that's basically it for my slides. And again, I think you've seen this earlier anyway, a list of the various demonstration sites. So at this stage, I'll hand maybe straight over to my colleagues in Scotland, and we might take the questions at the end, and I'll also look at the chat while they're talking. So I believe Anna or Tamsin is presenting next.
Yes, thanks, Ewan. I'll be presenting our site. So just let me. Hopefully you can see it now.
I'll be here to help with questions though as well. But Anna's presenting this one.
Okay, so my name is Anna Barron. I'm project manager at the research and innovation team in Scottish Water. And the aim of this presentation is to give you a little bit more details about our demonstrator site in Little Mill, and also give you a small site visit virtually. Our demonstrator site was located at Little Mill village in Scottish Highlands. It includes only about 16 houses. The number of population varies, as some of the houses in the area are holiday homes, so it varies depending on the season. Also, the COVID situation also impacted the number of people in the village. So I mentioned that because that was one of our main challenges in terms of the influent concentration coming into the existing wastewater treatment. The existing wastewater treatment at Little Mill is actually a septic tank. So the Little Mill village is, as I mentioned, is located in the north of Scotland and in a rural area. And we that was the reason behind selecting this site for testing the INNOQUA system, as that would be the kind of system that we would potentially apply in this kind of conditions. So this is the existing wastewater treatment works. You can see the you can't really see much, but it's basically just the inlet channel with settlement chamber and then just the main chamber of the treatment. There is some plastic media inside the chamber, but there's no aeration working on the side, so it's effectively a septic tank. North of Scotland has many of the this type of small wastewater treatment works, often septic tanks. And as if you were at the previous talk that Tamsin mentioned, Scottish Water's strategic objective, one of them is to provide sustainable treatment in the rural area, and INNOQUA system could play a very crucial part in that to deliver decentralized sustainable treatment. So that also was the point behind selecting this site for the testing of INNOQUA. So the existing wastewater treatment works, the sludge is removed from the site about 1 to 2 times a year. And I mentioned this in terms of in the context of sustainability, because with many of those sites in the north of Scotland, small sites, the number of trips that those tankers have to make a year, it's a significant cost and also carbon footprint for Scottish Water. So any technology that could reduce the number of trips and also the additional loading of treatment for bigger sites in the area, that would be definitely a benefit for Scottish Water for achieving its objectives. Our demonstrator site was included the Lumbrifilter and Daphniafilter, and it was installed on a platform. And the reason for that was that Little Mill was a testing site. It's not the permanent location for the INNOQUA system, and we wanted to make it as mobile as possible, so we can take after the testing period, we can take it away for once we find a more permanent site for the technology. For that reason, also the tanks required external insulation, but we thought that would be the best way to test the system and use the system in the future as well, so we can easily move it as required. So that's the real installation of the INNOQUA system at Little Mill. You can see in the bottom left corner, that's the flow intake from the existing settlement chamber, pumped to the Lumbrifilter and then pumped again from the small balancing tank to the Daphniafilter. Unfortunately, during the testing period, which lasted about a year, we tried to inoculate the Daphniafilter twice, but the Daphnia population did not develop. So effectively, our site also was a Lumbrifilter site only. So you can see the existing settlement chamber and the intake from the settlement chamber to the Lumbrifilter. We also use the splash plate distribution to the top of the Lumbrifilter, and yeah, there were no issues with that, and it worked very well. As I mentioned, we tested our site from October 2019 to end of September, beginning of October this year, with almost 3 months shutdown for the COVID shutdown. So there was a period of no flow going into the system. We, as I mentioned before, the influent concentration were quite low going into the system, but we achieved quite good average removal of BOD and good removal of suspended solids. Here a little bit more details on that. So our active layer was a meter high, and our average influent to the Lumbrifilter was just above 1.1 cubic meters a day. The temperatures of the influent was on average about 8 degrees. We experienced temperatures as low as just above 0 degrees, and the highest influent temperature we experienced on site was just above 16 degrees. After, as you can see on the graphs, after the sort of initial startup period, when we had some issues, also some issues with mechanical with pumping of the influent to the Lumbrifilter, we achieved quite a good performance, especially for the BOD removal. Following the shutdown for COVID, we and the inflow to the Lumbrifilter was stopped completely. So there was also a little bit of a period of a startup, and then we started showing a strong performance after that as well. And we added, after the shutdown for COVID, we added earthworms to the Lumbrifilter. There was still, following the initial visit, there was still earthworms there. However, we judged that there were not sufficient numbers to continue the treatment, so we added additional batch of earthworms after the shutdown period. I'm going to show you a brief video from the site. So basically just a site walkover. So that's give you an idea of our demonstration. Let me just give you. So as you saw at the on the video, yeah, luckily we didn't have to experience the rain. So we carried out regular visits. We aimed for weekly visits, and the video is from one of the weekly maintenance visits, and the top of the Lumbrifilter was raked at pretty much at each of the visits. So the top of the Lumbrifilter you saw there was just after it was raked, so it was quite I guess well mixed, and we found that the weekly visits were quite beneficial, and if the visit, the time between the visits was longer, then there were quite a lot of weeds starting to grow on top of the Lumbrifilter. So I guess that there was maybe slightly different experience than in Ireland. We didn't leave the Lumbrifilter unattended more than maybe 3 weeks at the time. So that's yeah, that's more or less our experience at Little Mill, and let us know if you have any questions. Thank you.
Thanks very much, Anna. So yeah, it is interesting actually to see the issue with the weeds that she had, and I wonder is it maybe partly to do with the location as well, yes, just physically where ours was maybe compared to yours. Was yours covered as well? I can't remember.
Yes, it was covered. So this was only uncovered to take the video, but it was uncovered. Following the shutdown, the first visit after we did after the shutdown, the tomatoes were over 0.5 meter high, growing up through the cover. So it was quite significant weeds overgrow. But yeah, okay. I think that so I guess to do with the site. Yeah. Sorry, go ahead.
Yeah, no problem. So yeah, I guess that was just to give you an overview, an idea of 2 different sites, and maybe the experiences we had with the technology and the system on the 2 sites. For the rest of the session, we're happy to take any questions where we can do it via the chat, or happy if people want to come on the mic as well, that's absolutely okay. Just a question that came from Johnny Tyler was with regard to the use of septic tanks and the sizing of them, and etc. So I have maybe put an answer, as of others, on the chat itself. Just one thing I would say on that is that at least in an Irish context, we sized our primary treatment based on septic tank requirements in an Irish context for a typical household. Could you operate without a septic tank? You could, certainly. Obviously, if you keep an eye on the organic and solids loading rates. I suppose one of the issues you have to consider as well is that these systems are dosed intermittently in general. And so you may need some sort of hydraulic buffer. But if your site characteristics are favorable, then it is possible to operate without a septic tank. And I think the agricultural site, in a way, as there are other sites, but the agricultural site can demonstrate that because of the level of solids influent in that particular case. And we didn't really see any significant issues with clogging, etc. And that would be far in excess of what you'd expect from a septic tank. I guess in an Irish context, currently anyway, if you're developing a small or a single house wastewater treatment system, you do have to have a minimum level of primary settlement in those systems. So that's, I suppose, what we were looking at in that context. The venting arrangements in the tanks. In our case, we just had two 4-inch vents, basically. So one was located at the top and one was located at the bottom of the reactor in the drainage layer, but just above, just in the middle of the drainage layer. That's all the ventilation we had. So 100 millimeter, sorry, I should say 2 by 100 millimeter vents, and we just did those using normal sewage piping. We didn't have any other type of ventilation at the top. In our case, the reactor was sealed, albeit you could open it. There was a hatch at the top that you could open, but other than those vents, we didn't have any other venting arrangement in the system. I'm not sure in Scotland, yours would have been quite similar as well in that case for venting.
Yes, yeah, pretty much the same. So it we had 4 vents from coming out from the bottom of the sort of the active layer. So, but yeah, that's pretty much the same.
So I think the next question, if you can look at the chat, is directed to Anna or Tamsin, and I'll come in afterwards because we also tried it in Ireland, but I didn't mention that, so I can come in on that as well at the end.
Anna, do you want to take the first part and I'll take the second part?
Yep. So the first time we inoculated the Daphniafilter, I think that was at the start when we started testing the site. So that would have been, I think, November or I think November last year. So at that time, I think the temperature was too low for the Daphnia to survive. We wanted to give it a try anyway. The second time we added Daphnia, I think from memory it was the summer, I think August this year. And so the temperature was definitely suitable at that time. However, discussing this with Victoria from Girona University, I think levels of COD coming off the Lumbrifilter going to the Daphniafilter might have been too high for the Daphniafilter for the Daphnia to develop, but we are not 100% clear on the reasons why they did not develop. But Tamsin, you may add to that, I guess.
Yeah, so as I alluded to in my presentation, we're keen to look into options for what we can do to further our research into Lumbrifilters. So in terms of our septic tank alternatives, because that's really what we want to look into. With having such a high base of them in Scotland, it's prudent for us to go out there and see what the alternatives are. So if we go ahead with INNOQUA, another site, we're going to have to look at all these issues and decide which bits are going to work for us and which bits we want to try, and the Daphnia may or may not make it into that cut, because like was said earlier, we don't want to kind of grow up all these water fleas if we think they're going to be killed off, but if there is some benefit. So part of any future projects would be looking at the Daphnia, would be looking at other options, filters or settling tanks and things like that, and actually playing around with the setup in INNOQUA to see what works for us and what we could potentially improve on for wherever we put it. So hopefully INNOQUA won't mind too much if we kind of get a bit creative, but we really need to find kind of what works in the Scottish context, which is really quite different, and also the context of what sewage we've got coming in, because as Anna said, at Little Mill that was foul only. It might be wherever we go to next, it might be a combined septic tank. So then we've got to look at what we're going to do there and kind of the different options. So it's exciting times to see what we can develop, and it's kind of all on the table at the moment. So well, I'm sure through sort of different forms you'll be able to find out what we do next.
Thanks. We actually tried as well the Daphniafilter in Ireland, and I think there was maybe a number of issues. One was temperature, albeit Daphnia are in the environment around us, so in the aquatic environment around us, so they should be, you know, to a certain extent adapted to that. I think as well though, there is the issue over the consistency of the effluent during startup, and they are quite susceptible if you combine lower temperatures with not bad quality effluent, but organic carbon levels that might be, you know, around 15, 20, and you have maybe ammonium. We found if you have ammonium kind of levels of 5, 6, 7, which normally they could easily tolerate. Perhaps in the scenario where you have lower temperatures, those two things combined can be an issue. In our site, we also had problems with a couple of large, I suppose, storm events that we had to kind of put through the system, which didn't help us. There was a second question there, just in relation to municipal wastewater treatment and being quite homogeneous. Yes, albeit the day-to-day variation in our treatment plant is quite high. It depends on rainfall, so it varies very considerably. But yes, I take the point. However, we did in Ireland, we did test the ability of the earthworms to withstand household detergents and strong detergents. What we did basically was we looked at what one might consider to be average detergent use, and we applied that to the filters for a period of time. Then we doubled it, trebled it, and it was at the stage where we trebled it that we started to know a drop off in performance. So at that stage we stopped the experiment. We actually counted the worms before the experiment and afterwards, and we didn't, at least from visibly, all the worms were active and alive afterwards at that particular dosing rate, but we could see there was some drop off in performance. And also you could see quite clearly they were not moving. When we would go into the lab in the morning, you could actually see earthworms at the outside of the reactor, and they would quickly move into the center of the system, because we used a Perspex system at the very high dosing rates for leaches, which would be really, you're talking about having to put down, you know, your toilet, a couple of bottles of Domestos all at once. You know, it would be something that shouldn't really be happening anyway. It was only then that we kind of, what we used to see when we go into the lab is that the earthworms would no longer start to move quickly into the center of the system. So at that stage we kind of called a halt, because we felt that they were being negatively impacted. So I think for day-to-day normal operation of normal household operation, it should not be an issue at all. And they seem to be thriving actually in the environment.
Yeah, just to come in there, so going back to my earlier point about community engagement, so that's why it's kind of important to do a lot of work with the community before you install these, so then you can have those conversations about, did you realize that if you put paint thinner down your toilet, then you might actually kill the downstream asset. I know Anna did a lot of work before we even went onto site, talking to the local community and kind of raising these issues. Didn't you, Anna?
Yeah. Mm-hmm.
So questions probably directed to me, the dairy project, Tony. No, actually the active layer in that, so the active layer in the tank was only 1 meter cubed of wood chips. That's all that was in that tank. If there's a additional, the tank wasn't 7 cubes, it was smaller, but we had additional headway just in case we wanted to mess around with the active layer height, etc. Because I suppose for research purposes, it's nice to give yourself extra room. But the active layer itself was a meter high, and it was a meter, well, it wasn't exactly a meter high, it was a bit less, but it was a total of 1 meters cubed of wood chip in the system. And underneath that, there was about 300 millimeters of gravel. So the gravel just, I suppose, acting as a drainage layer probably wasn't acting as in terms of treatment to any great extent. But I would say as well that the earthworm population there was, I mean, visibly higher than in the municipal system after a period of time. Maybe, I don't know, the type of wastewater. As I said, I'm not an earthworm expert myself, specifically in the area of earthworms, but it appeared as if we had a lot more earthworms per unit volume in the agricultural system compared to the municipal system. And maybe the type of influence, the nature of the organic material, etc., was more conducive to them. I don't know. But I just finished by saying it is an issue definitely for a dairy treatment plant. If you can expect about 50 litres per cow per day or something akin to that coming off, certainly size, you know, is an issue. I suppose one might say hopefully in a farm application the size may be available, but it is something that you would have to consider definitely. There's a question from Theo there, which might be more relevant to Anna or Tamsin.
Yep, so and Anna can answer for the full INNOQUA project perhaps, but from our point of view, we've only done the community engagement exactly where the INNOQUA pilot went, so in that community, but we have an ongoing piece of work kind of all nature-based systems in Scotland to gauge opinion. And that would include things like the worms and the fleas, and hopefully insects like flies. I'm quite keen on getting some black soldier flies into sludge treatment, but we'll see how that goes. That might be a step too far, but so at the moment we're very much looking at the general issues rather than focusing on one technology over the other, because I think regardless of the technologies, there's probably some general themes around how much the community is willing to get involved, how much they want to see or not see of what's going on. And then there's also this land issue as well, because a lot of the time nature-based systems take over kind of bigger areas of land, and as a utility, we don't really want to get into land ownership and own kind of masses of land across Scotland. So there might be kind of community ownership of the actual sites involved in that too. Anna, was there any work in the INNOQUA project for community?
No, it was project specific. So we site specific. I guess we carried out the community engagement for our site, and the people from the Little Mill village, they were very keen, and they were in terms of trying to learn what it's all about and what it does and everything. I guess the objective initially was that the community would be more involved in maybe even looking after the plant, or maybe that's the ideal way forward. But from our point of view, where the testing site was, because it's existing wastewater treatment work site, that would be, we can obviously discuss it with the residents and invite them to visit, but it would have to be specifically agreed and some arrangements in place that it's community owned, because obviously there would be no access to site where it was for the testing itself. So obviously there is much more work to be done for the community to be more involved, even though they were very keen. Yeah.
Okay, just looking at, do you see any, from Jeff, do you see a limit to the depth of wood chips you could use for this? We do see this point, something that looks like a big, yeah, it's interesting. We at the start of the overall project, the idea was to use a 1.4 meter high active layer, so 1.4 meters depth of wood chips. This was going to cause quite a lot of problems in terms of the overall tank size, particularly height, and actually not just in terms of, I suppose, application in, for example, Ireland or Scotland or places like that, but also we were moving tanks out of the EU to South America, and there were issues over fitting them on, you know, various types of containers, etc. So first part of the project, we looked at different active layer heights from 0.7 meters to 1.4 meters. And we found that from between 1 meter and 1.4 meters, there was no drop off in performance of any parameter that we measured in the system over a period of about, I think 100 days we ran that trial. I can't remember exactly, but approximately that. At about 0.7 meters, we noticed a significant drop off of most parameters, but particularly suspended solids, and obviously that knocks onto organic carbon, but also nitrification. So that's where we went with the 1 meter. I guess there's no limit to the height. It's more, it's I suppose it's an engineering issue, a commercial issue as well.
Yeah, there's a community there, a question on community ownership. Would community ownership involve the community managing the system and Scottish Water pay the community for the service? That's really interesting. So community ownership, it could be. So I don't think there's any decisions made as yet which way to go, but you know, going forward, we could move to a more community managed system where these systems are set up to be low maintenance anyway. And perhaps, you know, as they're using it for amenity as well as treatment, if they notice something is amiss with the system, they call in and we come and check, or perhaps they can perform some maintenance. Who knows? It's open at the moment. I would hope that we would move to some more collaborative, integrated system going forward, because that's better for the people that live there. They're not having, you know, Scottish Water employees coming in all the time. It's better for the environment. We're not driving all over Scotland. So I think there are definite benefits, but obviously there's a lot, as Anna was saying, there's a lot of health and safety issues and things like that that need to be balanced out by whatever you design. The second question, would Scottish Water be proposing to pay for the community? It's not out of the realm of possibility. Everything's an option. I would say that at the moment, if you are on a private supply for wastewater, then you don't pay wastewater charges. So there can be, I guess there's probably flexibility in that, but that's up to bigger people than me to come out and say that. But I think all these options are on the table if we're going to design a flexible and adaptable system going forward for our wastewater.
And I think there might be another question relevant to you again, Anna and Tamsin, from Paul Usher, if you can see it there.
I can, so definitely in terms of our experience, people in Scotland definitely care and know much more about the water supplies than wastewater. So wastewater is out of sight, out of mind. So and maybe that's due to the I guess good coverage of the collection system. So that would be part of the next step, I guess, in getting people interested and involved and understanding what's happening with the wastewater. So yeah, definitely that's a potential.
So what we've seen is that our customers want a great quality treatment systems that protect the environment at a reasonable and affordable price. So those are kind of the yardsticks we're measured on, and luckily we do a pretty good job up here in Scotland with those at the moment. So I don't see, there's not been any major research that I've seen that says they want to go off mains. However, in our more sustainable future, everyone's getting solar panels and doing all that kind of thing. I definitely think there is scope for more grey water systems and source treatment and things like that for the communities that want it.
I might just add to that, because recently in Ireland, our national regulator, environmental regulator, released its annual state of, I suppose, wastewater treatment in Ireland, and obviously raised some issues, as would be the case. But one of the interesting things, as responses from our national utility, Irish Water, was with regard to some delays in the development of wastewater treatment plants in some areas, or upgrades to wastewater treatment plants. And one of their sides of the equation was that in terms of getting planning permission and approval for wastewater treatment plants, that it can be extremely difficult due to public objections. So everyone wants wastewater to be treated, but no one wants it treated near them. And I think I'm just posing this, that maybe there's an interesting dichotomy, at least in Ireland, because in our water supply system, if you live in rural areas, you may be on a private scheme, in which case you will pay for your water supply and the upkeep of that supply. If you're on a public scheme, we do not pay at all here in Ireland. And I think something similar maybe can happen in a wastewater context, that people who have to manage or maintain their own wastewater treatment systems are much more aware of them and less afraid of them, etc. Whereas when you don't, or historically haven't had to do that, then the thought of a wastewater treatment plant near you is horrible, even though you still want to bathe in the in the sea that the wastewater or that the sewage is currently flowing into. So it's an interesting issue, I think, anyway, as to how to, particularly in the area of wastewaters, how to get community buy-in that these are really essential services.
So I think the floor is open now for everybody, and you can switch on your video and your mic and start talking.
Absolutely. I think, yeah, you're right. It was absolutely a good event. A lot of discussions, a lot of questions, especially on the first session. So that was nice. I hope that we'll be able to continue discuss and present maybe different question we have had. But at least, this kind of conference can allow us to compare the different views from different parts of the world regarding NBS, what can be the issue or barriers for implementing more and more NBS solution, and how we can, in a certain way, address the issue of wastewater treatment, and another way, maybe it can't. So that's really important also to see that, yeah, it doesn't work for any purposes. So, but it was pretty nice to discuss, yeah.
Yeah, so it was unfortunate that Andreas had an emergency and couldn't join, as I was hoping he'd give a lot of background about DWATs. But you very nicely, Jean-Baptiste, you made the connection between DWATs and vermifiltration. So, yeah, understanding how those links might be made is interesting.
I think there was many things to do, because as we have pointed out during this talks, is that we have issues about the footprint. We have issue regarding the volume that we have to treat. We have issue regarding efficiency in certain ways. So that's really important to integrate and combine, because if they have kind of combined efficiency, we can have a good efficiency at the outlet of the system, which can be quite good. I mean, for at least proof that the NBS solution can work very well.
You want to say something, Chris?
Yeah. Fundamentally, a DWAT system is a solids retaining system, and the rate of the DWAT system is the rate of hydrolysis of the solids, and that's what it all is. Your desludging time is a function of how much sludge can you hold, and when it fills up, it's time to desludge. And so, if we can then use the attributes of worms to reduce that solids load, we would probably go for very, very much longer without desludging, and the whole DWATS plant could be much smaller, because you're not rate limited by the rate of hydrolysis, because you're now only dealing with the soluble material. So I think the whole DWATS plant could in fact be very, very much smaller.
I was just
so that's something to bear in mind, Claire.
Yeah, I was wondering where biogas fits into this equation, because of course various of these technologies are great at degrading biological solids. That's what they do. But those volatile solids are also potentially biogas. So could you, for example, have DWATs with a household biogas, and then the final effluent after those processes that goes through vermifiltration or through something else? There are so many different bits of the puzzle that you can connect in different ways. I don't know if there's ever an optimum for all of these combinations, or whether it's all site specific.
I haven't done the I haven't done the sums on it, but the amount of biogas produced is generally a sort of a ratio of 10 households wastewater is needed to be able to supply one household with biogas. So the social issues as to who gets the gas and all of that sort of stuff is just, our people are just not interested in it. Right. Let's rather solve the problem of sanitation. Let's worry about, and you're saving electricity, you're saving so many other things, the health and all of that. Let's not worry about those tertiary things.
Okay.
Claire?
I was just going to say that there has been some organisations that have linked worms with biogas. So Luwot did it in Madagascar. So they had a it was like a public toilet. So it took and it was a dry toilet. So it took fresh human waste and co-digested it with municipal solids, so food waste, and then the digestate came out, and then that was vermicomposted into a product. And I think Ajit's using anaerobic digestion in some way in his systems anyway. So yeah.
Yeah, again, if you just like Claire and that, if you're talking about large-scale digesters, you're looking at a digestate to treat. Let the digesters take the gas and deal with that conventional technology. But then you're on the back end with the digestates, but then you've got high ammonias and that. And as we've seen just through the earlier demonstrations of the farm over in Ireland, they can take so much ammonia. But again, you've got to properly design that, because like any living organism, it doesn't like a huge amount of it at any one time.
I did have a sneaky little question in the chat box for you, Chris, which was about it was a question that came up earlier in the day, and it's almost kind of reverse knowledge transfer. So we here in the privileged Northern Hemisphere are responsible for most of the carbon emissions. A lot of these technologies presumably are lower carbon footprint on a life cycle basis. So how do we get increased take up of these technologies here, where we're generating the problems for everyone else to solve still? Big question for you, just how to fix the planet.
I'm not going to go into politics. Look, I think you have to, you've got what you've got. And that when you've got a whole lot of infrastructure, it's already there, it's sunk capital, there's a whole lot of knowledge about how to run it, and institutionally it's enough of a change to even get your head around zero carbon wastewater treatment plants, zero carbon, things like that. Those are the important things in your context that you've got to get your head around. You can't pretend that that 200 years hasn't gone past and you haven't invested in those sorts of skills. I think what's important is that the places that haven't invested in it are able to do that technology leap. I would imagine most households in the UK still have telephone wires going to it, even though cell phones are everywhere. You haven't thrown away that whole investment into copper cables and things. But whereas cell phones are ubiquitous in developing countries, and there's copper infrastructure is not there. So
reinvest when there are opportunities.
Yeah, go from where you are, not where you'd like to be.
Yeah, I do find it slightly frustrating being in a country where these nature-based solutions particularly are, they seem to gain virtually no traction. Constructed wetlands are a bit niche. Anything beyond a constructed wetland, we just don't seem to go there at all, either for water management or in terms of wastewater, but also in terms of urban infrastructure. I mean, I've been discussing SUDs with people for probably 15 years, and it's been a great idea for 15 years, and yet we're still not seeing that investment in our city infrastructure. It is damned frustrating. Yeah, let's not get into the politics.
Is it not?
Presumably, there's got to be a tipping point at some time when these things become the mainstream.
Is it not part of the thing? Low tech isn't sexy enough to have an uptake. Look, we were talking. I think someone dropped in talking about trickling filters. There's old wastewater tech. We rarely put them in because everybody thinks they're old tech, although they're robust as anything. And this is where we're coming in at a level that is low tech. They don't want to put in low tech. It's not sexy enough. It's got an image problem.
You've got to wire it to the internet somehow.
Yeah, you've got to add some bells and whistles on to it to get help traction.
Yeah. Yeah, I didn't follow the conversation or the virtual site visits in the other room. I don't know if this was a topic there in terms of how to increase uptake of these kind of solutions.
Not really, but Anna mentioned that there was even a lot of interest at the little village where they had the little mill. Am I not loud enough? Better now?
You're quite quiet.
Yeah, it's better now? Not yet? Okay. Then I stay silent. It's not better? Not? Okay. Don't know what to do. Okay, forget about it.
It's fine. It's fine. No, we can hear you if we don't say anything, Christoph.
Okay. In Scotland at the demo site, the people in the village were very much interested in the technology. So they said there was a lot of response from the people here. And what I want to mention is, I think it's these constructed wetlands or nature-based solutions. I think it's not a question of politics. I think it's also something to raise awareness in the public. So I think it's also a big media issue. Mm-hmm. And so that media should report more on that or give information. And I think many journalists are not informed about it or papers. So I think that's tremendous task to do something in that field as well.
Yeah, I was struck by comments probably from Chris and Claire about the wrong things ending up in the system, and that of course is a common theme here. We have issues with wet wipes being flushed, so the parts of the industry have responded with flushable wet wipes, which have their own branding associated with them. But of course, then you require the householder to be able to distinguish between a flushable and a non-flushable wipe and understand what the messaging looks like to change the behaviors, which means that you still get the wrong thing going down the toilet. So at some point you kind of beg for a political intervention just to ban all these things completely, or say any wipe, it goes in the solid waste bin, it goes nowhere near a toilet. Keep it simple. These things just aren't going to go down there. But the whole question of behavior change, communication, and when regulation has to step in to change behaviors, again, I get this feeling we're kind of edging towards a tipping point in our market. There's been a lot of faith up until this point that the public will do the right thing. But my perspective is it's becoming incredibly difficult for the public to know what the right thing is to do. So where do they get those messages? Where do they get trustworthy information about flushing behaviors, throwing behaviors, sustainability behaviors more generally? I don't have an answer to that question. It's something I've been exploring for the past year or so.
David, can I say something?
Go for it, Andrew.
From Freeland. I think listening to everything that I've heard today, I think the message is a bit complicated for the guy in the street. I think there's a real driver to get rid of or to get further treatment on septic tanks. And I've not heard a real concrete solution to that today. So we need a simple answer to that. That there is a driver to do that. So let's do something that's doable right now. That could be done. That needs to be done. So that's one issue. I think the second issue is I like the urban discussions around green walling, and I think that needs to take on a number of guises. And there's a number of solutions which he sort of, I think, suggested. There was the energy issue, there was the building management issue, and there's also the air quality issue. If they were all built together, then it's a complicated problem to put them all together, but it needs to be put into a package that people just go, yeah, that's the size of problem I've got, and this is what I need to do. I think I'm just confused. I mean, I think I'm a smartish guy, but I'm confused by what you've been saying. I'm not feeling a simple solution to any of it. I'm not seeing a decision to make. If I'm a buyer, I want to know what the decision is. I've heard all this, and I don't know what the decision process is.
Yeah, well, that's you've kind of nicely articulated a societal problem, Andrew. It's difficult to know what the right thing to do is, particularly when we start kind of taking a systems approach. It is complicated. But kind of my argument would be that most people, probably all of us in certain circumstances, don't need or shouldn't have to think about that. The only option available to us should be the right option, but we're not there.
Yeah, but that's why we've got to give the punter the right, just a very simple decision. We make it complicated, nobody's going to do anything.
I agree. Yeah.
It's simple in life. If they're not, nobody's going to do anything. And that's what we've not got right. There's all these clever minds, but we've not got a simple solution. We've not got, this is a decision you need to make. This is an option that you need to decide upon. And I don't feel I've got any of that today. Sorry, guys. I'm more confused than I was before I came in. Sorry.
Hello, my name is Tayo. I was just wanting to say something. Firstly, thank you for the really stimulating, thought-provoking day that's really given me lots to think about. I was just looking at Claire's comment there, and that actually reflects what I was going to say. In some of the work that I do, and my background's wastewater, but I'm also doing work linked to flood alleviation. And the other day, when I was talking about my work, someone said to me, the work you do is fleet of foot, as in, and it's very nifty. And it is about thinking about all these, sustainability, these different things, because some of the solutions that you're putting forward, as well as putting a tick box in wastewater, do put a tick box on lots of other things as well. So in terms of sort of getting funding and actually getting buy-in from community, etc., that works very well because you are ticking more than one box. And I think, and it is difficult, coming back to what Andrew said, it's not easy. And some places it will be easy, but in many, particularly the sort of strategic, larger projects, it is complex. But the joy is when you get it right and you do get the different partners working together and you do get a project where water management per se wins the day, and you're also getting that community engagement where people actually understand wastewater, because many people actually haven't got a clue. But thank you for the fantastic day.
Thank you, Tara. Thank you for that feedback. It's greatly appreciated. If you have the answer for us, please feel free to share it.
I would say it's good
that
it's good that we're hearing from like Andrew and Theo, because they know the conventional. We're in the industry. This is what we know, and this is what we talk day in, day out. So we're hearing it from a different view. The other bit, I think David was saying, so how do we get traction, all the rest of it. The other thing was when we do build even just root beds out there, in the wastewater context, it's now a wastewater treatment works. So we put high-linked security fencing around it to keep everybody away, because it's a wastewater plant. So even though it might be nice and green looking, we do our damnedest to keep everybody away.
Well, I think, I'm just going back again. I did enjoy today, to be honest. I was informed. I did know a little bit more about a lot of this, but I am a water treatment guy. But